Good. Uh, Dennis, can you quickly confirm that audio video screen is working and then we can get started? Okay, perfect. Then I think we can get started. So after delayed flights, technical problems, finally we all made it here. We can get started. Yeah. Good morning, everyone. I would like to welcome everyone to CODAI 2026 here in Krakow. It's great that all of you made it here. I mean, it's amazing to see so many familiar faces. Guys here in audience here live at High Peak on site, people online on YouTube, welcome. The second time we are streaming, really great. So let me introduce myself. My name is Michael Gleiber. I'm with Encharge AI, the director of compiler engineering. I'm also the general chair of the CODAI workshop. And I now officially would like to open the 4th edition of CODAI. Today, you will see a mix of original research, state-of-the-art systems. Please feel free to interrupt, ask questions, push back, continue in the breaks with the discussion. I mean, that is what this workshop is for. And CODAI is only best when it is interactive. CODAI is also about bringing people together. So we want to unite the academic and industrial communities. So that is what CODAI is about. In particular, we want to connect these communities to discuss, hey, what runs in AI compilers, what scales, what breaks, and what doesn't work, and what does work well once a model leaves the lab. So this mix, the mix of this workshop is intentionally interactive. That is exactly the point. So please feel free to contribute and ask questions. So one new thing we have this year is the interactive panel discussion. So during lunch, so don't, leave for lunch, but come back early. At about halftime of the lunch, we will have a panel discussion about future challenges, current and future challenges of AI compilers. We have so many great speakers who could only really squeeze it in at lunch, but we still wanted to give this back to the community. I would also really like to thank our sponsors here briefly, IC Resources and Huawei for supporting CODAI. This workshop really cannot happen without support. So thank you very much. It is highly appreciated. Yeah, now, before coming to the important parts, all of the talks, let me quickly introduce the CODAI team. So we have Sebastian Vogel, who is the general co-chair, who is a director of AI with MSP. Dennis Lieber, our program chair, he is with Accelera, currently not here, but remote with us and helping us on the team with Accelera AI and Miguel Avila with Aptiv. So only due to the help of this great team, it was possible to make CODAI happen in the current form. So now let's go directly dive into it and get started with session 1. So we have a really great program. For session 1, we'll start with Moritz Riesterer with NXP. He will present us the presentation with the name Building a Retargetable AI Compiler using IRI, followed by the heterogeneous execution of AI accelerators with IRI by Maximilian Bartel with Roofline. So with that, I'll hand over to Moritz, and let's give it a backhand. Okay. We good? Java. Yeah. Okay, thanks again. Sorry. Yeah, welcome everyone in the room. Welcome everyone online. It's really an honor to open this year's CODAI workshop. And yeah, in my talk, I want to give you an overview about building retargetable AI compilers using ERI. And of course, it's also kind of a journey that we are on at NXP. So I try to take you on that journey with me. So today I want to first start to explain a bit, why does NXP anyway need a retargeted AI compiler, and what do we need it for? And then I want to give a brief overview about ERI. What is ERI? Since I guess not everyone is familiar with ERI. And then I want to give you 3 concrete examples that we explored. The first one is what kind of model coverage we can expect across different application domains when we use ERI. Then we also used ERI to deploy machine learning models on MCUs. So I want to talk a bit about that, and also our steps to make it actually performant. And yeah, in the last point, I also want to talk about how we extended ERI to make it ready for our EIQ and NPU. And then I want to close the talk with some lessons learned, with some nice things and also some challenges that we've seen. So why does NXP need a retargetable AI compiler? So us at NXP, we mainly serve automotive and industrial use cases. And especially for the AI side of things, we also see different use cases from different domains. So we have audio use cases, vision use cases, some even radar use cases, and more recently also more and more language models or generative use cases. So that's on the domain side. But of course, NXP is a semiconductor company, so our main focus is on the hardware portfolio that we build. And that is quite broad. So we really have tiny MCU solutions, then more crossover MCU solutions, so with a bit more memory, a bit more compute resources, and then up to some really more or less powerful application processors. And in a recent addition, we have now even have discrete NPU solutions. So now, of course, if you want to deploy machine learning use cases to this hardware portfolio, we also see that customers, they come with models developed in different ML frameworks, right? So in TensorFlow, PyTorch, they bring it in Onyx formats, in LiteRT formats. And of course, for us, we need to kind of serve all of these machine learning models. And that kind of brings the necessity for us to give our customers a solution that is really retargetable. And in our work, we actually identified ERI as a quite nice framework to provide such a solution. And that's why we decided, okay, let's build really this retargetable AI compiler leveraging ERI. And ERI is really, really scalable and extensible infrastructure. So as a brief overview, what ERI is that it's really more like an ML compiler ecosystem. So it comes with some default setup, but that's not everything. So the first step is, of course, you have your ML frameworks, be it TensorFlow, PyTorch, whatever. And then you kind of import that in a first step into some MLIR dialects. So for the input dialects, ERI actually supports stable HLO, the TOSA dialect, or the Torch dialect. And that then gets further lowered, usually into the linear Algon tensor level. And on that level, you can do some nice graph optimization, such as fusion, kind of propagate transposes and reshapes, or you do some canonicalization.
And at that point, then Erie kind of splits between the host and the device. So for the host code generation, which is more or less the control flow, Erie actually defines some new MLIR dialects with the flow, the stream, and the hull dialect. And on there, you can do like some partitioning. You do the definition on what devices you want to deploy your workflows. You do the scheduling and the buffer and execution management. And on the device code generation, that is then actually really like the executables that are running on the target devices. And there, Erie also comes with like a nice support, for example, to lower to LLVM or to SPIR-V or to some virtual machine that you can run basically everywhere, but which is not super performant in the end. And then in the end, Erie brings that all together and serializes that into their virtual machine flat buffer. And that you can then deploy with Erie's runtime. And the runtime actually is not only like not only like taking this flat buffer and executing it, but you can also nicely define different hardware abstraction backends that Erie comes with. So you have support for CPUs, for Vulkan, for CUDA, Metal, ROCm, and so on. But the cool thing is about Erie, you can use all of that, but it also comes with like a lot of extension points. So you can actually customize Erie at almost every level of the compile flow. And even on the runtime, you can kind of bring your own hardware abstraction layer and you're good to go. And in the next three examples, I want to show you how we at NXP kind of leverage these extension points and yeah, customize Erie for our needs. So if you go back to our overview where we are, so the first focus I want to highlight is now how Erie performs across different domains and across different ML frameworks. And for that, we kind of did an analysis and a comparison with other more or less state-of-the-art frameworks like LightRT, Onyx Runtime, or Executorch. And we also have like models from audio, vision, radar, and language models. So I think it's exactly 40 models that we kind of benchmarked. And what you can see here is actually like what we call the deployment success rate. So what can you deploy out of the box and it's just running? In this case, we deploy to an Cortex-A CPU. So it's not a specific target, but it should give us a good idea of what can we actually deploy with Erie. And what you can see is that like the established frameworks, I would call them, they perform relatively well on different domains. So you see, for example, LightRT has a rather good coverage for audio models and vision models that we've seen. Onyx Runtime is also quite good for language models and even for some of our radar models that we benchmarked. And Executorch is kind of good on language models. I mean, it supports everything, but for the other domains, it's really like lacking behind. And what we've seen now with Erie, so we just chose an Erie 3.6 version. I mean, there are newer versions, but I think the numbers would look similar. That the coverage that we get across all these domains is actually quite okay. So for vision and language models, it's really good. For radar, there are still some challenges there. And for audio, it's also sort of okay-ish. So you can see that if you just use Erie out of the box, well, you get a certain coverage. It's not perfect, but it's a starting point, right? And then we actually teamed up with Roofline. So Max is here from Roofline. He will talk after me. And we said, okay, let's further push that. And with Roofline, we actually extended also the model zoo to 83 models. And across all these domains, we actually got a super nice coverage of 95% across domains. And that kind of also shows that this Erie ecosystem is really, really strong. So you can, for example, collaborate with Roofline or in general, make use of the ecosystem and you can get really nice results. So with that being said, so the first part is covered like the domain. So we can see, okay, we can use Erie to kind of cover our needs. So then in the second step, I want to talk a bit about how you can use Erie for your microcontrollers, right? Because that is like a big part of our portfolio, and we definitely need to have a solution for that. And Erie for microcontrollers actually comes with like a subset of options, and they call it Tiny Erie. So there's a There's a nice paper about it. I referenced it here. And you can imagine it that you can basically strip down certain parts of Erie to make it more efficient for your microcontrollers, because you don't need some parts of the Erie compiler or the hardware abstraction layer, for example, that are more or less overhead, because usually on a microcontroller, you just have a single-threaded execution, so you don't need all this multi-threading support. So we just said, okay, let's take this tiny Erie subset of options and benchmark that on our microcontroller portfolio. And what we've seen is the one here on the right side, that we compared it also with kind of TensorFlow Lite for microcontrollers and micro TVM. And what you can see is that, unfortunately, the performance that you get out of the box is really not nice. So what you see is that the lower is better in this case, right? So because we normalized it. So in this case, usually TensorFlow Lite Micro gives the best performance. For micro TVM, we just used it out of the box, so we didn't really use the auto-tuning capabilities. But you can see that the tiny Erie out of the box is between 50% and even sometimes 100% overhead when it just comes to the latencies that you get for the models here of the MLPerf tiny benchmark. And of course, that's not good news, right? Because for us, it's quite important that we get good performance also for our microcontroller portfolio. And we were thinking like, okay, where is this performance lag coming from? And if you look into TF Lite Micro, and even micro TVM has some options to actually integrate the CMSIS NN library from ARM, which is like a library of optimized ML kernels, specifically targeting Cortex-M devices. And the analysis actually revealed that the kernels that Erie generates are really the problem. So it's not really like the runtime overhead, it's really like the kernels that are not performing well. And that led us to the idea of, okay, let's maybe try to integrate CMSIS NN kernels into the Erie flow. And maybe we can even dynamically decide if we want to choose CMSIS NN kernels or the Erie generated kernels. And we did that kind of by extending Erie in this global optimization phase or the pre-processing phase. And we then implemented kind of this compile time selection of full code generation versus using like the CMSIS NN kernels. And how we did that is, well, so first of all, we really chose a lot of different like kernel configurations and benchmarked them on our devices. So both for the generated kernels from Erie as well as for CMSIS. And then we kind of trained like this tiny decision tree that then helps us during compile time to say, okay, for this configuration, I want to go with the one or the other. And then we integrated that through a pass. So from linalg, we actually have this label by backend pass that is then just annotating like this IR with like an attribute, which is then just say, okay, this part should be deployed using Erie CodeGen, the other part should be deployed using the CMSIS kernels. And then after this annotation, we actually made use of a nice feature in Erie, which is called like writing your custom dispatches. And how that works is that basically you can make use of the transform dialect in MLIR. And in this transform spec that you basically write, you basically define, okay, what is the input MLIR that you want to match? How do you want to rewrite this IR? And then you can also define, like, for example, external functions that you say, okay, hey, compiler, here's my external library. Be aware of it, that you can use it, and during runtime, please use it then. And in this way, you can then basically pattern match like now this annotated linalg operations with the CMSIS annotation, and we can just replace it with like library calls into CMSIS kernels. And there's already an integrated pass in Erie for like an interpreter pass, which is then interpreting this transform spec and applying this transformation. And the result of it is then that we basically have a mixed IR between like still some linalg operations that we didn't touch and some just function call operations basically into the CMSIS NN kernels. And another important thing is that we can also actually switch the compiler that we use for example, compiling the CMZN kernels. Because that was also a limitation that we've seen in our analysis before, that a big portion to this lack of performance is also coming from the LLVM compiler, because it's not really optimized for these Cortex-M devices. And GCC does a better job here. And since we keep like this library separate, we can even then compile the library with GCC and then still link everything together in our virtual flat buffer. And with all that integration, we actually got quite nice result, and we brought down like the tiny ERI performance kind of on par with TensorFlow Lite Micro and Micro TVL. So, and that gives us a good baseline now for further optimizations. I mean, you can of course think of like, okay, how can we even further improve the code gen side, right? But since we have that kind of as a backup solution, I think tiny ERI really becomes a solution that we can also use for our customers. Okay, so now I was talking about the domains, I was talking about microcontrollers. And in my last point, I actually want to touch on how we also support some custom NPUs, such as the EIQ Neutron NPU that we have. But before diving into like the specifics, how we extended ERI for that, I want to give you a brief overview about what is EIQ Neutron. So it's kind of our scalable integrated NPU. And here on the right, you see like a high level diagram. There's also a nice paper about EIQ Neutron, by the way. So I recommend taking a look at it. It's also taken from there. But what Neutron is basically, it has like a compute engine, and within the compute engine, you have like an dot product engine, basically, a part for activation units. And you have a data engine, and you have like some scratchpad. And you can basically now scale the NPU by just adding more of these compute engines. And you can either use these compute engines like in isolation. So that's what we, for example, do in our microcontrollers. Or you can use it as a complete subsystem. And when you use it in a subsystem, we basically add like some tightly coupled memory, some DMAs, and even some RISC-V control cores. And kind of the programming model, or how you can use Neutron today, is actually through a kernel library. So we have a set of optimized C kernels that are more or less implementing like different layers of modern machine learning models. And how we actually then program Neutron to use this kind of kernels is done through a backend compiler. And the goal of this backend compiler is then to generate like some microcode, and the microcode is then containing some compute jobs, data transfer jobs, and also some synchronization barriers for Neutron. But today, this solution kind of leverages LiteRT. So for the backend compiler, the front end and also the output is a LiteRT model, and also the host runtime is actually LiteRT. So we have like LiteRT integration for Neutron, and that is a bit of a bottleneck, right? Because as you've seen in this domains before, like we cannot always go through LiteRT, because with some domains it's just hard to cover that. So we asked the question, okay, how can we actually leverage ERI to kind of connect this solution with its extensive front end, right? And we did that in kind of two steps. So the first one was that we said, okay, we somehow need to bridge ERI or MLIR in the wider sense to our backend compiler. And for that, it was clear that we need to define like an interface, and that interface is now an own dialect for Neutron. So we call it a Neutron dialect. And that really allowed us now to integrate it into an ERI compilation flow. And so in a first step, we again just take these funneled inputs from ERI, and we work on a linear level. And then we just like wrote kind of a conversion from linear to Neutron. So for just of course, just for the ops that Neutron actually supports. And then once we had that, we could also like integrate like this backend compiler into our conversion flow. So through a few passes that you see here on the left, we actually like lower than this Neutron IR through our Neutron converter, and then get back like this microcode and embed it again in some custom operations that we call the neutron microcode dialect. And then in the end, we can apply the same as we did before with like the microcontroller stuff. We can again write a transform spec that is pattern matching like this neutron microcode operations. Then it is basically then replacing it with some functions that are then just calling, for example, the neutron driver with the generated microcode and so on. And then we can just go on with the flow. And in this way, we achieve the same thing like before. We can keep whatever we want in Linalg and code gen it, for example, for the CPU. But we can also then specialize it for this function calls into Neutron. And of course, that was more on the compiler side, but we also needed some work to do on the runtime side. So what we did was then also to extend the runtime side with an hardware abstraction layer backend for Neutron that is mainly taking care of like the buffer allocations, because Neutron has some specific requirements when it comes to the buffer allocations. And for the runtime, of course, it was also necessary to integrate the Neutron driver and calling the Neutron firmware. And that was then all nicely done in Erie. And so with that integration, we now have a nice kind of alternative to this light RT specific flow using Erie, and that is opening up like the use cases to all kind of model formats and so on. Yeah, so with these three examples, I hope I could kind of convince everyone that Erie is really a nice platform or a nice ecosystem, right, to work with and to super extensible and quite flexible. So to the end of my talk, I want to touch a bit on our lessons learned, right? So what did we learn from all of that? So I think what we really saw is that Erie is nicely scalable, right? So you can really use it, like you can strip it down for microcontrollers, you can just use it as is, you can extend it. However, one of the challenges that we've seen is that for most of the use cases or for most of the targets, out of the box performance is still not great. So I think there's really some work needed to further improve that. Then of course we've seen that Erie is nicely extensible, right? So with all these extension points in the compiler as well as in the runtime, you can really customize Erie for your needs. So whatever target you have, whatever programming model you follow, Erie kind of helps you with it. One challenge that we faced over our journey is that a lot of these specifics, like how to extend Erie here and there, the documentation is really a bit lacking. So it's a lot of tedious work, and you need some time to really understand Erie. So I think there maybe we as a community, we could really try to improve that further to make it also easier for others to adapt Erie. And of course, the last thing, and that was the main focus of my talk today, is this retargetability, right? So as we've seen is that Erie supports kind of most of the common machine learning frameworks. It comes with a lot of support for different devices from CPUs, GPUs, and so on. And then if you take that scalability, if you take that extensibility, Erie really helps you to build like a retargetable AI compiler. However, if you really want to build like this end-to-end compiler, one challenge that we also faced is that the testing that Erie brings like out of the box is also a bit limited. So from Erie version to Erie version, sometimes you see things break or things change, performance drops and so on. So I think having a really robust like of testing, even for the upstream Erie, would really like help in maybe further boosting the adoption of Erie. And as a last message, maybe I want to finish. So we are really convinced that Erie is a great platform for building compilers and also for experimenting. So our hope is really that we as a community can grow the Erie ecosystem together and make it a success. Thank you very much. And happy to answer your questions, of course.
Yeah, thank you, Moritz. So any questions from the audience? Please.
Yeah. I think there are two open sourced solutions. So I think AMD has a plugin for their AIE accelerator. And I think recently also Synaptics, I think they open sourced their compiler. So when it comes to like how to write a plugin and how to do this, I think that is also a nice inspiration how to get started. Of course, understanding the details is then also a lot of kind of code reading, but at least that's a good starting point, I think. Yeah. Yeah. I don't know. Yeah.
Local correctness issues, right, with types and so on. But at the moment you start doing more global changes, I think it's hard. Is that something you encounter or?
Yeah, I mean, one thing we also realized is that the pattern matching in a transformer, like as you said, right, it's very specific. Like if you have a data type or like even some attributes, right, it's for every different configuration, like you need a new pattern, and that doesn't really scale, right? So it's really hard to pattern match these kernels. So what we think is it's a good starting point, you know, to get something running. However, in the long run, maybe, yeah, we would like to rather translate it into some passes that are a bit more flexible. But to just get something running, it was a quite nice tool because, yeah, you can describe everything in MLIR, so it's rather nice.
Thanks.
I think we can take one more question. Please up there.
I have a quick question, Georgie from HTEC. You said that you're struggling with the performance, right? When using LLVM. So my question is, what version of LLVM you're using? Because some companies compare some older version of LLVM with GCC, which is not fair. So
yeah, so for this, I mean, that was specific for microcontrollers, right? For other targets might be different. I mean, we just used at that time the LLVM version that was used in IRI. I would actually have to look up what version they used, but usually IRI is quite close to the main LLVM.
Okay, so because LLVM community is doing a lot to reduce the gap.
Yeah.
Okay, thank you.
Okay. Thank you. Yeah. With that, thank you for the questions. Thank you, Moritz, very much for the talk. Let's give him a back hand. Was really great. So after Moritz, we have Max. Max, can you quickly help me find slides? Here, these guys. Okay, just F5. Okay, so up next is Maximilian Bartel. So Max is the CTO of Roofline AI. He has innovated in the compiler space for quite some time. He's very good in understanding AI hardware, AI software, and is into efficient and modern machine learning workloads. So he's going to show us the talk with the title Heterogeneous Execution of Accelerators using IRI. Let's give a back hand to Max.
Yeah, thank you for the nice introduction. Let me first start a bit with what we are doing at Roofline. And the problem that we are seeing in the industry that building edge AI products is painful. For the best-in-class solutions like NVIDIA has, normally deploying an AI model could be done in less than an hour. But if we take a look at a lot of the accelerators that are out in the industry for edge devices, after a lot of interviews with customers, it normally means 3 months plus. And then there are often complaints like, my model is not supported, my model is too slow, or how does it work? And sometimes even takes them a year to get a model running, but they want to iterate faster. They want to try out new models, new use cases. And this is simply not possible with the tools that are out there. This is exactly where we plug in with Roofline and our SDK, where at its core is an IRI-based compiler. So we come out to let you run any AI model on the best chip for your use case. And to get a bit more specific, with any model, we really mean any model. So we support all the major frameworks with TensorFlow, TensorFlow Lite, or LiteRT now, PyTorch, and Onyx, and any model architecture like CNNs, RNNs, and transformers. Then it goes into our software development kit, which consists of the compiler, of the runtime, and also a lot of performance benchmarking that Moritz just mentioned. And then you can run it on any CPU like ARM and RISC-V, which is our focus, but also x86, any GPU, where we have a major focus on SPIR-V for mobile GPUs, and accelerators like the NXP Neutron, which I will show later. But sorry, I'm a bit sick. So with that, for us, it was pretty easy to compile state-of-the-art LLMs at the same time they're released. So day zero support, we call that. So this here is Gemma 3 and multimodal LLM. So we have an image and text input, and we basically ask it, hey, I'm a robot, can I proceed? And based on the image, it says, no, you need to slow down. And it's running fully on device with 9x better performance than Executorch or Torch to compile. And at that time, Llama CPP also didn't support that model. So we're actually faster to support this model than Llama CPP. And this one here is running on a Snapdragon X Elite systems on an ARM chipset. Let's come to the topic I want to discuss in this talk. Because Moritz gave you a very nice introduction to ERIE in general. I want to highlight one of the core features that we have enabled at Roofline, and this is heterogeneous execution. So if your SoC wants to stay relevant in the industry, kind of heterogeneous execution is the only way forward. When you have an accelerator, maybe the accelerator even now doesn't support all the layers. Maybe it's just a systolic array, which can accelerate MAC operations. Or B, it supports all the interesting layers now, but who says that it will be in 5 years? But probably the lifetime of the SoC is a lot longer than that, especially if you're like NXP in the automotive space. The chips that are out there will stay there for a long time. So the only way to make still use of your NPU is via heterogeneous execution in tandem with your CPU or your GPU. And this is a core thing that we needed to enable in our ERIE-based compiler flow and runtime flow to come up to solve this challenge. And now I want to show you first what we needed to do in the compiler, or how we communicate to the compiler that we're going to execute heterogeneously, and also what we needed to do in the runtime to make it usable. Then I will show you a CPU plus GPU example, and also CPU plus Neutron example, so an accelerator that makes a lot, that gets a lot of benefit from the heterogeneous execution model. Cool. So no compiler talk with a bit of IR. It's not much, it's just 2 slides. So let's say we have like an AI model, and we want to execute this Neutron stub.operator on a different device than the rest of the code. So here, Neutron stub, of course, refers to Neutron. So let's say this is going to run Neutron, whereas the rest of the model, like the Linux.generic, which could be like a compute up or whatever, is going to run on CPU. How do we communicate that to the compiler so the compiler can actually optimize memory access patterns, scheduling, things like that? And the way that it's enabled in ERIE is following the API that basically PyTorch implemented. So in PyTorch, you're going to move tensors from device to device. So this is the to-CUDA call that you do, and then you move kind of a tensor to the GPU, and every operation operating on that tensor is going to be executed on the GPU. And it's very similar here. So we're inserting flow.tensor.transfer ops on line 10 and 12, which move the tensor we're operating on from device A to device B, kind of signaling that the operator, Neutron stub that operator on line 11 will be executed on Neutron. And then we also move it back because that was the contract that we had with the function call. So we need to adhere to the contract that the developer gave us here. And there are a few more things. So after the transfer, there will be an analysis dedicated to where each operation is going to be run on, because it's not trivial. If you have just a DAG. Operations is a very general infrastructure. We also introduced on line 4 and 5 2 devices to kind of signal that those are distinct things. And maybe the most interesting part is on line 2 and 3, where where we kind of needed to signal to the compiler what the device topology actually looks like. Because when we're on edge devices, we very often have a unified memory. So kind of both devices can access the same memory and we don't need a copy there. But if you think about more consumer grade things or server grade, if you're going to move from main memory to the GPU, it's not a transparent, maybe it is a transparent access, maybe the GPU can call into the host memory, but it's for sure not a unified memory. So you need to have a bit more infrastructure around that, maybe a copy or things like that. And the compiler needs to know that to make the right decisions on scheduling and things and those things. So this is the compiler part. This then kind of goes into the ERI flow, and we can then compile things for Neutron and the other things for CPU. But we also kind of need to solve this at the runtime level. And let me briefly give you an overview about the ERI runtime as is. So the ERI runtime is super small. It can run on microcontrollers, but AMD also uses it for server applications. So it scales between different devices and is a fully asynchronous execution model in there based on timelines that I will show you a bit later. It can be extended, which the hardware abstraction layers in orange here. And you have one for CPU, for Vulkan, for CUDA, and the runtime in general try to keep it transparent. So for it, you kind of decide on the hardware abstraction layer you're going to run the dispatches on, but the overall runtime code is very device agnostic. The runtime is modeled after Vulkan without all the shader components, which makes it very powerful if your hardware exposes all of these nitty-gritty and details, but it can also be adapted to easier APIs like the Neutron API quite nicely here. The compiler, what it does, it kind of plans the calls into the runtime. We call it shims for allocation, things like that. So the compiler plans how much memory will be allocated later, and the runtime takes that instruction and executes it. And the interface from model to the compiler can be either a VM bytecode, or you can also embed C code for the runtime part. The kernels will still be as low level as possible for CPUs would be ISA. And the scheduling model of ERI runtime is also very powerful. So ERI kind of schedules the whole graph at the same time, and then the execution model is based on an event and semaphore-based system. So here we have the host thread on the left side, then we have a GPU worker and a CPU worker, which is distinct from host. So CPU for us is just a device to execute something on. And then we're with the first 3 calls, kind of giving the overall structure of the execution to the devices. So kind of signaling that GPU will start with semaphore 1, then the CPU needs to wait on that and start with semaphore 2, and then the GPU can then, as soon as semaphore 2 is kind of signaled or over, start execution. And after that, execution starts, and there's no host interaction in between those devices. So the GPU worker and the CPU worker threads are communicating directly with each other without the runtime intervening between that, which makes it very powerful because the host, as soon as you schedule the graph and start the execution, is free. So you can use that for some pre-processing of other data, preparing the next data, running a GUI or things like that. So there's no blocking thing. Just at the very end, most of the APIs, when you mem copy from device to host, there will be a blocking call, but even that can be kind of scheduled into the graph, and then you have a fully async execution model here. So let's start with the GPU example. So the GPU was our test bench for the solid heterogeneous execution model, but we also envision that in the future, there will be cases where you can run NPU and GPU heterogeneous execution instead of NPU plus CPU or GPU plus CPU, which of course would give you a nice benefit because the GPUs are normally faster for the things that we want to execute. Here we just decided on the input size of specific matmuls. So if the matmul is bigger than a certain size, it will be executed on a GPU, and the rest will be executed on the CPU. And a very important, ERI treats CPU just as a device. So the host thread is completely separate from that. So this is a complicated graph. I'm not going through all the details, but one thing that we have to keep in mind is that the semaphores per device, we try to use the device API if possible, because normally that means that we don't have any host interaction. So with Vulkan, we use the Vulkan semaphore event-based system for internal things. And this is a very different timeline that the CPU is on. So how do we kind of communicate with there? And for Vulkan, because there's no host callbacks or something like that, like in the CUDA or HIP API, we kind of built what we call a semaphore bridge, which you see in the middle here on the right side, which kind of tries to bridge the gap between GPU and CPU and just is there to signal things to the CPU device execution model. And with that, with a tiny bit of overhead there for Vulkan, we can still get a fully asynchronous execution model for CPU and Vulkan, which is pretty nice. So this is how it would look like if you were to, if you have a nice resource monitor. This is like an Apple device. So this is actually running Metal, not Vulkan, but they're very similar. And this is running Qwen 3. And parts of the model, the big matmos, are offloaded to the GPU. You see that GPU usage and CPU usage are going up when you execute this. So decoding is memory bound. This is why you don't see like the 100% resource allocation for GPU and CPU. But still, I think this is a very, very cool demo. And this was our test bench with the whole infrastructure here. Let's come to a real world use case for the system. So you saw the same thing in Mo's presentation. It was in collaboration with NXP here. So the NXP Neutron Accelerator is specifically made to accelerate dot product plus activation units. So, but this inherently means that parts of the network cannot run on it. It's a specifically designed accelerator just for those use cases. And here, the whole heterogeneous execution model actually plays to its strengths. Because first of all, we can schedule CPU Neutron completely asynchronous in the whole graph, like I showed you with Vulkan and also the general infrastructure, which is quite nice. But the other nice thing is, because the compiler already knows that the kernel is going to be run on a different device, we can already write the output of the kernel before into that device memory. Basically meaning we have a zero copy between Neutron and CPU here, even though the Neutron memory is only part of the whole host memory that is allocated to the CPU. This is also specifically interesting because the Neutron memory is only 2 GB. So we have a small graph partitioning algorithm running before to make sure we can execute all the models. And now we can actually run models that are bigger than 2 GB with Neutron and Tandem because we offload only the parts that fit on Neutron to Neutron. And this here, LLMs are always a nice demo. So here we're offloading the matmuls with the NXP Gen AI flow to Neutron, and the rest of the model is going to run on the CPU. And especially for prefill, this makes a very big difference. And you see here a small demo of generating text. If you look into it deep, we also needed to say that the lead allocator for the input buffers is the Neutron device, which kind of shows you that this feature is very, very complex to use it effectively. Something that you have to keep in mind. We also got very cool performance numbers with that. So when we execute the model on one CPU core, and this is not so uncommon when you think about it, because in an automotive system, maybe 3 or 4 cores are dedicated to something else. You only have 2 cores to execute your AI model. So this is a very common use case here. When you execute the model on one CPU core versus one CPU core plus Neutron, we get a very nice speed up to 2.3x across the board. Especially the bigger the sequence length, the more we can amortize the overhead of the heterogeneous execution. But even if we go to 3 CPU cores, which is a bit more, you can see speed up of up to 1.8x, which is also pretty nice. At the same time, what we don't show here is that the resource allocation per CPU core also goes down quite a lot, since the main compute ops, the matmos here, are offloaded to a different device. So probably if you tune this a bit more, we can find a sweet spot with 2 or 3 cores where the resources are quite high and Neutron doing a bulk of the work. And then we have 3 cores to do something else on a very on an edge device, which is pretty cool. So this kind of comes to the end of my talk. Just wanted to kind of reiterate the 5 key advantages that you would get when you work with us. Shameless plug here. So you get a full SoC support when you collaborate with us. So we can use CPU, GPU, and NPUs now on your chips. The model coverage, like Moritz showed, is a lot higher than you would get out of the box with Erie, and also it's a unified infrastructure for all of your AI models. Performance is very high. So Moritz showed how we can reach for MCU very high performance, but when we compare us against solutions like TF-Lite and Executorch for bigger systems, we also see that we are oftentimes better than they are. Stability and tooling, we're testing a lot every night, have a big, that's a big focus of us. And of course, the whole Erie ecosystem that we would like to grow together with you, and also happy to help you get started with Erie. And of that leads for you to kind of decrease your time to market when you bring a new chip to the market. And with that, happy to show you our newest advances, especially in tandem with the NPU support for Neutron, and happy to take questions.
Thank you, Max, for these incredibly good insights. Are there any questions from the audience? Don't be shy. Take one over there.
Maybe just one question from my side. So I understand the main benefits of your solution will be execution across multiple accelerators and platforms. Did you actually compare the numbers that you are getting only for GPU or only for NPU comparing to a vendor SDKs? So in one of the example, I saw that you run something on Qualcomm. Did you compare IRE or not necessarily IRE, your solution against some Qualcomm solutions?
Yeah, so for CPU, also for Qualcomm, their main execution stacks are TF-Lite, Onyx Runtime, and Executorch, and we compare us against them. Like every night, we run a very big, over 200 or 300 models now, benchmarking suit, comparing us against those on different devices. We perform very good, very often faster than Executorch. TF-Lite is also very fast, but it kind of lacks a lot of features that it would look like. For the accelerator support, it's a bit harder to compare against other things, but we're also doing that for the customers, yes.
If there's no other questions from the audience, I would have a question. Briefly, we heard the question earlier on that pattern matching on different levels of IRs is ultimately the key to bring the right part of a model to the appropriate execution mode. I'm wondering, do you have a suggestion or what's your view from a software company? What would you expect from the hardware enablers, right? IP providers, SoC integrators. What level of SDK integration would you like to see? Is there some quasi standards already that are being built that we would say, to take an example where ARM is going, right, saying TOSA is the way to abstract it, or would it be a different IR that you would expect? So generally, where do you see, where would your wish go if you said, hey, IP providers, this is how we would like to see an execution backend being provided?
It's a good question. Depends on the hardware. So if it's a fully programmable DSP, for example, I kind of the best case would be that we have an MLIR dialect that would have all the vector intrinsics for the DSP. So we can kind of plug it in with the default MLIR infrastructure. If your device is more like an ASIC that has bigger kernels or has the necessity for that, then something more on the stable HLO or Linux level would make sense. And then there's also thing in the middle where your accelerator is very good at specific tensor sizes like 16 by 16 by 16 matmos, and kind of exposing that to the compiler would also be very helpful. So like Moritz said, ERI is very extensible, or MLR in general is very extensible. But a small MLR dialect, so we can plug into those things, makes the integration time a lot less.
Thanks.
Okay. Any last question before we leave into the break? If not, then thank you very much, Max. Yep, and then we will be back after the break.
Nicht mehr fragen. Ich frage mich so, also war das nicht einfach ein Button da unten zu landen? Nee, da war was. Ja. So, wie switch wir jetzt wieder auf? Ich glaube, ich habe nur das Ding, wie praktisch das Participant bin, aber noch draußen. Passt. Aber das ist.
Okay, welcome back everyone to our session number 2. My name is Dennis Rieber. I'm with Accelera AI. And now I have the pleasure to lead you through the next 90 minutes, which is kind of the academic block of the CODAI workshop. And I'm especially happy that I can not only welcome, but I can welcome back Geronimo Castellon from TU Dresden. He was already here before at our workshop in Hamburg. And now he is back to talk about compilers for in-memory computing systems. Please.
All right. Yeah. Thanks for the kind introduction. Thanks for inviting me again. So it seems it wasn't as boring last time. So yeah, I'm gonna be talking about compilers for in-memory computing. So in general, in my group at TU Dresden, we work on emerging computing systems. So we heard about heterogeneous computing before. That's something that I've been working on since maybe 2006. So we look into sort of systems with HBM, right? And we do have CPU, GPU. The AI engines were also mentioned this morning in the keynote. So we have been working also on compilation for the AI engines for AMD. And more closer to the topic of this talk are near memory computing systems like this one from Samsung or this one from UpMem that maybe some of you would be familiar, which is like trying to move computation closer to where the data is located. And then an extreme case of that is in-memory computing, where you perhaps leverage the physics of the memory cells to implement some computation. So today I will be focusing on this sort of compilation, and we'll report a little bit on these aspects as well, just to give you an overview of what we have been working on in the past 3-4 years. All right, so for those of you that do not know, so the motivation for in-memory or near-memory computing is actually well described by this little diagram here that I stole, which shows the energy that you need to do the actual computation compared to the energy that you need to move data around a chip, right? Which is here in the orders of 20 picojoules, and depending where the data resides, it could be 16 nanojoules, so which is like 3 orders of magnitude higher. So that's sort of the motivation to do compute near memory or in memory. So there's been a lot of architectures doing this sort of paradigm. We actually wrote a review focusing on commercially viable solutions a couple of years ago, and that has already evolved quite a bit. So there's a lot of these proposals about how to implement architectures that can achieve this. All right, so kind of the idea is to reduce the phenomenal bottleneck that you have in classical computing systems. All right, so if you look at some of these examples from the computer architecture domain, you'll find plots that look like this. So this is a Nature Communications article where they showed several orders of magnitude improvements in terms of execution time and energy consumption. So these are actually great results. This is for executing memory augmented neural networks. And then similar results you will find here. I think this was for hyperdimensional computing using content addressable memories. And so in most of these works, and I'm just highlighting these works just as examples, but if you see most of those works, we'd always promise or show that they could achieve incredible gains in terms of latency and energy consumption. So I think this is great. So from my point of view is from these great designs that sometimes are very special purpose, often you can actually abuse those designs and use them for other workloads. So that has motivated some of the things that we've been doing, and I'll be talking about, which is how can we generalize out of these designs and maybe build compiler infrastructures that allow to use those accelerators automatically instead of having to design them by hand and sort of hand-tuned applications by tedious work by PhD students, I guess, right? Okay, so that's as a brief motivation of how can we get these results for generalized applications via compiler methods. So in that context, I've been working also on high-level abstractions. We heard about MLIR this morning, so we work on MLIR as well. And this is a slide that I have shown multiple times where what you see here is something that you want to code, which is this is a mathematical kernel, it's an interpolation kernel that appears in high-performance computing codes. And if you're very naive, you would go and write it like this. And if you are an expert programmer or you're using a tooling to generate code out of a DSL, you get actually an implementation that looks like this. And this implementation is already 100 times faster on a traditional CPU, right? And the reason why this is way faster, even though, I mean, this loop does not look very complicated, and you could actually apply polyhedral compiler, you can apply many things. There's a lot of stuff that goes unnoticed by the compiler to be able to optimize it all the way here. Right? That's why I use this very simple example to show that once you have chosen a very low-level abstraction, it's very difficult to reconstruct the semantics of what the programmer intended to do, in this case, an interpolation kernel, to maybe leverage algebraic properties or factorization of these expressions to create a code that can execute in parallel using vector instructions using multiple threads, all right? So the reason I use this code is because even though it is very simple, we can see that with advanced compilation techniques, we fail to bridge this gap of 100x on mainstream CPUs. So it's very hard to imagine that we would be able to bridge this gap for, say, more exotic architectures, including in-memory computing, near-memory computing, or maybe some of the heterogeneous SoCs that were mentioned in this morning's session. All right, so MLIR or high-level compilation methods, I think, are a great vehicle because then we now have some high-level abstractions so that we can maybe reason about tensors and tensor algebra, convolutions, or maybe come from databases. Yeah, so databases, relational algebra. Then you can lower that down to maybe some tensils and what you can do with stencils, sorry, or with linear algebra, as we saw before in the lineage dialect in MLIR. And then you progressively lower these abstractions and do optimizations at the right level of abstraction, which makes it easier to implement. So yeah, and this is a story that has been successful in many domains. And just to give you an example, so this expression can be implemented in multiple different ways if you can leverage the algebraic properties of these operators. And any of these reorganizations will give you fundamentally different ways of writing that application or that kernel into for loops. And it is way easier to do these transformations as it is to implement those transformations once you have already have a C code that has married itself to a given schedule of operations. So just to give you an example, so yeah, so that code that you saw there, so we worked many years ago on sort of embedding that DSL for tensors for HPC computations here in Fortran or here in C++, and actually demonstrated that you can beat manually written code for these HPC kernels. So here higher is better. Green and red are versions provided by the compiler. Blue is handwritten for Fortran code, and these purple ones are ones using optimized libraries. So I saw before, for instance, that very often in compilers we sort of lower the code to use optimized libraries. And here, if you choose the abstraction correctly, you can even do better than optimized library because you know the sizes, you know a lot of things of what is going on in those kernels. So you can actually beat as well libraries that are optimized for a given size or a given kernel. And that's even without already taking into account optimizations that a DSL compiler can implement across the boundaries of functions, which I think is also a great added value of working with high-level abstractions in a framework like MLIR. Okay, so this is quite old. So more recently, we have extended this DSL. I'm not just going to talk so much, but it's an interesting activity that we've been doing in MLIR, where we do all of the language development in MLIR. And here, just to give you an idea, this is sort of the DSL now. It looks very Python-y. It's inspired by NumPy. And now we can generate code, efficient code, for even complex expressions with tensors that use another arrays to index into tensors. So subscript of subscripts, which is actually quite challenging to implement in compilers and optimize for, can be expressed in this simple NumPy code, which implements this computation, which is used in weather modeling. And yeah, that's quite a difference in terms of lines of code. All right, so that's on the side of abstractions and modeling software operations. So now let me go back to this in-memory computing kind of idea. So we have here maybe some high-level operations represent a vector addition. This is how it would be represented with an explicit loop. And in the end, in MLIR, you would model that in say in an LVM IR, which looks very pretty much load store. This is a very von Neumann model under the hood. So most of the infrastructure is built on the von Neumann infrastructure anyway. So now if you go and look what the addition would look like if you are, say, using logic in memory, so say logic in DRAM, if you would like to code this addition in logic in DRAM, this is what you would find as a code, right? So here you see some logic operations, some NOT and majority gates being applied, some signals, and eventually this would compute the addition that you want to do, but it's just doing it directly in the DRAM cells. And perhaps even more exotic, if you use content addressable memories, which is a way of, say, storing sort of lookup tables into the memory, then the paradigm that you use to compute with content addressable memory is so-called search and write. So you search for a pattern. So this pattern will be massively matched in the memory array. And once that pattern is matched, you can then decide to write something. So this is sort of looking into a lookup table, and once you have a hit, then you change a bit, for instance, right? And that's how you compute with content addressable memories. So both of these implementations are actually operating in a bit slice manner through multiple words in memory. So it's a very different abstraction, or it's a very different compute model than the von Neumann model that our MLIR and LLVM infrastructure has been built upon. So in my view, we sort of need a more bottom-up analysis of what these primitives are, what we can achieve with these in-memory computing engines, so that we can then build bottom-up abstractions from the compiler point of view, so that we can actually generalize and use these accelerators throughout multiple different compute domains. Okay, and on the issue of bottom-up, here I'm using a slide from Mike Niemeyer from Notre Dame, which actually shows this sort of bottom-up very nicely with these arrows. So what you see at the very bottom is a bunch of different technologies that you can use to implement memories. Yeah, you have MRAMs, you have Flash, and so on. So we have a lot of work with them with FEFETs, right, for electric FETs, and what sort of cells you can build with these devices. And for instance, with some of them, you can build CAMs. Some of them you can build crossbars that you can apply, that you can compute operations in the analog domain. And for instance, with these crossbars, perhaps you can then accelerate matrix vector multiplications, and so on and so forth. So this is bottom-up understanding of what can you do with technology, what sort of architectural templates appear, and how these architectural templates can be used to accelerate workloads on different application domains. So that's how we got this landscape of multiple architectures. So with crossbars, CAMs, you can also apply stochastic computing, logic in memory, bit slicing as a paradigm of how you compute. And this is something that we've been studying over the past years, sort of trying to come up with an abstraction of what operations can you execute on these machines. Out of that came a table that looks like this. So I'm not going to go through the table. It's not as perhaps complex as you think. Is you find operations that you would expect, like some arithmetic operations that you can apply on these devices. Maybe something a little bit less standard, like a top K or a symmetry search, because you have CAM support. And the idea is, like the idea that we had was, can we then define this very abstract set of operations so that we can build if you wish, sort of the ISA, but not the ISA for a processor, but sort of the ISA of what these memory devices can execute. All right, so out of that came our what we call this Cinnamon framework, so CINM, compiler infrastructure for near and in-memory computing. So there we started from linear algebra abstraction, so sort of the simpler things, because with that we can actually sort of hook to ML frameworks, but also to other HPC applications. We then built a bunch of intermediate languages for in-memory and near-memory computing, sort of trying to understand what is the abstraction that we want to put in some of these MLIR dialects. And then as discussed also before, using pattern recognition and target-specific models to steer the optimization within the compiler. So yeah, this is something that we actually first put a preprint like in 2023, several years ago. It was presented last year at ASPLOS. And I'm just going to show you some of the examples of the examples compilation flows that you'll find in this compiler. So as I said, you start from, so there is a connection to some of the ML frameworks. There is also a way to pass architectural parameters to the compiler, and I'll talk about that in a minute, sort of to also retarget the compiler, but also to allow design space exploration of the hardware, which relates a little bit to what Devin Sheng was saying this morning in the keynote. All right, so I'll start with a near memory computing example. So this is the UpMem system. And if you're not familiar with the UpMem system, what it is that together with the 64 megabyte of DRAM bank, they attach a very simple in-order processor that can compute some instructions. I just saw a message in the chat. Sorry. So yeah, so you have a small processor with a little scratch-out memories that they call WRAM and IRAM. And so you can process directly on the data that lies in DRAM. So if you want to compute the matrix multiplication expressed here in a high-level language, if you want to write that for this system, you would have to write this sort of code, which is very low level, where you have sort of explicit allocation of addresses for the data. Actually, the interleaving in the DIMMs that have a processor is different to the interleaving of the DIMMs that do not have a processor. So as a program, you have to deal with all these complexities of shuffling data, moving data into the near memory computing engines. So you have to define all of these things per hand. And that's sort of for us as compilers is that we should be able to automate this away. And that was sort of the first flow that we implemented in Cinnamon. So now you can start from a language that looks like this. So this is a high-level DSL for the matrix multiplication. So this is then lower to the lineage abstraction. So nothing very fancy there. And then we can start going into sort of this Cinnamon abstraction of loading the matrix, loading the other matrix, and calling this operator gem. And since we know how this operator gem is going to work, so we know how to lay out the data. And then we can do explorations of different tiling options that we can then perform to better use those scratch pads that are locally within the DRAM DIMMs. And for instance, in this case, I just remember that it was interesting that this tiling, which looks like this horizontal partition, was a tiling that eventually gave us the best result for several benchmarks, which is, at least for me, was not expected. And that calls maybe for understanding or for better modeling how the systems organize data, how the systems compute, so that we can actually do a better steering of optimizations within the compiler. And I'm just going to get back to that in a later slide. So in terms of results, it actually sort of worked. So what you see here are different matrix operations, benchmarks from, I think, from the polyhedral benchmark suite. And what you see is that every time you increase the amount of DIMMs, so this 4D, 8D, or 16D, it means that we're using more DIMMs. We're telling the compiler to use more DIMMs, meaning that you have much more processing units, right? So if you're using 16 DIMMs, it means that you have 2,000 processing units operating close to memory. So what you see in these plots is that every time you increase the amount of DIMMs, so the performance improves, which means, yeah, the compiler is able to automatically use more resources if given to it. And then the other thing that you see here is the optimization versions, so the ops, and the optimization version would do some exploration actually quite simple back then on how to improve the implementation of the core of that kernel to run on that amount of DIMMs. And so you see that every optimized version runs better than the unoptimized one. So in general, we showed that we could achieve 40–50% speed up in geomean across all these benchmarks. Then we also look at a set of benchmarks, which is the print benchmark suite, which was created at ETH. And here you also see a bunch of results. So in general, so those manual designs that were provided by the people at ETH already had a speed up of 2 to 5x compared to CPU. And with this compilation flow, we were able to actually improve over those manual designs by 1.5 or 2x. So faster than 100 in code, and with 10 to 40 times less lines of code because we are starting from a high level abstraction. All right, so that's for the near memory computing system. Now to a SIM example. So here again, some matrix multiplication here, a bit generalized. So here we have some tensors which are three-dimensional. And so what a in-memory compute crossbar would look like is exemplified here with this diagram. So what's happening here is that you are storing in those memory stores, you're storing the equivalent to the weights. In reality, you're storing sort of the inverse of the weights. So these cells here are not just, say, a capacitor like in DRAM or a bunch of transistors like in SRAM, but this memory cell here is something that can store a value of resistance. So the trick that you can apply now is that if you have a bunch of resistors that have a configurable weight, so this is programmed, then you can pass voltages through the lines. Instead of setting address bits, you put voltages. And those voltages go through the resistors. And at the end, what you get in every column is an addition of those currents. So the current that you read here is equivalent to the product of these input voltages and the resistances, and actually the conductances. So it's a dot product implemented in the analog domain that you can leverage to implement matrix vector multiplication. So this will be the matrix. So you store the weights in this matrix. This is the actual memory. And if the weights are not changing, so they can just remain there. These are non-volatile memory technology. And then you pass the inputs as analog voltages. And here you have to, or you can read out the dot products as analog output, which is then transformed into the digital domain. So, so this is an example of many such crossbar architectures that can implement complex operations that require multiple iterations in a software-based von Neumann computing. This can then execute in say in this case constant time. So for that we also built sort of the compilation tool flow using MLIR. Maybe here just to give an example of something that we did. So what you see here is a loop interchange. So loop interchange is a very common transformation in compilers. But in this case, we did loop interchange to reduce the amount of write accesses to the memory array, which is actually beneficial for lifetime, right? So by reducing the amount of writes that you do into these non-volatile memory cells, you actually increase the amount of or the lifetime, the amount of time, or the amount of years that you can use this memory. Okay, so in terms of results, here the baseline is a bit weak. So we're comparing against execution on an ARM. So this is all simulated because we don't have, back then we didn't have any prototype of such an array. So the baseline here is the ARM execution. And what we are trying to show here is that, yeah, we have an accelerator that was built for ML, but who cares what it was built for? We can actually, if we have good pattern matching at a higher level of abstraction on an MLIR dialect, we can actually find those locations in the code where the compiler can automatically use those crossbars. So you see that the gains vary as you go through the benchmarks. For instance, for LSTM, which is not very heavy on matrix multiplications. So the first implementation on the array was actually slower than running on the ARM. Only through optimizations we managed to get it down to a better performance, right? But here we were just showing that it is possible to leverage these accelerators throughout multiple benchmarks. Of course, these benchmarks are sort of easy, right? So this is not entirely solved, and so we could rip those, or we can extract those gains of this emerging hardware for multiple applications, not only in terms of execution time, but also in terms of energy efficiency. All right, then I also talked about CAMs, similar thing. So now we were working with people using one-shot learners and also hyperdimensional computing. So they would write their algorithms in PyTorch or Python. It would look something like this. And then by pattern matching, finding some of those functions, we could then use a content addressable memory. The compiler will understand what sort of CAM that is. Is that a multi-bit CAM? Then it could work like this. So this is an implementation of how that would run on a multi-bit CAM. If it is a ternary CAM, so then we know that we have actually to do some matrix multiplication. We'd have to do some normalization of the signals before we can actually put it into the array. We lay out the data in the array. And if that array has actually what is called selective search, so it could actually also be supported by the compiler. So as I said, so this was sort of K-names, one-shot learning kind of benchmarks. Now the Cinnamon workflow works for CAMs as well. What you see here is that in terms of accuracy, using these arrays, the accuracy does vary from the implementations on a GPU compared to some of these arrays. In terms of latency, you will see that implementing on a 3-bit CAM will also give you orders of magnitude improvement. So in general, sort of 14 times faster than running on the GPU and with 10,000 less energy consumption, at least based on the simulations. Some things are optimistically modeled in the simulators, and we can talk about that maybe offline. And I said that the compiler was built sort of retargetable, so we can pass some aspects of the architecture to the compiler. So we can actually explore different ways of mapping data into that system. So without maybe going into too much detail, here are different flags that you can pass to the compiler. And so this even you optimize for density or for power or a mixture of density and power. And what you see in all these plots is that there's a lot of variability. So there's a lot of, so the design space you can play with as a compiler is quite big. All right, so one thing that we want to do next, is something that we've been talking to with Mike Niemeyer, is how can we continue to bridge the gap, not only now from the algorithmic representation of the kernel that you want to run, all the way perhaps to the geometry and the device parameters of how those cells are implemented. So I talked about near memory computing, crossbars in memory, CAMs in memory. So the other thing that we looked into is also logic in memory. So how we can execute logic operations in memory. And this is work with Medita Hori, where we looked at in-memory computing with NVMs. And so actually this was an interesting compiler problem because now you can execute, say, for instance, you have a bunch of bits on a memory row in this NVM. You can actually compute multiple different logic operations on that row. So you can do AND on the first 32 columns and then an OR on the following 32 columns and so on and so forth. So you can actually have sort of a MIMD parallelism, weird MIMD parallelism in memory with some constraints about what can you really map in parallel on the different columns of the memory. So this is something that we optimize for. And what you see here with respect to a naive implementation of, say, a logic network into the memory, with an optimized one, is that we managed to improve the latency by 3 times, while also improving the reliability in terms of faults, the fault probability by 1.4. And compared to baseline, orders of magnitude improvement in terms of EDP compared to the CPU. All right, so let me try to move on a little bit faster. So this is something that we're working on right now. So this is a preprint out there where we are sort of working on how can we model in general these new execution models that are enabled by near memory or in-memory computing. So what I was mentioning before is that so we have this compilation flow and we do some optimizations in this compilation flow, but we realize that some of the assumptions that we work with perhaps are not always apply because we come from subtiling or some of these optimizations are there is a common understanding based on how CPUs and caches have worked over the years. Whereas here you have some new details about synchronization between banks, data movement, DMAs, and sort of things. So what we thought is, can we perhaps build like an abstract modeling framework that allows us to foresee the execution time of different, the effect of a tiling or the effect of a data partition quicker than just going through simulation. So we work on a sort of a formal representation of how data is partitioned, how this data is partitioned and then mapped to the hierarchical structures of memory, like for instance, banks or channels of the memory. Right? So we have this data and operator decomposition on the hierarchy. And based on that, we can then sort of estimate what the schedule would eventually be. So we get some error, which is tolerable, right, for a compiler exploration. And that's something that we were working on so that we can then further improve our compilation flows for these different sort of engines. Apart from that, we're interested in not just modeling latency and energy, but maybe also focusing on things like reliability, endurance, and so on. All right, so that's it. So there's several projects that are starting or have recently started in Dresden. This is one, Active3D, which is between Dresden and the RWTH Aachen, where we're looking into this three-dimensional implementation of in-memory computing accelerators. An excellence cluster in Dresden, which is looking also at, say, sustainability aspects. And recently, I was awarded a consolidator grant where we are going to start looking into this thing. So if you're looking for a position for a postdoc or a PhD, or you know someone that is interested in these topics, reach out to me. I will be looking to extend my group in the near future. All right, so as a summary, so I talked about automatic optimization for heterogeneous systems and with a focus on in-memory computing today. Talk a little bit about what I believe is the power of domain-specific abstractions to sort of allow high-level optimizations. How can we model these primitives that are enabled by new hardware so we can build optimizing and also safe high-level compilers? So there's a bunch of challenges. So I think still this field of the primitives that you can implement on these accelerators is quite varied and changing. And I think it is still sort of an unknown whether we can really build everything, so like have reusable abstractions that would work across fundamentally different paradigms. So that's something that we'll have to wait and see. Work on simulators, prototypes, cost modeling, as I mentioned before. And yeah, this co-design that was mentioned in the morning, going from algorithmic all the way perhaps to geometry, I think is an interesting avenue of research. Right, with that, I'd like to thank you for your attention. I'd like to thank also people in my team and yeah, some of the agencies that has funded some of this research. Thank you very much.
Thank you very much for that very exciting talk. In the interest of time, we can allow one short question from the audience. If there is nothing immediate, please use the lunch break for further questions about this very interesting talk.
Sorry for not allowing time for questions. Thank you.
Well, next up, we have Oliver Brinkmann from University of Tübingen, and he will talk about neural architecture search for custom devices. So the level above what we just heard, so to speak, matching the topic of our talks. Please take it away.
Yeah, thanks a lot for your introduction. And yeah, I would like to go one step up, but also down to the chip level. So we will mix a little bit up the different viewpoints here. And yeah, everybody knows the situation. Yeah, we as a hardware guy, we somehow believe that the ML guys are not really interested what we really need. Yeah, so there are new ML models, very large transformer models with softmax functions that are very difficult to implement, and we have to follow somehow with the hardware the trend. And sometimes it would be good to talk. Yeah? And if we cannot talk, of course, we'll need tooling, and that's the idea. Yeah, to bring applications either, for example, in the vehicle or in very, very small devices like a video capsule device to analyze the GI tract. And we would like to contribute to that by having some kind of flow, starting with some kind of system observation, system orchestration, because we don't have to rely on a single task. No, we are faced with multiple ML workloads that have to be considered, and of course that complicates the search space much. We have to put the different workloads into a joint search space. We have to take a look what can we implement in hardware, and finally we have to get down to the hardware. And so that's an view from Mercedes with a lot of tasks. Half of them are ML functions, and some are running in sequence, other are running in parallel, and then you have to deploy it. And you have a lot of interrelationships between the different tasks. And then, of course, you have to think about how to bring it down to device, to orchestrate the system, to do optimization steps to optimize the neural network, probably sometimes to adapt the hardware, and finally to do deployment or retargeting from one device to another device. In order to do that, of course, you would need a hardware view. If you construct your hardware by yourself, then of course you can also influence or modify or change the hardware that the networks can run better. If not, then you have to have exact performance models for the hardware to adapt the neural networks accordingly. But let's start with the system orchestration. So the upper left block here. And I have a general picture here that illustrates it a little bit. You can have multiple sensors, because that's the input. We have to control, we have to read the data from the sensors, and then we have to control the actors at the end. And in between, we have multiple functions, and in the meantime, a lot of ML functions. And so it's not good to have an isolated view to a single ML function. Then probably next steps, you're thinking about, okay, where I have to deploy which ML function. And it's shown here, so the neural processing unit 1, probably we have 2 AI functions implemented, of course. Then we have to do some kind of task switching, if it's possible, if supported. Then we could have some memory compute, as shown just before. We can have some kind of DSP calls for DSP-related functions, and so on. And but what's important aspect? What the sensors are delivering? The sensors deliver data in a given frame rate, and you know exactly how the frame looks like. If you have a camera device, you usually transmit the data in a row major form, row by row. Could also be color major, but it's not usually the case. And then you have also for the other sensors data formats that describes that. And if you don't consider what kind of sensor input you get, you think with your ML workload quite free, and then probably if you have a convolution, then you have some kind of blockwise data access patterns, because you have to shift your filter kernel across the data. And that could look like this one, but it could also look like that one. Here we have subblocks, and the other data access patterns, we do it completely row by row. And if we go to a leader resource, we can have at the end 3D data access patterns and so on. That means we have to consider the data access patterns from the functional point of view, but also from the hardware point of view. And we have to somehow bring that together. And if we do that, then of course we can deal with memory in between, because then we actually know how many data we have to save in between the different functions. If I don't have that kind of analysis, I have to save the entire image, for example, in the memory. If I have some kind of blockwise transmission, then probably I need less memory. That's important. That means from the data access patterns, we have two views. We have on the one hand side, we have functional data access patterns that are described by your functionality, basically your operator coming from your ML workload. On the other hand side, you have hardware data access patterns. For sensors, it's clear, but exists also NPUs with fixed programmed data access patterns to the memory. And then, of course, that should somehow fit. And from the function point of view, it's shown here. If I have two ML workloads, as a triangle symbolized here, and if I don't consider the constraints, data dependencies in between, then I don't know if I can execute the function in parallel or not. If I have the constraint and I don't take a deeper look what data access actually will happen, then of course I have to execute it in a sequential manner. But if I consider the data access patterns in addition, then I can have an overlapped execution. Oh, there's a mistake here. That's one and that's two. And I have an overlapped execution possibility. To get there, one of my PhD students developed first a language to describe setups, to describe system setups, how many, to describe the components, compute components of your system. Then you have ports and interconnect. Here's the interconnect, you have ports in between. And of course, the ports can also be associated with data access patterns. And then you can formulate not only a single one, but also multiple one. If multiple patterns are supported or the functions behind them that will be executed on your device have multiple data access patterns. Okay, now we have to bring that in line. That means we have to go into a single channel. We have a producer view and a consumer view. Yeah? And of course, a transmission view. The transmission view is actually some kind of a serialized version of the data across the system. And then we have to check now if we have some kind of compatibility between the right-hand side data access patterns and left-hand side access patterns. So the question is what we can do. If they're incompatible, then we can, of course, adapt. First, one kind of adaptation is to have some kind of reorder buffer in between integrated to reorder the data so that next device can get the data in the right way. But of course, I have to buffer more. The other perspective is to tell the ML workload, oh, please change your operator. Yeah? Please change the operator in a way that the data access pattern will behave in a better way, so I can optimize the system. And that can be integrated in an optimization loop to find good matches, because not all arrangements are possible here. And of course, it can be done also with polyhedral tooling. It's probably a little bit misuse of polyhedral tooling to bring that together, to combine it in a way to find a set of well-suited patterns for good implementation. So that's the first idea to come on the one hand side to the good memory hierarchy. On the other hand side, to have hints for the next step, neural architecture search to follow that kind of constraint. And here that's a generation aspect of the streaming buffers in between. If I have some kind of somehow harmonized patterns, then I can synthesize appropriate streaming buffers in between. And of course, the streaming buffer have to adapt to different patterns. But if they are completely incompatible, then of course you have to buffer. And we have explored it, running out of time. We have explored it a bit. For example, multiple stage pipeline with DSP elements, with multiple NPUs, and then you can check, okay, what's the appropriate size of the streaming buffers in between with a given data access patterns. That's shown here. Okay, next. This information have also been used into neural architecture search. And we have developed a neural architecture search framework, HANA. It's actually more, it's neural architecture search and a lot of additional stuff like conversation-aware training, but also deployment is included. And yeah, it's a complete tool suite. You can get download it from GitHub, and then you can play around. So next, but let's now talk about the NAS, the neural architecture search aspect. of course, there exists a lot of NAS approaches. A lot of approaches are SuperNet based. You construct a SuperNet, and then you have some kind of function that basically tries to optimization function that tries to include the constraints in optimization function. And that means you have a mixed criteria problem, a multi-objective problem. We would like to go a little bit in other direction because we have some kind of network macro architecture already in mind, and that can be described. That you have, okay, you have some kind of blocks here, and also you can have some kind of residual passes, of course, as well. And then you can refine the blocks as shown here. Also with different patterns. Then you have different motifs that describe the patterns, and you can select that. And each pattern, here you see, for example, a search about a standard operation or depth-wise convolution and all that stuff. You can combine it a little bit away, and each operator itself can also be adapted. And that have to be somehow intersected with the constraint coming from a hardware, but also with the constraint from the data access patterns. How it's implemented, it's quite convenient to use PyTorch for that. That means, as you describe your neural network, you can also describe a meta neural network where you can generate a lot of alternatives from them. And that's shown here. So we define a neural network topology, PyTorch-like. Yeah? Then you can parameterize the used operators. You can parameterize different passes. You can select different passes. You have choice operations to sample different alternative passes during network generation. And yeah, that can also be all described in directly in Python using the PyTorch library. Okay, then based on that, if you have done that, then you have described the search space because it's a parameterized network, and you have to find parameters for the for all possibilities. And the parameterization can be extracted and just sampled. That's the idea. So you can iterate it multiple times, and you sample in each step a new neural architecture that complies to the constraints you have specified. That's the idea. But how the constraints are considered. Each node inside is annotated with symbolic expressions, and during extraction of a neural network, the symbolic expressions are evaluated, and by construction, you get valid neural networks out. And then, of course, you are much quicker. We can compare that also with unconstrained neural architecture search. And yeah, and then usually if we take a look here into the search space here, just visualized in terms of the number of weights and the validation error, then the unconstrained search basically explores first here a large area, and we can directly restrict the search in a way that we take a look in the area we would like to look. And yeah, and also to look for networks that follows your described data access patterns. Yeah, on the next slide we see also two variants, one with a constraint of 50K weights, and the other is 200K weights, and then the last is about generation times, exploration time. What we see here on the left-hand side, you see that multi-objective optimization could find good models. That's here, what you see here, but they're out of spec. That violates the constraints. And if we consider all the constraints, then we see with respect to the number of search steps that, yeah, we need much more search space to find suitable solutions, and our blue solution converge much faster. Of course, it's a more constructive way. You see the same here in the middle. And oh, pardon, here, that's next. Where even a greater dependency on initialization and additional search parameters can be recognized. And here on the right-hand side, you see if constraints are restrictive and only small models have to be trained, then of course we will end up with a much faster training again. Good. And yeah, that's a comparison with a lot of other existing approaches, and we will see that we find very accurate solution even with very small number of parameters, and that's quite good for implementation. Going next. So what we have done so far, we orchestrated the system a bit. We have multiple networks, we have the data access patterns, we have the NAS. Now we would like to get down to hardware. And now we would like to focus on a very special case of the hardware. And that means it's not hardware that would fit in an autonomous vehicle, because in that case you would rely on commercial off-the-shelf hardware, of course. And if you then apply, you cannot completely apply a hardware software co-design for that. It's more a hardware NAS, because you cannot change that much. But of course, you can change your configurations, the memory planning, that's possible. But here we would like to change more. We would like to develop together or refine together your neural network with an underlying hardware. And we have done that for a use case. So that's a video capsule here. You can swallow that, and to put AI in that capsule, it's a hard job because you have very resource limited systems, and it needs also very energy restrictions. And our approach is here to have a generator for the hardware, but also a generator for the deployment. That means that the deployment tool have to be generated in the same way you generate your hardware. And so Paul used TVM for both, actually. TVM to generate hardware based on hardware templates he has already developed, but also to generate a deployment tool that's able to deploy your neural network on a generated hardware. And to do that, it's somehow good to have some kind of understanding, okay, what's the relationship between the AI accelerator and the deployment tool? And then if you explore it quite in deep, and he showed that compiler-aware hardware design is quite good. It's not good to generate hardware accelerators that can where you don't find a good deployment solution for, and the task should be somehow aligned. So just to have a rough understanding of what you can do. You see here we have on the one hand side high-level IR and low-level IR. That's used in IRI, that's used in TVM. So what we can optimize at high level, what we can optimize at a low level. And at a high level, usually you think about the streaming domain, the compute units, addressing formats, memory hierarchy aspects. That means more the general perspective are considered, and of course the mapping to that kind of high-level perspective. And also you can decide on multiple instances. Yeah, and then the mapping, you have to do then the mapping the nodes to the compute nodes, and also, of course, the edges to the interconnect. And then if you describe the amount of data across the interconnect, you know if you need some kind of buffering in between, also within the accelerator, and also you can derive address schemes. So, and then the next step is to go one step lower, to go on the component level, And for doing that, of course, you use a low-level IR. That means you just describe, okay, if you go for a systolic array implementation, so that's our favorite implementation for the accelerator, you define, for example, the dimension of the MAC array, 8 by 8 or 16 by 16 or something like that. Also including the number of registers you have to use in between. Then, of course, the streaming buffers to interconnect them, and of course, to describe the address generator. What we can do then we can bring both sides together. So on the one hand side, you have your base accelerator architecture. On the other side, you have the use cases. And the idea is, you don't want to generate a fixed accelerator for only a single neural network. That's not a good idea. That means you have to do the job what we have shown here before for multiple neural networks. That you find for multiple neural networks that have to somehow relate to the same complexity class that's important, that's useful to find appropriate accelerator parameters. And then, of course, you can also use that accelerator for executing the different neural network architectures. That means at the end, you have a specialized accelerator architecture that deals with the different input formats, different neural networks. And then, of course, you can go for an FPGA implementation, but we have actually used also the pathway down to an ASIC implementation. And here you see some kind of experimental evaluation for what tasks we have considered. We would like to use a video capsule task and also an audio task. That means, so we have a camera interface to the accelerator. We have an audio microphone interface to the accelerators, and then we have to switch between 1D and 2D convolutions that have to be also carried out. And then you will find an appropriate set of parameters to come to an optimized implementation of an accelerator for that kind of given set of neural network architectures. Yeah, here currently we perform more or less only for that step, more or less an exhaustive search using a generative evolutionary algorithm, wait for long, but here we would like to improve further. And at the end, no surprise in terms of the MAC array size, 8 by 8 MAC array was well suited for the audio and video use case, and the local memory word depth should be 128K. Then we have global memory banks. We need 3 global memory banks, and we need a global word width of 64. And then we showcase that we connected the non-AC camera from AMS. That's a capsule-aware camera. We can directly connect to the system on chip, and to do localization, and also you can go forward to go also to anomaly detection. The camera has not a very high resolution. It's just 320 by 320, and we need just 1 frame per second. The camera can more. We could also do more, but you don't need more during traveling of a capsule in your GI track. But we would like to see more than 90% accuracy. And then we need the image preprocessing, the DNN inference, and of course the prediction at the end of the device. And energy control for the capsule to make the decision at the end. Then we exploit a little bit what's possible, because at our platform we have a RISC-V CPU, we have the accelerator, and we have also built a RISC-V CPU with some custom extensions. So that's done all in a Scale4X project. That means if you go for ARM, you have to decide on performance classes. Which performance class fits well to our application domain. If I support custom extension, then I can start with a microcontroller with a very, very low performance class and put some custom extensions, for example, Mac, of course, to accelerate execution, but also to make execution more energy efficient. That's what you will see here with the speed up. If the baseline without custom extension is 5S1, then the custom extension provides a speed up of 4.3. And if you go to UltraTray, the adapted accelerator, of course, we have a speed up of 588. And also area, 0%, that means that's a start point. Then we need 8.2% more for the custom extensions, and including the memory for the accelerator. That's the reason why it's a high number, 297%. And of course, we can in every step half the power consumption. Overhead is wrong here. And so that was a chip that was chips that comes out. Left-hand side, the first version we taped out with partners from the Scale for Edge project. So that was optimized for audio use cases, for example, for autonomous driving, siren detection. If you have autonomous ride, you have to check from which direction ambulance car with a siren will come, and then you have to adapt your maneuver accordingly. And on the right hand side, there's a new version for video, audio, and also for use cases for neural implants to have some kind of seizure protection. And you see here you have here's the RISC-V CPU that's from Minres. Then a SOC subsystem, and here the UltraTrail accelerator, and of course a lot of SRAM around and a PLL for clocking. So this system can clock up to 1 GHz if it's needed, but it's not needed for that kind of use case we just discussed. Okay, that was just a nutshell what we are doing, but it shows a little bit a different perspective about deployment, optimization, also from a system level perspective. What we have seen, it's might be good to migrate from single machine learning viewpoint to a multiple machine learning viewpoint, that we can support multiple models here. Then, of course, data access patterns plays a crucial role for latency, for area, but also for energy. Then we discussed hardware awareness, using constrained search spaces to optimize the deployment by appropriate operator selection. Then, of course, the co-design aspect to find an optimized hardware neural network architecture for domain-specific set of ML workloads. And what I didn't show, of course, we need also performance estimation for doing that. We have done that in a white box and black box view. White box if you have total control of your accelerator. Black box view if you have to map or make an assessment for commercial off-the-shelf. So that was our perspective on that problem. Thanks a lot.
Thank you a lot for that exciting talk. In the interest of time, we sadly have to skip the question section, just so that everyone can get to lunch in a timely manner. And now for the last talk of our session, I want to invite Professor Daniel Müller-Kritschneder from Technical University of Vienna. Please take it away.
All right, so now I'm keeping you from lunch. I brought two topics today, so maybe what I will do is, since you're kind of quite of late, I will be a little bit fast on the first one, where we do this distributed inference and memory optimization. And I want to concentrate a little bit more on the work we do on fault tolerance for especially TinyML deployment. And a little bit the motivation for that is I guess it was already said a few times, as Oliver motivated it very well. We see this kind of rising number of AI workloads in automotive. And a car is still a real-time safety critical system, right? So we have to still also deal with real-time constraints, and we have to deal with functional safety. And that's a little bit part of where we kind of concentrate our work on. A second motivation is a little bit when you go to this tiny ML trend, right? You see all these very nice applications where you can run neural networks direct to your microcontrollers. So for example, gesture recognition is a very nice example where you have a radar sensor and you can implement a touchless control, and the neural network for the recognition runs directly on the microcontroller, which is on the board of these sensors. We tried it out, so we could get quite nice results even with this Infineon system, which is a radar sensor. And as you can see, it has very, very limited memory, only like 32 kilobytes of flash and 16 KB RAM, but you can still fit kind of a nice neural network in there for this kind of gesture recognition. Another application we are now looking into is space. So there's a lot of now work to get AI onto satellites. And there again, we have very hard radiation environment. So there you have to deal again with aspects of soft errors in your system. So a little bit to take you away, this is a little bit more historic. So what we started off with is we basically looked into distributed inference. So we wanted to run neural networks on several IoT devices. The idea was each of these devices doesn't have enough memory to fit a more complex neural network. And now we want to kind of pool the memory resources together. This was a joint work with Andreas Gerzlauer from UT Austin. They actually started this line of work already quite some time ago. And the idea was basically what you know is if you want to compute a certain part of the output, laser pointer, right? You only need, so this is kind of HW tiling, you only need parts of the input of the convolution, right? So you can actually just compute this part. And you can even kind of propagate this back over several convolutions and convolutional neural networks. And the idea is then, if you distribute that on several devices, you can build this kind of fused tiling, it was called, where you kind of distribute the inputs onto the devices. Each one computes then its output tile, and then you merge them together. And then you can go for the next one. So the kind of these kind of cones which are creating, they become bigger and bigger. So at some point it makes sense to pull the information together and start the next approach. We did then an extension for the backbones of these convolutional neural networks. So we kind of did tiling on the channel level. And also again here, this is kind of two layers. And the idea is for the first layer, you compute parts of the, also one output feature map. Then you can still propagate this at least over one more layer, but then you will only get partial sums. And at this point, you have to kind of merge these paths together, and you get the full output again for these two layers. We kind of saw that this kind of brings down the memory footprint. So we tried this out in a cluster on Raspberry Pis at the time. The runtime sometimes gets better. It really depends on whether you have very fast interconnect or the interconnect is slower, because then the communication overhead kills you, because the devices are also working in parallel. And we took this on. We also did this for memory optimization. So what we did is we kind of found a few networks where we had kind of big intermediate buffers. So very often, if you look kind of the lifetime of the buffers, if you have like an image input for your TinyML application, usually you can hide all the other buffers within this input buffer, because if it's the biggest one from the lifetime, you anyway have a big tensor arena for this input buffer, and then you just override it with all the temporary buffers in your network. If you have like a network where you have like a big intermediate buffer, that one becomes a dominant one. And again, what we can see here is if you kind of create these parallel paths, you can split this big buffer. This changes then the lifetimes. And the idea is then, okay, since we now have the split buffer, we can compute one path until the end. Then we only have to keep this kind of smaller buffer in memory. And then we compute the other path over this big buffer. And overall, kind of the tensor arena shrinks, and we can save some energy or some memory demand there. From that, we kind of try to formalize that. So we kind of came up with a method where we're trying to create these parallel paths over a large range of different layers. So the idea is always we kind of create these parallel paths, and then we kind of look for good opportunities to apply it. In this case, it was for memory optimization. We used some MLIP formulations to get this done. And from the results, we could really see for several networks where we had these kind of dominant intermediate buffers, and we could bring down the memory footprint quite significantly. At the moment, we are kind of now moving this to the ONNX level. So we had this first, we did this more on the relay level of TVM. What we kind of noticed is all these compiler frameworks have pretty, let's say, the lifetime is not that long. So when we kind of started, a PhD starts, he starts with one framework, and then he finishes. Actually, that framework is already phasing out. So our first work was very TF-like for micro, then we moved to TVM, relay, and then Relax came, and I think now then the next one is IRI. On this ONNX level, we're a little bit more independent of that, and therefore we're kind of trying to get all this ruling now into the ONNX runtime or do some graph rewriting there. It looks pretty straightforward. So if you have some kind of convolutions, we kind of create these ONNX graphs with this lot of parallel paths to compute, and they are still kind of valid operators. Our main application area is now for real time, so we can just interpret this graph as a task graph, and then you can just apply actually standard scheduling techniques on this. And since each of these operators are very small, if you don't have preemption in your accelerators, the chance is still higher that if you kind of issue such a task, you can nicely finish it. You get, again, a valid buffer, and this makes it easier for the scheduling task. So this was a little bit on the real-time side, what we are doing. My second topic I want to now bring up is this functional safety topic, where we look into fault tolerance. And the idea is there are different standards you have to kind of consider. Here are two. Now there's actually also a third kind of a range of standards coming up. So the first one is just this kind of safety of the intended functionality. So you have to make sure whenever you bring functionality into your system that it actually can solve the task you're looking for. So especially if you go up with the autonomy of the car, so you have to make sure actually that whatever software you're implementing is able to solve this task. And you have some fallback techniques, plausibility techniques, which make sure you are safe in any situation. At the same time, you also have to consider the standard functional safety, so this ISO 26262, which basically has different aspects. One is more on the process side. So whenever you design the system, there's a very rigorous safety design process you have to keep. And a second aspect is that your system has to be safe in the presence of random hardware faults. So what can happen is that you have a particle hitting your chip. That can lead to a charge, which can lead to a bit flip. So a 0 becomes a 1, or a 1 becomes a 0. And then if you have some computation happening, and this is a variable is saved in this flip-flop, this can change, then the variable number, and this is kind of a corruption, then possibly or propagates the corruption of your output. The classical way of dealing with this is in the automotive architecture. So usually, at least dual redundancy, you have a main processing core, which is operating on the workload, and then you have a checker core. Usually, it's a little bit shifted in time so that there's no, for example, if you have fluctuations in your supply voltage, that this is hitting different parts of your program. So usually there's a little bit of a time delay there by a few clock cycles. And then you have a comparator which makes sure that the outputs actually match. And then you have all these other techniques like ECC on the memories and so on. If you now go to machine learning, there are different ways, one direction, we can deal with it. One way is we can also go for redundancy. So if you have like a multi-core system, we can kind of issue several networks. We can actually make different variants of them. So kind of have a little bit diversity, but they're all solving the same task. And you can do some averaging or voting over them. There's another technique which is called algorithmic-based fault tolerance. This is a quite old technique where you're trying to find bit flips in linear operators. And since convolutions and dense layers are linear, you can really nicely apply it to this machine learning workloads. And then on top of that, you can also just, train your network with errors. So you can put errors in while you're training to make it more robust against these corruptions. Or you could also just ignore it and say, whatever overhead, right, you are looking for the to make it more resilient, so actually just make your network bigger. So your neural architecture search has a bigger budget, and you're saying I just go for overall bigger accuracy. And the question is a little bit, what makes sense to do in terms of the overheads. These kind of techniques where you really redundant computations are very kind of costly because you at least have 2x overhead. And the one we have been looking into was this algorithmic-based fault tolerance. The idea is very easy. It's a kind of very old technique where you're saying if you have a matrix multiplication, you take a checker vector at BT, and you multiply that first with W. So that is kind of a compile time constant folding operation. You don't have to do that at runtime now because W, your trained network, is already known. And during runtime, you would take this constant and you would multiply it with the input. And this gives you one output vector, which you can sum together. This is the one checksum. And then you take this VT vector again, you multiply it with the output. You get again an output vector, which you can sum around the elements. And basically these two have to match, which is very simply can be seen because Z is basically W times A, right? So this should be the same result. The benefit you're getting is that these operations are vector matrix multiplications. So they are much cheaper than your primary matrix multiplication. Therefore, you should not see these 2x overheads. So that kind of technique is already kind of old, maybe older than a few people here in the room. But it was kind of also adopted a few years ago, especially for convolutions, where they have shown how to kind of directly incorporate this into the convolutions. We integrated this method into our own inference library. So it's called NuRISC-V-NN. It's basically a port of CMSysNN from ARM with on RISC-V, and it uses the RISC-V embedded vector as the target or C kernels. The advantage of this is on the top level, we kind of can directly map from CMSysNN. So the advantage is a lot of the frameworks actually have integration hooks for CMSysNN, and then you can just basically put your own kernels below that, and you don't need a lot of integration effort. We ran this in a TVM pipeline and kind of looked into what are the numbers we are getting. So we used 3 small TinyML workloads, basically the TinyML prof, and applied these methods. So we applied this FIC method from NVIDIA. In terms of the runtime, we get like 20% overhead. We also tried a more selective method where we could actually just increase it by 10%. Then in terms of the single data corruption, it means that the output doesn't match the output we have seen from the error-free run for that input. We could see actually that there's a pretty high, for these tiny ML networks, a pretty high number of errors really propagate to the output. And as soon as you're hardening it, you get to much better values. And the selective hardening was actually not trying to cover all the errors. It was actually only those errors which led to a misclassification at the output. And there you can see with the selective hardening, we get basically the same result as for the fully hardened network, where we kind of try to reduce the misclassifications due to these errors happening. Then we did a second approach where we tried to also put this into more on the compile side. So we went into and did a graph transformation for the same kind of operations. The idea, you can see it here, is if we have kind of a convolution with bias and then the activation function, we can only actually protect the linear part. And you can see we kind of create a pattern where we add additional redundant information or computation on it. And at the end, it really kind of makes the checksum check and gives you one bit. And this bit indicates whether the result should be correct, or if there was an error happening, or if there was no error happening. This runs kind of nicely, and we will later see it on CPUs or fine-grained accelerators. As soon as you go, of course, to more fixed function accelerators, they are not used to this pattern, and also the internal kernels are not kind of designed for these kind of patterns. And there we actually saw, of course, that we get kind of in terms of runtime very bad results, because we're kind of the accelerators are pretty expecting these kind of patterns, and if you put this stuff on top of it, they have a hard time to kind of run this efficiently. From the results, so this is a little bit maybe not so easy to see. So the idea is here we kind of injected into so it was completely in software C level, we injected into the primary registers of RISC-V, so these are the 32 X registers. And here on the X-axis, you have basically the instructions as they progress over the program. And this is the baseline now for this audio record, where you can see the red dots are an error was kind of happening. And the top row is that there was really a misclassification happening. The second row is that there's basically only the output was incorrect, but it was still the same class was detected. And then we put in the ABFT, so the linear protection. And you can see now most of the errors can't propagate to the output anymore without being not detected. Here you can see the errors which are detected. And there's one more effect you're seeing. There are also a lot of errors which are actually detected. So at the layer level, they actually modify the intermediate tensor, but that value later gets actually masked by follow-up activations. So you would not see it at the output. So actually what you're also getting is you get a lot of errors where detected where you actually see that the output would still be correct. Here, these lines means that there are some, of course, parts of the program which are not protected by this ABFT, and therefore we kind of duplicated these parts in order to get also detection there, which basically is endure redundancy, and then we can also protect these parts and then get kind of very low in terms of undetected errors. So overall, we see similar patterns where we, as soon as we have these protections in, we get below 1% of terms of these SDCs propagate to the output. The first row here, these are the kind of detection rates. So we can kind of get to above 99% in terms of detection rates for most of these networks. And from the runtime, we see it really depends on the network. So with one network, we actually get also 2x, right? So it was actually not very well suited for this kind of techniques. But for kind of the standard networks, we also see this 10 to 30% runtime overhead when we do it at the graph level and not at the kernel level. So to sum up, so what did we reach, right? Okay, it's a little bit, we see like, if we do it unprotected, we see kind of 5 to 12% misclassification rate for this computation in software. As soon as we protect it with this ABFT method and dual redundancy, we really get this misclassification down, but we pay it with 10 to 30% overhead. Another question is this a good choice? And it really depends a little bit. So I do a kind of, in Germany, we say, pi times thumb computation. So we kind of do a little bit of an estimation. So the idea here, what I kind of brought up is we have like a base accuracy for the network. And then we have kind of a loss due to these soft errors. And the thing is, usually these SDCs are not that common, right? So for example, if we have 10 gigabytes of SRAM already, so very big memory. We see this kind of every 170 hours, taking a fit rate I took from one technology. So if we kind of do the computation, right? So we can say we have the soft error rate. How often does it really happen per inference? And then multiplied with the rate where we can really see a misclassification. And if we do the math, so we actually see that for this kind of, but it really depends what your fit rate is, right? For this, we would only see it in 1 over 6 million inference runs, this misclassification, right? Which is a very, very small error in terms of accuracy. and you're paying this with 10 to 30% overhead, right? So if you, for example, use your neural architecture search and give it 10 to 30% more resources, right, it might probably be able to get the accuracy much higher than that. What is the advantage of this method is it really tells you also that an error happened. So especially if you say you want to have some monitoring, or the other thing is, of course, due to these standards, actually automotive chips have to have this kind of detection rates. Then it makes sense to put it in. But you could also always think that you don't run it for each inference. Maybe you only run a few inferences where you really do health monitoring on your system. And then these techniques becomes kind of interesting because you can get still a primary output, but it would really tell you, was this primary output computed correctly, or is there, for example, maybe you have a core in your system which is not performing so well, or has like a higher SDC rate than expected, or even some other errors. And since it's an unbalanced computation, you should also be able to kind of detect hard errors or intermittent errors in your hardware. All right, so that was all from my side. So I kind of made up, I think, a little bit of the time. And yeah, there was a lot of people involved in this research, so thanks to all of them. And now I'm open for questions if there's time. Thanks.
Thank you very much for that talk. And yeah, if you have questions, I think we have a little bit of time, so please let us know and we will hand you the microphone so that our online audience can also follow.
Any questions from the audience? If there's no question from the audience, Daniel, thank you very much. I have a question. Super interesting in kind of how you blend together functional safety and then kind of argue that to a certain degree there's also the downstream task that kind of is affected from the safety methods according to the overhead. What I'm generally wondering, and I have to confess I'm not an expert in safety, I'm wondering if I look at what is actually happening in the system and what's being deployed in the SRAM, there's potentially also the code for the kernels, there's control registers in the CPU cores, etc. What's generally the approach to secure those parts while kind of not securing the memory elements where, for example, then the weights are stored for the actual computation. So I'm a bit wondering, how do you make one thing secure or safe while you keep the other parts kind of unsafe with no overhead?
Okay, yeah, very, very good question. So overall safety, of course, always is a system property, right? So either the whole system is safe or it's not safe. I think, for example, for code, it's a little bit easier because if you have constants, you can just create checksums, which you can check. You can also, I think what's always important is what you see, if, for example, use constant that you're reloading them from protected areas at a certain time. So what you always try to avoid is that you kind of have very long lifetimes where you kind of bring data into an unprotected area and then you keep it there for a very long time, because then if this SDC is happening, they would remain there, right, in the system. And that would kind of could even corrupt it more and more, right? Because you would degrade with every error. So kind of the idea is you have protected areas, for example, memory ACCs. And if you bring it then to an unprotected area, you would be reloading that at certain times. And what we have seen is, for example, is also with these EDCs, we had to also protect the kernel. So if you do this ABFT, for example, if you have pointer accesses, right, you have to really protect these pointers with also techniques that you have redundancy, that you check that your pointers are really pointing still to your buffers and not starting kind of to write information into an offset buffer or whatever. So these kind of things are always on top, yeah, but they are not really too expensive in terms of the primary computation.
Okay, thanks. Any further questions from the audience?
Yeah, thank you.
Oh, again, thank you very much for the talk. Before I release you all to the lunch break, I just want to highlight again that at 1:30 we will start a panel discussion. So please feel free to join us again after a shorter lunch break, and yeah, enjoy. Thanks.
Okay, so welcome back to the second half of CODAI here at High Peak in Krakow. We are very pleased to actually have in the lunch break. So thank you very much for those of you who decided to take a quick lunch and still come back and join us for a panel discussion. We have the fantastic opportunity here to have Max, Ollie, Geronimo, Daniel, and Perry here on stage. I think the four of you have been presenting this morning. Perry will present later today. Perry Gibson, he's a member of a technical staff from Fractile, working on quite some MLIR-based technologies as well. So we would like to host this panel for answering and discussing some of the pressing questions we are having. And let me start with some of the questions, and then let's simply figure out who wants to respond. And let's make this an open discussion. There's also no predefined, well, there are some predefined questions, but we don't need to necessarily follow those. So what I'd like to ask, and since we say we bring together academia and industry, there is a bit of a question of business models. Ultimately, it's not only technology that we talk about. Ultimately, to some degree, AI is also driven simply because there is a market for it. And the thing I'm wondering is, with AI moving so incredibly fast, and also the hardware kind of adopting and being released, there is a question of how fast can you bring an AI model onto hardware? And the ultimate question is day zero support, meaning there's a new AI model, it runs the next day, there's new hardware, it is ready to be used for the AI models out there. So what I'm wondering is day zero support rooted and based in a market need? Do you see some opportunity there? Or is it more an engineering dream to kind of be ready to use from the first day? I'd like to, link that a bit with your experience on use cases, working with partners, working with industry. What's your view on that day zero support and its opportunity?
Why don't I just give to the industry members first?
Yeah, it's a good question. So there are a few things I saw over the last 2 years. And the first thing is that the device you can prototype on is also most often the device you will deploy on. Look at NVIDIA. So when you do experiment on NVIDIA, of course, then the first implementation out there will be on NVIDIA, and people will then try to optimize that. And kind of this is also one of my personal goals, that you can also experiment on the edge. So kind of have a device that can run your experiments and then just use that out of the box. So kind of that day zero support is by design the device you actually experimented on. And also for other things, like you see on LinkedIn, like a new model comes out, you want to try that on your device, and you have some research departments or departments in the companies building demos or use cases. They can just like take that model, plug in a new text-to-speech model that is way better. For us, it's a huge opportunity, like a big business case and selling point for our software, at least.
Thank you.
Yeah, day zero support is probably easy if you start with the NVIDIA platform, because a lot of ML models are developed at NVIDIA platforms, and that's a problem if you would like to get out of that kind of vendor lock-in, or if you target a platform where NVIDIA will not help you because it's too energy hungry, the form factor does not apply, then you are running really into trouble. And then that's what I told also at the beginning of my presentation. The disconnect between the ML and the hardware community is huge, and we need some kind of bringing a format to get the different communities together. If I'm speed up with ML model development, to be aware of what can be implemented in hardware. Sometimes you have only to change a bit and it's ready. And if it would already be incorporated into the design of the model, then you have completely trained model already available, which would be implementable on hardware. And that's somehow a disconnect. And the next is, even if you start with existing model that can be deployed, kind of still run into trouble. Currently, we, for example, a project running together with ARM and Cambridge. Yeah, also on smaller platform, we would like to have smaller LLMs running, and especially the memory problem, how to plan the memory, and the software does not really help you to preload the data in the right way. Even if they support KV cache and that stuff, the more global orchestration is still really an issue, and there needs a lot of aspects to be solved to get this to running at day zero.
I'm not sure if we can answer all questions all through, unless you say you really want to add on top what have been said.
I do have something to say, but I guess maybe we
Well, the thing, and maybe into your direction specifically, what I'm wondering is, on one side, their serious report is sort of not necessarily asking for best performance. But when the moment we talk about performance, there's ultimately the question, well, do you deploy ultimately on the back end side onto kernels that have been generated by engineers, by experts, by looking deeply into the documentation of hardware, or even thinking about how the hardware has been initially designed, versus truly being able to lower into the microcode of the microarchitecture that is down the line? How do you see that trend? I mean, still today, and I think very much today during the presentation, there was examples where I said we deploy towards kernels. How do you see that going forward? Do you see the technology with MLIR or others and with the pieces that you presented being ready to be resolved, or will it stay that way?
Okay, yeah, yeah, I guess the questions are connected indeed. Yeah, so I would say this idea of the zero support and going all the way and supporting all the features without going through kernels, I think that is a dream, but I think it's a very good dream to strive at. So at least in academia, I think that's to avoid vendor lock-in, to improve. So, but it's a difficult thing to achieve, and I think Oliver mentioned that. I think from the point of view of the companies, day zero support is very important for the psychology, right? So because you don't want people being frustrated in the day zero, right? And now to the question about kernels by hand optimize, I do think that's still the first step today, right? Because this disconnect between maybe these things are not compiled or were designed. So still most of these new capabilities are exposed through hand optimized kernel by some hardware experts. And that's and I think that's a good starting point for the day zero support from the compiler, so that you can just go and do func. But yeah, as a dream, I think the power is on the right compiler abstractions to be able to lower automatically without requiring all the other stuff. But that's more challenging and takes more time. That's not day zero, I would say.
From your view, especially from academia, 0 to 100, dream to reality, where are we?
Yeah, it's a very tough question. Yeah, it's tough because you don't know what's going to be the next algorithm. So if it's fundamentally different, so we are in 10%. But if it is leveraging the sort of the keystones that are already in these frameworks, I would say you could be at 70%, 80%. But then the 20% would cost you a lot of time.
Yeah, I think while going a bit off script, there is I think an assumption here. I think Oliver, you mentioned it earlier on. The models today are being trained on NVIDIA. So there they run. So asking for how does the next algorithm look like? Well, it has a CUDA representation that I can tell you. So if you take that into account, is it still the 70% that you say?
No, that's what I said. I don't think it's 70% if you go off-road, off-piste.
To this, I think from the kernel and compiler side, I think one major kind of driver is talent. Actually, it's very hard to get good compiler engineers. It's even very hard for us to even be train them. So I had a very good students who then kind of went to very good industry jobs, and I wanted to have them in my group. But I think you can get people who do very high performance kernels and do this implementation much easier than you can find people who really know the compiler abstractions and can do compiler work. So I think therefore it's very good that I think it's now moving that there are courses which are offering that. You need more talent in this compiler area, and more people who kind of have this know-how. And I think that is a major driver. And I think the other thing is, if the platforms are very specific, then usually what I see is people use this retargeted compilers, and at some point they build their own backends, right? Because their hardware has some specific kind of characteristics, they know it very well. They can basically implement it in software and don't need to teach it to compile because it's kind of very fixed function. When we move more to this kind of day zero support, I think one thing might be we move to more fine-grained ISAs, also for the accelerators. I think in RISC-V now there's this matrix vector ideas, which will allow you to have very fine-grained software-defined kernels. And if kind of a lot of platforms adopt that as their interface, then of course it becomes much easier because then you can build something like CODAI in a way that you're saying everybody maps to RISC-V, right? And then from that ISA, everybody has its own implementation how to run it in the hardware. But the question is if that is really the way forward, or if saying the hardware is more coarse-grained, so you want to map a whole convolution to it, you want to have fuse operators on it, or when you say, you know, you do image to point, you do matrix, and then you use these instructions.
You raise an interesting point there. Also, a follow-up question I wanted to ask is, today we heard a lot about MLIR, right, as one of the technologies at least that provides some abstraction levels that go far beyond what we had previously. If we think of the architectural challenges what you're just pointing at, meaning if we think of heterogeneous spatial architectures, when I say spatial architectures, I mean basically data flow architectures, coarse-grained, coarse-grained reconfigurable architectures, kind of configurable but fixed function accelerators. There seems to be a bit of challenge because you just pointed out the more fine-grained it becomes, the more likely we find a way to lower it. While from a hardware design perspective, we try to kind of take the biggest chunk and put it into an acceleration mode. So I'm wondering, is there an unresolvable duality to it, or is there a solution that you would propose?
I guess it's a trade-off, right? So if you have more flexibility, it comes with a cost, right? So if you have, for example, RISC-V, then you have brilliant instruction stream, and you need to have the microcodes on there and so on, right? So the question is, if you always run the same microcode, then put it directly in the state machine, right? Then you can optimize on this state machine the compute data. I think it really depends, and I think this goes back to this maybe day zero question. Do you expect the models to change a lot? And then what is your use case? Well, you go to automotive and you say this chip should run models for 10 years in that car, then maybe programmability might be a good thing to have because we don't know what kind of models will be out in 10 years and might still want to patch maybe, right? If you are very sure that this will be the workload you are kind of will see all the time, then of course make it fixed function and don't pay for the overhead for the programmability. I think it's it's hard to see, right? As I said, we don't know what kind of will be next models. And they look very similar to what we see. Yeah.
Yeah, Harry, please.
Yeah, I think it's a tricky challenge, especially for like novel players in the hardware space, because if you're going for like compared to NVIDIA's position, they're this dominant player and people are going to be trying to fit their models for like the hardware that they're training on. So like NVIDIA's proved that they work quite well in the like kind of general environment. So if you're a hardware player, if you try and just build a GPU, odds are NVIDIA will beat you because they're better at making GPUs than you. If you try and go too specialized, then something that isn't a transformer or a CNN or whatever you're trying to optimize for becomes the dominant architecture and then you're done. So where do you find that midpoint there of like hardware that's flexible enough to deal with this evolving space of models, while also actually having some hardware features that differentiate you from NVIDIA so that for some particular deployment, you're doing really well. I guess also kind of connecting to the kernel question and like how that interacts with compilers. I think that there is this process of like learning about how a particular hardware architecture works and like what works well. And I think that when you're a company, you're trying to focus on what do your customers want right now. You go for like the hot models you care about. You might hand optimize those kernels to get good numbers. But I think internally that's a learning process where your compiler team is saying, oh, we've handwritten these kernels or someone else in the company has for this like DeepSeek or whatever kind of model. What can we look at the with regards to the techniques used to get these handwritten kernels working really well? Can we generalize that? Can we make some compiler rules from that? So I think it is that kind of constant process of iteration. There isn't a magic compiler you can write that will give perfect performance on hardware you don't understand yet. I think it is like social process. It is a process of learning, iterating, and generalizing.
Awesome. You're pointing me to two fundamentally different directions, and I really like to ask that second direction. But let me start with the first one, because that was kind of in where we wanted to go and where others were hinting. From academia, we saw today approaches, novel approaches for how to ultimately deal with different architectures, in-memory compute capabilities, and kind of ultimately mapping that with algorithms. So kind of you making proposals there on the algorithmic methodological side. But then again, we would like to embed that somewhere and make it use, right? Of course, we can pick it up on a proprietary basis and industry will take care of it. But there is a bit of a question of consolidation. And that's where I'm inspired by your suggestion just now, where you say basically what hardware vendors are providing today is really the full spectrum in a very fine-grained element, right? And kind of that's also what we see on the compiler side. There's solution to everything. But at some point, I would hope to a certain degree for a consolidation where things, well, I don't want to say collapse, but kind of consolidate and converge, because people just recognize that is from an industry point of view, the ecosystem to use, but also from an academic side of things, an ecosystem you could serve into or provide into. So I'm a bit wondering, do you see there a chance? Or does this XKCD's choke off, well, there's the 15 standard for the 14 other standard. Does this continue? How do you see that? Is there convergence happening on the compiler side?
Maybe I'll start. So I think this, at the end, what you want to achieve is this convergence has to, in my view, has to be based by principles of abstractions or things that you can reduce, right? Because the companies will be providing these and this and that, but things will look similar if you're able to sort of build abstractions and then have Fractile or Semron or whatever company build that last chunk of a specialization, because that's proprietary. The rest can be open source, shared ecosystem, and I think there's a lot of value in that. So that's what we are aiming at. Like if you see those dialects are supposed to be good abstractions that can be then specialized for the different particular technology, right? That's sort of the vision. Whether that's going to fly, because that's in your question, whether that's going to work, I think there's a lot of like political psychology issues there that I hope will resolve.
Which is part of kind of our mission here, to kind of get together and kind of see if we can resonate with things going into a certain direction and kind of bring people onto that mindset of saying, hey, that might be the right way forward. Looking at time, 4 minutes. Again, going a bit off script, Perry, you just mentioned it and saying, well, there is know-how in the kernel teams, right? The kernel teams have written thousands of kernels. In some cases, that is, I think, thousands of kernels. Do you see an emerging possibility for fundamentally new compiler approaches, meaning couldn't a large language model with a base of previously written kernels kind of go into the direction of specializing, right? You kind of provide the full documentation, all registers are given, it kind of gets the reference. Do you see an opportunity for ultimately not a mathematical based compilation, but a reasoning based compilation?
Yeah, absolutely. I think like the face of software engineering has been changing even like since my career started. Like these models are able to give code that can work quite well, and like the performance improves over time. Like you can also have this kind of auto-tuning, auto-scheduling approach as you can start to iterate a little bit more and run real kernels. And you might get to the point where there's like some optimization techniques that are kind of quite uninterpretable to human beings, but like the numbers speak for themselves. I worry that we might lose something if we like completely give up having interpretability of how performance works in our machines. But I think that like there will be incentives for us to at least explore that and view it as another tool in the compiler box of tricks, so to speak.
Yeah, so I think what you said before, that these handwritten kernels are actually a very important input for compiler designers. I think that's definitely true today. As to optimizing the generation, I think there's a lot of work on that area, and especially if you have well-defined abstraction of what the operations are, then there are interesting approaches of doing this semantically correct, because I think that's the challenge, right? You can throw an LLM to produce a bunch of things, but then you don't know if it is safe, if it's really doing what you intended to do. So I think there's interesting stuff about how to preserve semantics and do this automatically. But even in that case, I think it's important. These things are rule-based. There are some applications of, and to be able to capture those rules, you still need intelligent designers to sort of put the guardrails on the ML exploration, which I think is key still.
So in the startup space, there's actually quite a few startups doing exactly that, right? So kind of have an LLM generating kernels, and then I have like an infrastructure to test them semantically and things like that. I think there are use cases where this will, like in the foreseeable future, not work, like automotive, safety predictive things, where you need to have like you need to know how the transformations are working. But I agree also with Perry. It's kind of like another tool in the toolbox. Compared to like kernels, you need a compiler that is deterministic, but you can also, if you have enough kernels and enough compiler data, go to this LLM route, and then it's just the third pillar that might emerge at some point. But it's also like what we need to kind of think about is computationally very heavy. It takes a lot longer than just a heuristic-based compiler that can compile a model in a minute.
We really think today we believe somehow in the compilers that they produce correct code. And can we then still believe? Because if we reflect what we get from the LLM, then okay, there's something wrong. Please think about that. Oh, yeah, it's a good idea. Yeah, okay. How to do the same at the generated code level? That's quite difficult to assess, I think.
Yes, but also the mindset for AI models kind of changes over time. So you have quantization schemes anyway, and like you change your accuracy of the model with that. So I think people are not as strict with AI models as with like language compilers, which is, I don't know, you could argue that's a bad thing, but also like this whole LLM generation is for sure something where a lot of innovation is happening.
In view of time, because kind of need to end this, but I also heard we have a little bit more time. I'd like to go through, and because we touched on many things, right? The day zero support of models, right? Really early on, and then on the backend side, we discussed kernels versus generating the code, and then ultimately also dealing with coarse-grained hardware and more fine-grained hardware. Now talking about the big thing of do we just generally open the whole thing up and then fundamentally create new microcode and then ultimately the instructions. From all the things that can be tackled, maybe we go one by one quickly here. What is the thing that you'd like to really see solved? What is the thing you really believe that's where we should focus on as a community to really make the next thing in AI fly?
I have Mike, I can start like, I guess first building that community would be
building the community.
Yeah, building the community itself. So we have kind of a lot of people switch from TVM to like a more MLR based compiler flow. But kind of this opens up a huge design space, and we then see like everyone doing their own thing, but at the end the features are very similar. So there's a lot of wasted time. If we at Roofline, we're betting on Erie, but also the community around Erie, like it grows. But I think there needs to be like an effort from a lot of parties, from academia, from industry, to kind of come together to one community, because I think just like LLVM, that it's too big of a problem to be solved globally.
Okay. Just a quick comment in here. So one way we try to tackle that is with this workshop. By the way, we will have tonight a social event. We could also make the social component of building such an ecosystem fly tonight. Please reach out to Michael if you want to join to get the details of where we are going.
So we're going to the House of Beer for everyone who wants to join.
Oh yeah, House of Beer. So it's a beer. Oliver.
Yeah, that's a good starting point. House of Beer to establish a community.
Solve it over.
Yeah, that's cool. I completely second you. And for us and a lot of other people, it was really difficult to get out of the TVM the NVIDIA vendor login, and a lot of people put emphasis on using TVM for deployment, and now NVIDIA changed all, and you cannot use that tool anymore in that sense you would like to do that. Even it was open source, and that's what we have to also keep in mind. Everyone tells if a tool is open source, then we can use it forever. No, that's a good example. That's not the case. That means open source is good on the one hand side, but we need to have a good support that we have a mature open source platform in two times from the political perspective, but also from the tooling perspective. And here I would like to see an ecosystem. You're correct. IRE is cool on the one hand side, but the learning curve at the beginning is very high, and you need a lot of effort to get in. And even for small accelerators, which need just configuration data, it's probably a little bit too much. Yeah, and we need something in between. Probably at a beer house, it's a good starting point for doing that.
We have 2 more minutes.
All right, quick. So I agree on the community and political. Maybe I'll just take another stance from more like the principal way of things are working. I think you mentioned the learning curve. I think MLIR and this idea of having abstract lowerings or raisings, I think that's a great one. Whether MLIR has struck the best one, I mean, that's the most popular one. But I do think there's a need to perhaps automate and make some of these things generatable automatically and correctly from the start. So that it's also easier to bring things together, is easier to adapt. Because I think right now, so we've been working with MLIR for many years, and it's always a pain whenever something changes, everything changes. So there's a lot of fragmentation, politics, and so on. So it would be great to have some way in some of these things to have them formalized and have them a way easier way to entry and build correct flows.
Yeah, I think I don't have much to add. So I fully agree. Maybe one idea we could think of is for other open source projects, there's actually governance happening, right? So there are the Linux Foundation and somewhere else. So I think that might kind of take a little bit of the risk to bet on these ones, because we kind of had bad experience with Tensorflow Lite for Micro, right, which was Google, and we didn't know what was happening, why decisions were taken. TVM is now a similar case, right? They put a lot of effort in, you contribute, and then you find out, it goes in some direction, and it's cited somewhere, right? Yeah. You don't know exactly what's happening. So in mind, one idea is always to say, okay, there's like a public forum where this is discussed, right? Put it under the governance of one of these organizations, like Linux Foundation. And that could actually help maybe to build a community and also to give some security, right?
Very good point. Yeah. Barry, you can round it up.
Oh yeah, so I guess like tools like MLIR and whatnot are about like making it easier to build domain-specific compilers, and I think that means that compiler people are enabled to learn more about the particular domains that they're targeting, be that application or hardware. But I think there is also that tooling community question of how do we outreach, bring people that aren't in the compiler community, like to work with us to like, empower them to actually use what these tools can allow us to do. I think that the compiler could, in a sense, set the center of the moving forward. If we're like willing to do the work ourselves and like with other people both above and below.
Amazing. To your last point, compiler work is not the nerdy part. It's actually quite sexy if you think about it. So thank you very much to our panelists for joining here during the lunch break and offering your half hour where actually we could have been eating. I'm kind of starving to be honest. But thank you very much. I think this was a very insightful discussion, and thank you very much for that. Yeah, please give a warm thank you.
All right. So up next, we have a talk by Tianqi Chen. And let me quickly unshare and I'll see straight. So let's do first a tech check. So Tianqi is joining from the US. Tianqi, can you hear us?
Hey, can you hear me?
Hang on, we cannot hear you yet. The same, always the same time in every online meeting. So can you say something again?
Can you hear me again? Can you hear me now? Hello, hello.
Hang on 1 second.
We hear you, but we hear you somewhere there in the back. Can we somehow get the audio onto the room? Yep.
Okay, sounds good.
Just give us a second.
Headphones. This is not correct. It should be this one. Tianqi, can you try again?
Yes, test. Can you hear me now?
Yes, we hear you.
Okay. Let me.
Okay. Now we got you. Perfect.
Yeah, okay. Can you see the
1
slides?
second.
Let me make sure. Can you
Okay,
see the slides now?
let me do
Yeah.
the introduction first, and then we can get
Okay.
perfectly
Sounds
started. Okay, it's my special pleasure today to introduce Tianqi Chen. He is a distinguished engineer with NVIDIA, and he's also a professor at Carnegie Mellon University. I think basically everybody in this room has used one of his software projects so far. So Tianqi, we have a packed house of users. I think you have just heard some discussion, some opinions. We are really looking forward to see what you're currently working on. So please take it away and show us the latest projects.
Sounds great. So thanks, Michael, and thanks everybody for the intro. Thanks everybody for being here. I would like to tell you a bit about some of our latest projects, both in terms of the projects we're pushing and also how we are kind of moving TVM forward. There are like quite a few exciting things we're working on here. So the general theme of the talk is building ML system foundations at age of AI, right? So that's like I think from the panel session as well, we started to think about, hey, we are at age of AIs and how we can think about we are going to change our general approaches to building ML system foundations. And today's talk, I'm going to talk about two aspects that I think will be of interest to a lot of audience here. The first aspect is about how we can use AI to supercharge ML systems, in particular ML compiler and general kernel buildings. And the second question is how we can make ML system interopt with each other more easily. Namely, we have people talk about MLIRs, we have people talk about TVM and other framework PyTorch and so on. And how one of the key questions we have always, how we can make things kind of interopt and work better together. So the second part of the talk is going to focus on that component. So as the first part, using AI to supercharge ML systems, we know that AI can write code and increase our productivities. And we already start to see benchmark 3 bench that shows, hey, we will be able to have AIs do software engineering. Now, while you send GitHub pull request, AI code review is kind of mandatory for quite a bit of our usages. We also start to see, kernel bench, which is another kind of popular benchmark that showcases, okay, AI is able to reasonably getting to a level where you can start to generate correct CUDA code, which is kind of exciting, right? So it kind of makes the question about, but there's also still have a question of readiness. Like, what does it take to slot AI into a development cycle? And more recently, even, if you hear announcement from NVIDIA, there's this project called VibeTorch that allows, or Vibe Tensor, that allows you to kind of have AI to create a mini PyTorch from ground up, right? Although it's not most performant, but it can do it. So it's really interesting to see like kind of progress of AI, right? So on the other hand, one of the questions we want to ask is, we know that AIs are powerful, but we also know that they are not always reliable, right? So sometimes and also we also know that even though AI can generate code, there's still a question about how can you build operational workflow so that you can really slot in AI into our real development cycles. As of today, when we develop LM inference engines like SGLang VLM, TensorRTMs, we have not yet, extensively leverage AI to automatically generate components, but we hope we can get there, right? So we are using AI to do code reviews, to refine our code, but not necessarily directly using AI to generate code. So the question we're asking is, what are we missing here? And so that motivates us to kind of like think about from first principle about what does it take to bring AI to a particular use case. In our use case, I think we really want to focus on large language model inference serving, because this is like one of the most important use cases where we care about. And we believe that in order to solve that problem, we need to kind of do it in 3 steps. The first step is we want to clarify the landscape. And the idea is that we really want a way to standardize and communicate to AIs and to engineers about what are the workloads we are facing, right? Because AI are really good at working on things while you describe the right thing to them, but you really need to send instruction to them. And also it's also important for different engineers and different people to talk in common languages, right? So we kind of need a standardized way to describe what workloads are facing. The second thing is we really need to set a right goal, because AI is really good at optimizing for certain goals and also do reward hacking in a lot of cases. So you really want to be able to kind of like have a target that captures production grade workloads in a scenario that occurs in LM deployment in practice. So instead of saying, okay, go and optimize this, generic gem operations, we really want to tell AI that, hey, this is a particular layer in, DeepSeek that I want you to look into, right? And that also comes with specializations that AIs can help. The final question that people ask, how can we ensure zero-day production path? We have AI generate code, and we can also have human written code. They can be seamlessly deployed into a real LM engine right away. But the question is, what does it take, right? Does it take an engineer to go and review and refine and then see how it used in productions? We really want to have a day zero way, which means that as soon as AI generates something, we want to be able to say, okay, here's AI code running through SG lines, running DeepSeek, end-to-end. I want to see the end-to-end impact on my system. Right? So these are the three first principle questions that we like to ask. So we are kind of building a project called Flashing for a Bench, which kind of aims to answer these three principled questions. And the goal is we want to try to build a virtual circle for AI-driven LM system, right? So it starts from data set and trace, and also talk about how we can apply the AI generated code back onto the learning assistant data set. I'm going to kind of unpack it a bit. So the first step is what we call flashing for bench data set. And this what we do to set, the first step is what we call flashing for trace. So this is what we do to clarify the landscape. This is because we do believe that it's important for us to kind of like record what are the important workloads out there. And so it's what it is, right? It's kind of a standard JSON schema that describes the LM inference workloads. It comes with definitions that describe things like what is operator type they have, what are reference solutions they have, and so on. A reference solution, a solution generated by AIs, the workload that we can capture from a real-world workloads, and the evaluation result. So effectively, it's kind of a standard schema that we use to describe, what are the important LM inference workloads. It serves as several purposes. For example, for engineers, it's a very clear input-output specifications. For AI agents, it helps to present a precise target to AI agent. More importantly, we really want to be able to build infrastructure and tools around it. We know that we cannot build all the tools, but we would like to build some of the key components so that everybody can interact with it. So in this case, the standard schema is something that you could build, for example, a benchmarking tool that takes flashing for trace and run benchmarks on your hardwares. You could build an AI agent that takes flashing for trace and produce output and also produce that in flashing for trace format so that the benchmark tool can take that and and do further evaluations, right? We really believe like this kind of like a reasonable standardization is very important. However, we also know from our machine learning compiler experience that it's really hard to define a complete set of operators, right? So for everything. So instead, flexible traces aims to serve as an evolving standard, evolving schema. So we are starting from capturing the most important workloads in LM inference. We are continuously expanding with the community to kind of like make sure we cover the important workloads of interest. The second thing is the flashing for a bench. So we are curating a benchmark with the goal of setting the right goal for LMs. So most of the benchmarks so far aims at try to solve like simple problems, like how do you do matrix multiplication on certain shape that may or may not be relevant of the real world LM inference. So what we do instead is we first try to directly trace from real world inference engine about what are the operators they are working on. And then we will kind of also do careful curation, so we get a small set of representative data set that we care about, right? So this gives the ability to be able to kind of like really collect the data set that represents the real world relevance of interest. And we have models like Llama, DeepSeek, and Qwen, and other models that serves as a benchmarking traffic. Finally, we really want to enable what we call day zero integration, right? So the idea is that we really want to be able to, once you have a data set, implementation specified by flashing for a trace, you want to be able to directly check how these kernels are doing in terms of your, real world LM inference benchmark. So what we do is, because we kind of partner with the Flashing for community. Flashing for is this one open source inference libraries that's now kind of de facto standard for LM inference, so that and most of LM engine directly interface with Flashing for, right? So what we do is we directly enable an environment variable called Flashing for bench apply, And under the hood, the flash infer kernels will now try to dispatch to the element kernels when matches the workload without you changing one level. You don't have to change any lines of code, right? So, and you try to do things like substitute best kernels format trace in flash infer, no code change involved. And we also partner with SGLang, VM, and other engines so that you can directly test out how this kernel is running on those engines. And of course, the goal is focusing on LM inference kernels. There are also other approaches like backend bench that focus on general kernels, right? So we do believe like this kind of quick end-to-end day zero integration is really important to really showcase that, hey, this is the AI kernel that can improve the frontier of the workloads. So we have open source FlashNode Bench is also a paper at MLSys conference this year. And you will be able to find the link in this URL. That's kind of like a live leaderboard that showcases how different different models AI models perform on a benchmark. The takeaway is, as of today, the models are not doing better because we're kind of using the best flash infer baseline there. We really want to measure against the best state of art, right? However, and also, on cases where the models are doing better, we find that as of now, they are only trying to call in like a Q-BLAS in a better convention, right? So it's not yet getting to the rate of, really the best level, but we're also tracking the progress towards how well it's doing by looking at, okay, although it's not as fast, right? But how fast it can get, right? So that's a really interesting question that we can keep track. However, we do believe like progress can move very fast, and we really want to measure against the progress, and we really love everybody to collectively work together on this, including building compilers and the kernel solution around it. We just announced this Flashing for AI kernel contest in MLSys this year. And with the goal of creating high performance GPU kernels for state of art architectures on Blackwell. And there are the specifications are in Flash bench format. You are more than welcome to bring your agent or bring your best engineering skills to participate, right? So this is something that you should definitely check out on the competitions. Okay, so that's the first part. I do want to talk about second part, and this is the part where I really hope, how do we bring ML compiler community, and how do we bring like a TVM forward actually? And this is about how do we make ML system interoperate with each other better. One of the interesting thing that a lot of people talk about is, with the solutions of TVM, MRI, and others, it's really easy to build things like domain-specific compilers, right? And also, as you start looking into like ML systems, you can start to find there are a lot of components you kind of need to interact with each other. This is more like a runtime, not a compile time thing, because most of the components you kind of need to be able to kind of like build by different parties, right? So it's really hard to kind of like merge everything together, compile. For example, KB cache is one example where if you do LM inference, you kind of need to build in that. We have different DSLs like QTAL, QDSL, Tileline, Triton, right? And there are a lot of them coming out, and I think we are going to see more, right? People like to build DSLs. And because different hardwares have different characteristics, it also makes sense to build different DSLs for different hardware now today. There are kernel agents that try to generate code. We have graph compilers like TensorRT that tries to generate things. Most of the cases, previously it doesn't matter, but most of the cases today, if you want to build something, you have to interact with an environment language like Python, right? Or frameworks like JAX. Or, if you want to ship to automotive, you kind of need to also consider non-Python environment, right? So one of the challenge that we're looking into is that there's a huge amount of interoperability challenges on how those components interact with each other, especially when they are built by different parties, right? So how can we move forward in this, right? This is really a huge challenge that we're facing. I think there are two ways to solve this problem. One possible way is that, okay, let's try to design a one unified programming language that solve all the problems. And you try to, program everything in that language, and hopefully, that language have great interoperabilities. Maybe one day will solve your problem. However, we know that the ecosystem today do not yet work in that way, right? So a lot of modules are built by different components. They have to work in Python. And because of nature of Python, you kind of need to interact with Rust or C++ for efficiency, right? So by nature, ML system today is cross language. And we kind of need to, alternative thing, if you think about that, is we want to accept the nature that, hey, the diversity is here to stay, right? And how we can enable this diverse ecosystem to work together better and more effectively collaborate in the future. So this is what we want to solve. Of course, we only want to solve a small problem today. The problem is, the interface level. The interoperability challenge at heart is a challenge of ABI and FFI. Okay, what does that mean? First of all, ABI means that when you call from one component to another, how data are being stored, and when a function is called. For example, today if you have a torch tensor, and you want to pass into a function that treated as a CuPy NumPy arrays, you cannot do that because the underlying data layout of torch tensor and CuPy NumPy array is different, right? And also this usually involves foreign function calls, because every machine learning application is effectively mandates cross-language interop, like calling from Python to C++. Every DSO themselves are in nature their own languages, because you kind of need to generate, like if you write, usually you write MIR or LVM code or TVM code that generate LVMs, and then it's kind of like you kind of interface that with the C language, right? And you need to build your own language bindings to support things like how do I bring them in PyTorch, how do I bring them in TensorRT, and so on. So our take is that this diversity is fundamental and here to stay. We want to focus on sustainable interoperabilities. And specifically, we want to make FFI, because foreign function is a first-class concern. We know that it's hard because it's making general interoperability is really hard. Otherwise, you don't have to create specific languages, right? So we don't want to solve it for the general problems. But we do think that it's possible to solve it just for ML system applications. Specifically, ML system applications focus on tensors and a few other field data structures, right? And we think we can solve that for this narrow scope of problems, and deliberate trade-off so that we don't solve general purpose scenarios, but we focus on AI ML system needs. And that brings the project I want to share today with everyone. It's called TVM FFI. And well, it's kind of like so what's the relation with TVM, right? So in general, it was a result of several years of lessons from TVM, but we believe that it's a component that's generally useful for broader ML system community. So today, this is a component that's now spin out as a standalone project libraries that's stayed independent from a specific compiler framework. So you could, for example, write a MIR compiler that targets TVM-FI as interface. You could use TVM to naturally target. You can write your own code generator to target. It's so and it mainly serves a minimum purpose of ABI and FFI for ML systems, right? And it was meant to use across ML compilers, custom DSLs, runtime libraries, and agent. And also, it's of course the relation of TVM is kind of like it's a calling convention that evolves through several years of Apache TVM lessons that's being brought into an independent library. The key elements are, first of all, we use DLPack, which is a common in-memory tensor standard for storing tensors in memory. We have a compact value and function ABI to represent how you might want to call things from each other. We built it on top of a stable C API and ABI, so that you can directly use compiler to target that. It naturally enables cross-language bindings and propagate exceptions language boundaries and with error handling. Finally, it brings first-class PyTorch and Python support, while also seamlessly support non-Python environment out of the box. To be clear, this is not a compiler solution. Okay, this is a runtime convention, so that compiler and others can interrupt. Compiler and other runtimes can interrupt, and we believe it's very useful. I'm going to give you some examples on how it's being used today. Okay, so with this convention, one thing that we can do is actually we can use TVM ABI to ship one library for all the ML system needs. So normally, say you have a library or DSL agent, you want to generate something. What you can do is you can generate your libraries with TVM ABIs. And then there's the libtvmfi, which is a minimum runtime that's shipped by a pip package that we can that offers a stable C API for that. What we will be able to do is once you install these minimum packages, you will be able to leverage some of our Python specific runtime libraries to directly interface with variants of PyTorch, JAX, NumPy, CuPy, while your particular compile library do not depend on all of them. So like we kind of handle the ABI Python layer handles interoperability for you. More importantly, the same library can be shipped to non-Python environment so that you can interact with XLA callback. We also have a Rust binding so that you will be able to directly write Rust code that targets the code that being generated following the TVM-FI ABI convention, right? So it kind of gives you one library for almost all the ML system needs. The first library that adopts TVM-FI is FlashInfer. So FlashInfer is this standard de facto library for IM inference. And how does FlashInfer use it? Right, the way it uses it is that it will use it to ship agnostic binaries across Python and PyTorch versions. So what you can do is you will be able to take existing C++ code in this case, and we will have a TVM-FI export function that exports this into TVM-FI ABIs, and then it gives you FlashInfer sample code. Then you will be able to have utilities to be able to load it in, and you can directly run it as a torch function that you have in here. But also you will be able to deploy it into a non-Python environment, and you can use a C++ library, effectively serve as a C++ library that you can call onto, right? So for FlashInfer, it really benefits us because it gives the ability to be able to ship one unified interface that works for PyTorch, but we also get requests for, hey, can you work it on JAX? And previously, what you have to do, you have to build a FlashInfer JAX binding. But now today, what we are doing today is we just build a JAX TVM-FI binding that binds JAX to TVM-FI for all, and everything that works for TVM-FI will be able to available in JAX. So FlashInfer is one example. I'm going to show you another example in QDSL very soon. Okay. So how does it work under the hood? It's actually very simple. The idea is that we define what does it mean to call a function. And this calling convention is called type erased function or PEG function. The idea is that for any of the function exposing by TVM-FI, it contains several arguments. The arguments, which is a list of arguments, in-memory array of arguments that we're interested in, number of arguments, results. The handle is mainly for closure, so you can ignore that for now. So this is a complete example implementing add one on CPU, written in C, and because the reason why we write in C is because usually if you write in C, it's really easy to write a LVM based compiler to generate that, right? So what you have to do is first of all, once you get arguments, you just read from each of the argument. You check each of the TVM-FI any have a type index. So you check if they are right type index. If they don't, you can use this set raised function to raise the error message to the Python layer if needed. And then you will be able to get a DL tensor back. You can decode your variables, and you can run your compute code here, right? Once you have this, and this, you have this C symbol with TVM-FI prefix conventions, you will be able to directly use the Python binding, for example, to be able to load it in and directly passing torch tensors to it and directly run that, right? So it gives you ability to be able to generate functions according to the ABIs, use it for JIT or AOTs, and allows DSLs to ship kernels for all the environments. And this is kind of like illustration of more specifically what it means, right? So for TVM any, roughly you will have a type index in a head, and you have some payload in there. We have a complete document here. You can go and check it out. Okay, later. We also have various utilities to accelerate agentic flow. For example, agents like to generate code and quickly test them out, right? So we have this loading line function that allows you to directly load in CUDA code, for example, generate something that ships with TVM-FI so that you can quickly test it out in Python easily. Okay. Another exciting thing that we do think TVM-FI can benefit is how we can benefit compilers, both graph compilers and DSL compilers. So since we announced TVM-FI, I think in August, actually on October, we are working very diligently with multiple teams in NVIDIA to directly integrate TVM-FI as their default ABIs. Specifically, QDSL, if for those who don't know, is one of the new DSLs for implementing state-of-art GPU kernels, right? And one of the questions and pain point QDS always had is, how you can interrupt with PyTorch better, for example. And also, usually for DSLs, we also want to be able to make sure the host overhead, which means that, usually DSL GPU are running very fast, very fast. But, on the host side, you still need to kind of convert from PyTorch, check all the variables that are correct, your constraints are correct. Sometimes the host runtime can be even larger than your GPU runtime, right? How can I solve that problem? So previously, QDSL have a lot of pain points that we really want to solve. So I'm happy to announce that QDSL kind of now officially come with TVFI integration. What you have to do is you don't have to do anything. You have your Qt kernels. You enable, for now it's opt-in, but we kind of wanted to kind of move toward default in the future even. So once you compile it, you are going to get an add-on kernel that follows the same TVFI convention. So you will be able to directly passing torch tensors to it, which is kind of amazing. Previously, you kind of need to use explicit conversions from DLpack to be able to call into this function. We also have AOT support, which means that you can have the same thing. You can export the shared libraries. The shared library allows you to be able to load it back onto different environments. Specifically, any of the environment that TVFI works. For example, now with this library, you should in theory use C++ to call into it without having Python environment. Or you can use Rust if you want. Right? But I'm going to show the two examples on how you can use AOT. The first example is you can use TVFI libraries, and you will be able to directly load it back and call from torch. We also have a library called JAX TVFI that integrates TVFI with JAX FFI, so you will be able to load it back, and you can use JAX FFI call to call into that from your JAX environment. And we're actively working on other environment like TensorRT integration and so on, right? So for DSOs, it means that it gives you ability to be able to compile your kernel with TVFI enabled. There are additional things I do not have a chance to talk about, but in reality, by adopting TVFI, the overall calling host overhead get reduced by 10x. From originally you have to spend more than 10 or 100 microseconds on the interface level to about 2 microseconds. For reference, most of the kernels we care about at Blackwell is about 2 microseconds. So like previously the host is killing you, but now with TVFI you are able to kind of claw back a lot of performance. We also do like a shape constraint track directly within the compiled code, so that you don't have to do your constraint track on Python. That's also a huge saving. It allows you to pass PyTorch directly. You don't need to worry about how do you bind PyTorch. And this is a very great advantage for DSLs, because previously most DSLs need to worry about how do you bind PyTorch, but now you don't have to worry about it. You generate TVFI ABI functions. TVFI is going to handle it for you. And also, it gives you kind of like a compiled argument validations, as TVFI performs like fast compile check. So for example, it's going to raise a nice error, like type error, if you pass integers for functions that expect tensor. Of course, no, it's not only QDSL that adopts it. There are other DSLs that adopts it. From Talan, which is based on TVM, also adopts TVFI. And what they find is that both in terms of CPU overhead and compile time, they are getting huge amount of reductions in terms of like CPU overhead and compile time. So, of course, people might ask, what does it take, right? Do I have to adopt TVM as a holistically? I want to build my MR compiler. How can I use TVFI? The answer is yes, you should be able to use it. For example, actually QDSO was MR based, right? And we kind of make it target TVFI very nicely. This is mainly a runtime interopt convention ABIs that's going to benefit everybody. And of course, we're also going to continuously building first-class support of TVFI in TVM, so that TVM community can also continually benefit that. For example, Talan is one example. So to conclude, we are kind of in an exciting time of building ML systems, right? And I really believe that it's important to build reusable components that makes all those things talk to each other, instead of saying, hey, I'm going to build one solution that works for all, right? So we are kind of moving a lot toward that directions. And TVFI is the first step in the TVM community, so that we believe to be able to build useful components that broadly are useful. And we are going to bring in a lot more in the future as well. And if you're interested, definitely check out this GitHub repo, Apache TVMFI. It's already being widely used, and we're kind of getting a stable state where it's already being battle tested in like FlashInfo, QDSO, and a few others are coming. And SGLang actually more recently, SGLang adopts the TVFI as a JIT ABI convention. Okay, with that, I will be more than happy to take any questions.
Perfect. Thanks a lot. Big thanks for sharing all your thoughts and taking the time to participate today.
Yep.
I think we have time to take a number of questions from the audience.
Who wants to go first?
Come on, there's so many compiler experts here.
Yep. Here's a question.
Yep. I might have to repeat the question. Let's see if we
Maybe
can hear
I follow up the panel discussion. And yeah, of course, you need to have some kind of reliable code generation. And do you expect that we will get at the end to a solution where no human-based assessment of the code is necessary? What do you expect?
That's a great point. So I think today we are not yet at that point, right? So I think as one lesson we take from multiple years of ML compiler development is that usually you want something in the middle, right? So of course, one day eventually maybe you don't know, but you don't have to have human to access the code. If you're comfortable with agent accessing it, I think we're already getting to that point to some extent. For example, the Vibe Tensor project we just released from NVIDIA shows that you will be able to get a completely runnable, PyTorch-like framework by agent, right? So we're kind of roughly getting to that state, but I do think it's important to. I don't want to deploy that into production, for example, right? So in order to deploy that in production, it's still useful to kind of modularize and making sure we can have reasonable test and a bit of human intervention. The question here is not about, can we have zero human interventions, but can we have as little human intervention as possible, right? So that still gives you translated to things like 10x productivities in terms of like a work to be done. Yeah. And that's why we kind of build a flexible bench, because we do believe like some of those fundamental components can help us to be able to get that productivity. Yeah.
Perfect. Thanks. Any further question?
Yeah, here's a further question.
Oh, thanks very much. Yeah, things like the tensor as all developments, I guess you're right. You have these logical tensors, but different frameworks might prefer certain data layouts for their fast algorithms, or logical tensors might be sharded or in some other way split up. So like, how do we kind of reconcile with that challenge of like different environments requiring different layouts?
That's a great question. So the question is now the layout, how do we reconcile a layout challenge, right? So the idea is that TVMFI do not aim to solve the reconciliation problem. It just aim to solve, at least have them talk to each other, right? So for example, if you expose a library that expects certain layout, you still expect the input environment to be able to shovel the data into that layout. But at least we want to enable a mechanism so that at least you can call into each other, right? And in order to reconcile the layout constraints, a lot of cases it might need compiler or co-design efforts. That's my take. But on the other hand, I do think that it's also important to kind of follow a reasonable standard. For example, if you can directly interface with how PyTorch stores things, it will be much better, right? And it's not hard to represent certain pack layout in PyTorch as long as you have add a few dimensions. So that will start from there. Yeah.
Okay. Thanks a lot. Okay, I mean, I have one more question to finalize. I think what you're working on, I mean, it fits perfectly to the theme of this workshop. So we want to bring compiler communities together. I mean, many of us have started out with the TVM. Now many are working on MLIR, XDSL, Mojo, and so. Yeah. What is your prediction? Where is this going? Are you going to bring all of them together with your new proposal, or do you see different languages, different frameworks having different niches?
Yeah, I do see, like I said in the talk, right? I do see like ecosystem diversity is here to stay. Also, like one can say, let's build one solution that rules them all. I do believe like having a broad ecosystem and having the interop together is kind of like the right state and right goal to tackle it. So really, the question is how we can make sure interoperability is more seamless, right? So that's why we want to have ABI convention that helps each of the component interop with each other. With TVMFI, actually, it's much easier to deploy your own DSLs to a production system because, say, once TensorRT is able to call into a function in TVMFI, any DSL that exposes the TVMFI will be able to seamlessly integrate into TensorRT, right? Or JAX or PyTorch, because we kind of already have binding support for them. So having this kind of like a common ground while allow everybody to be creative in their own components while talking to each other, I think it's like it's going to help the community broadly in general. Yeah.
Okay. Thanks a lot. Let's give another good back hands to Jianqi. Thanks a lot for taking the time.
Cool. Thank you, everybody. Yeah. Thanks for having me.
Okay. Have a great day. Bye. Okay. I think we are going to take a 1 to 2 minute tech break to set up the next presentation. Good. So up next in our international track is Perry Gibson. So Perry is a member of the technical staff at Fractile. He will present us the talk with the title, The Compiler Before the Horse, Design Space Exploration at Fractile. Let's give a big applause to the Perry.
Oh, thank you. So I guess just might start by introducing Fractile. We're a startup. Hopefully by this time next year, everyone will have heard of us. But let's say, for those not in the know, we're building next generation frontier model inference hardware. We're based in the UK. The aim is to run the most advanced models up to 25x faster at 1/10 the cost. And we're doing that by co-designing the memory and compute in a way that's tightly coupled. Quite ambitious, but I think we've got the capabilities and the risk management to pull off. And I think a key part of that is the software stack being part of our story from day one. Here's the thing that we don't do at Fractile. Like we've been saying this the whole time, we don't want to build a DeepSeek machine. I think if you look at the history of ML hardware startups, models change quickly and you're always having to make some bets, but like we want to make sure we don't overspec on what the models are today. Sure, contemporary frontier models need to work well because ultimately that's what will sell the hardware. But we do need to kind of like figure out what will workloads in 2 years look like and make sure the hardware is capable of handling that. Again, it's making informed bets. And so we really need to find that balance between generality and domain focus because NVIDIA does general quite well. But we need to like find where in that spectrum of ASIC for just one model versus general purpose can do anything. We need to do it quickly. So we really don't want to be a one-trick pony. Just a little bit about myself. My focus has been machine learning and systems. If you saw earlier today, Dr. Jose Cano was talking about High Peak next year in Glasgow. I was in his research group at the Glasgow Intelligent Computing Lab, where I was looking at like machine learning acceleration with compiler-centric view. And now I've moved to Fractile, where I'm trying to apply that to industry. So it's been quite a natural transition, but obviously there was a switch to prioritizing certain like engineering requirements that in academia one doesn't necessarily have. One of the things that Dr. Cano and I developed during our time was something called the deep learning acceleration stack, where there's the problems you're trying to solve with like ML models. There's hardware you're trying to deploy it to. And then in between, you've got this whole like stack of both ML, software, hardware techniques that you can use to get more out of your model. But the thing that we need to be aware of is that like choices that you're making at any level of the stack are going to interact with each other. So like there really needs to be this collaborative process of knowing your own area of speciality, be it compilers, ML or algorithms, system software, and being able to like learn about the other parts of the stack and also work with people that are experts in their own little area. I might start by like pointing out a couple of other keynotes that I think were quite influential to me over the past few years. The golden age of one being computer architecture, the other being compiler design by Patterson Hennessy and also Chris Latner. I think they both kind of were developed. I think Chris's was afterwards, but like kind of from the same observation that since Moore's law has been dying for over a decade, let's say, this actually makes architects and compiler folks' lives more fun because it means that it kind of further motivates more application-specific hardware and related compilers rather than just saying, "Oh, just wait 2 years and we'll make our adder tree better." So, like, but I think a takeaway from that is that it thus means it's more and more of a responsibility to think and collaborate across the stack. So I guess just taking a little bit of what we're doing at Fractile, like especially the early days, I joined like mid 2024. We really wanted to have that rapid design iteration. So we were exploring the fundamentals of the architecture. We were thinking, like how much in-memory compute do we do? Like what are some off-the-shelf IP that we can leverage? Where is our differentiator going to be? And getting some proof of concepts done quickly could be useful for stakeholders and also our own understanding if there's knowledge gained from that. But what we really wanted to make sure is we were doing realistic workloads. Micro benchmarks are not enough. You can make map models as fast as you want, but these models are big and comms and other stuff will dominate. You want to understand like the whole system. And we really can't promise a magic compiler. We need to be able to say what is realistic for us to generate. And like, as these workloads develop, what can we have with that day zero performance? So just going to take you for a little journey of like what we've been doing with the compiler in Fractile. So like, why would you even build a compiler when your system doesn't exist yet? Isn't it way too early? That's kind of putting the like cart before the horse is kind of the extended metaphor that I might kind of like overdoing, but let's have some fun here. I think it's important to focus on knowledge gain. Like a compiler can help you learn a little bit more about your system. As long as you're doing it in the right way. I think worrying too much about making it production quality and when you don't even have like register interfaces or all the like parts of your system ironed out yet is a waste of time. But there are like some high level structures and other things you can do that can help like inform conversations with hardware people, architects, and other people in the systems part of the organization. And moreover, like building something that's broadly end to end, even if it's a bit sketchy, helps validate your team can work together, make something that actually works. Also, showing that, say, a model on a simulator can give you some token generation is an early win, makes people feel motivated, and can show that your organization can actually do something. So we had a few design phases. So when I joined, we had one of our great contributors to the company was a former CERN physicist. I showed up. He'd written a simulator for initial system design in Python. He'd also written a compiler using just pure Python regexes. I mean, like it was kind of amazing that it worked, but like I don't think that was like something that was going to scale for us. But like, yeah, really impressive that like someone can come and just do it because there are no rules really. So from that point on, we were like, okay, what do we want to learn here? Let's get some proof of concepts that will let us validate parts of our system. Are we going in the right direction? What things do we need to change in the broad strokes of the architecture? Then from like some early wins there, can we reassess, there's some lessons and maybe plans about how we actually build a system that can be taped out in, a realistic amount of time and cost. Then we need to, when we've got the high level architecture sketched out, we need to think about the minutia. Like there's the low level programming interfaces, all these memory spaces. How are we doing all the data transfer? There's like a lot of minutia that we need to think about. And then finally getting into that execution, we're trying to build some production quality systems here that we're maybe hoping to sell to hyperscalers or whoever. So that's heads down. Let's get some proper engineering done. So yeah, just kind of walking through the validation stage. So we needed something that worked and quickly. So a goal we chose was running Llama 2 7 billion on our functional simulator. It was moderately sized LLM and kind of would stress out our systems without being like a trillion parameters and like, have a debug loop that was crazy. And this allowed us to reason about how we would lower this workload to our hardware, at least our hardware as we envisioned it at the time. And we designed and implemented 13 compiler phases using a lot of open source infrastructure that was available. So first of all, being MLIR, a lot of people have talked about it already, but it's framework for compiler development. And you've got these dialects are representing various domain-specific operations at different levels of abstraction. For example, here's some IR showing just adding like 1 to some value. There's no magic there. And one thing we looked at was that MLIR has like lots of support for machine learning representations. It's a very great open source community here. And you can export from many of the DNN frameworks, for example, using the stable HLO dialect. And it also has Python bindings. And Python is great for hacking around with when you just wanted something that worked quickly. So here's a quick example of like a very shoddy Python transformation that we might have made. So here we can just walk through our graph in some inefficient way, apply some transformation. In this case, we're going to replace an addition operation with a subtraction. And here's the IR change. Compilers ultimately is just taking a text file and changing it to a slightly different text file. And you just do that a bunch of times. So we were working closely with our runtime software and functional simulator teams. I mean, roles are not that straightly defined, well, a lot of them were the same people, to develop and integrate some low-level hardware APIs and debug and develop the simulator. So we got this version 0.1 compiler and software stack. For the most part, I'd say it's a graph compiler because our system is looking at running in data centers. How do we partition this graph over multiple devices? There wasn't much value in doing low-level kernel optimization because, yeah, like there was minutia that like are going to change quickly anyway. So yeah, we got this sketch of our system, and I think that really helped us understand what we needed. And then later we can like flesh out some details. So ultimately, that part of the project was a success. We ran Llama 2 on our simulator, both single and multi-token. We completed this work in a single quarter, which, you know, partly is due to the great team that we've got, but I think it's also part to like a lot of you here. It's because these tools are out there available. You know, we can they're open source. We can contribute. We can get what other people have been doing. Like this wouldn't have been possible without like the wider community. And yeah, we got a great understanding of many aspects of our prospective stack. And yeah, here's an example. We put in the token hello, and Llama generates the most likely token, which is nobody. I was hoping for world, but yeah, that's what we got. So then we kind of took this point to reassess. You know, implementing this end-to-end graph compiler developed our workload and systems intuitions. We've also got the hardware part of the organization that we were like heavily communicating with. So, you know, information from our initial test chips and other discussions motivated some major architectural changes, or, you know, a couple of major ones. And this created a bubble of time for us to build some solid software foundations. So, you know, while we kind of worked out some of these architecture changes, we thought we'd do some things at this point. So transition to C++ compiler, or still set up some of the infrastructure for it, wrapping some of those Python passes that we wanted to keep, and transitioning when we've got the time. Did some tweaks to the compiler pipeline that we had, because we thought, well, hey, you know, this is all going to be thrown out eventually, but there are some changes we can make iteratively to just kind of bring us a little bit closer to something we can build out. Anticipating those hardware changes as and when they come, as we like decide, oh, we want to have some passes that are going to be more flexible to the direction we're going in, and just some general infrastructure for the company. So, you know, doing some Bazel build system stuff, setting up a monorepo, the kind of things that is good to have like at that point in our development cycle, so that we could like just run for it at the stage that we're at now. So now let's kind of move on to this define stage. So I'd say it's like time to eat your vegetables. So at this point in our development process, the high level architecture is locked in and on track. And now what we really need to think about is the minutia. How would bare metal programming work here, like in our system? And we want to uncover some design or programmability issues early, of like what's happening within individual processing elements, or like individual SOCs or whatnot. So some big questions that we want to answer there, some of the nuances of the programming model, synchronization mechanisms, specifically where are different configuration parameters living, all that kind of stuff. And yeah, crucially making sure that we're like understanding different workloads that aren't just DeepSeek or Llama as well. So at this point, we kind of stopped using MLIR and whatnot for a while, and entered a stage that I like to call it the human compiler, where we're wanting to write some of these models at a low level by hand. You know, so saying like, well, what's our scheduling core going to do, for example? What would our compiler generate? We just want to like say, hey, like at this point, like write out some layers of DeepSeek or a state space model, start to build up some libraries of like, oh, here's something that seems reasonable, like written in C. You know, thinking about fine-grained scheduling, memory mapping, and all these other questions. And as well, some new low-level APIs, as we kind of have communications with hardware people about what our register interfaces and other things going to be. So yeah, our pipeline is we might take a model off of Hugging Face, sketch out some stuff on the whiteboard, write up like what that might look like, what hardware requirements are in, say, a Notion page, then write some C in assembly. And we can automate the compilation of that as time goes on. But we really need to make sure that we're comfortable that we could write this by hand, because you know, someone's got to do it eventually. So now, like, we've kind of understood our workloads a little bit better. We're comfortable that our hardware is actually programmable. There's nothing up my sleeve that it'll magically work. How does this part of the system know to do this X, Y, and Z? So I guess I'll say, like, from day one to today, like, we've really grown. So now we're like 70 employees. And it was, I'd say that, like, although I'm coming from more of a compiler systems background, it's very intersectional and this interdisciplinary. We've got ML people, we've got hardware people, and I don't want to center too much what the compiler team has been doing. It's all about people going into rooms and being able to like listen to other people give their expertise on like what can actually be built from a process node perspective, like what the latencies of NOx will be and all that kind of thing. It's very much a collaborative process. And yeah, everyone took their turn wearing the architect, modeling, and ML engineer hats. I think that's like been a really positive experience of the culture, and I think necessary to actually achieve the kind of co-design exploration goals that we've had. So now, like our priorities, we really need to ensure successful tape out because we live or die on that. And yeah, we've really got to scale our team, so we're aiming to double by the end of the year. We need to build that compiler. We've got that initial graph level compiler where we generated some LLVM IR that worked well in the functional simulator. But now we want to think a little bit more about how do we match that handwritten low level stuff in our compiler pipeline. There's some integration requirements with inference servers that we've been looking at already, but questions around what do we actually need from the ever-moving space of things like VLM, SGLang, etc. Because yeah, these large-scale models have a lot of questions around deployment that aren't just about fast kernels. And our ongoing evaluation of emerging workloads, we need to make sure that like if something funky comes out of a research lab that seems like it's going to change the world, we need to be able to be confident we can support it. And yeah, having fun along the way, because otherwise what's the point? So yeah, overall, in conclusion, I'd say that taking a compiler perspective early at Fractal has been a key part of our design space exploration. It's not been the only part, but I think being able to like bring stuff that works and is a realistic workload, with compilers automating stuff, like taking a big model and turning into something we can run has been really valuable. And kind of contributing to that co-design with our software architects and hardware designers. Like we are embedded at the core of the organization, and I think that's essential for actually building a domain-specific accelerator like we're trying to do here. Ultimately, I think compilers are about understanding how a high-level workload makes it down to metal. And if you take that perspective, then it's not putting the cart before the horse to work on the compiler early, as long as you're using it to like focus on the knowledge that you gain as part of your design process. Otherwise, you're just like wasting your time making compiler passes that aren't going to be used for a couple of years. So yeah, overall, like, thank you very much. We are hiring, so feel free to come and chat to me or check out our website if you're interested, and happy to take any questions.
Okay, thank you very much. So any questions from the audience for the speaker? Okay, if not, I have a question myself, working at a AI startup as a compiler engineer and leading a team. So where are you in points of this discussion we had in the panel, so day zero? So what is your current approach for bringing up new models, and how long you need for that?
Yeah, I mean, I think it's a good question. Of course, still being like pre-product, it's something we're anticipating rather than they're like testing with customers right now. I guess when there's maybe two sides to day zero, there's one having the model can it actually work, and then there's that time to performance. I think in terms of the model actually working, by having like some general purpose hardware, for example, like we've got partnership with like a RISC-V vendor, and having these open source MLIR dialects, for example, stable HLO and other ones, we can be relatively confident that we could generate some code from a model if it can be exported on our system. Whether or not it's performant or not is a question of like other parts of our compiler pipeline. I think it's important that we like have that like view of learning about how to accelerate stuff in our on our system. Some of that is about writing these kernels by hand, doing these partitionings across devices, all that kind of thing, and then saying what are some patterns we can from like mapping, DeepSeek mapping, a state space model, that kind of thing. Are there some generalizable patterns that we can start to bring and add to our compiler? So we're building some hardware that is a bit different from NVIDIA GPUs, but we want to make sure we don't get too far away from that. Otherwise, we kind of get stuck with something that people aren't building models that support it. But yeah, I think that getting something that works is key to us. Getting something that is performant as quickly as possible is also critical. but that's part of a learning process, and making sure you've got the infrastructure to apply the things that you learn about mapping workloads by hand in a more automated fashion.
There's a question from the audience.
Yeah, hi. Thanks for the talk. I really like the perspective of how you use the compilers to sort of understand the system. Great. Do you have any concrete examples of things like things that by doing the hand-coded things, you realize, oh, I need to be able to express this in my high-level abstractions, or the other way around? Well, you were doing sort of this bottom-up approach first, things that you realized maybe the hardware guys were spending too much time and was perhaps not needed. Like examples of co-design or insights or things that did not work.
Yeah, so I think from that side of things, like there are system we're like actually writing stuff by hand. We were previously hand waving certain parts when you're doing it at the graph level compilation. But then we're thinking, okay, what are the like quote unquote processors on our system? And we're thinking, hold on a second, we've got things for moving data from one place of the system to the other. We've got things that are managing our synchronization between different things. And when we're like configuring all these things, the question that came up quite a lot was, where are these configuration parameters living? How, like, what part of the system is allowed to configure different parts of the system? And I think some of those questions hadn't quite been answered yet. So like during this exercise, we were like making sure we had some like software defined like a little Python script somewhere basically where we were documenting like what tensors and other data are we allocating here in these programs and where is that memory living? And our kind of compiler mapping team ended up quote unquote inventing memory spaces that were like in principle in the design but hadn't been explicitly called out with regards to say writing parameters of how data is getting accessed across different banks and that kind of thing. And I think that like actually getting into the weeds and, as I said, eating the vegetables was essential in doing that, because otherwise we'd find out way too late where does this data live and we haven't actually made hardware for it.
Okay, Michael, if we have time for one more question, I'd like to ask that.
Go ahead.
Perry, you haven't been talking about quantization yet. I feel like you may have an opinion on that regard, specifically because you also mentioned fallback options to your RISC-V core that might be more capable than maybe the hardware that you ultimately deploy to. Would you consider a compiler taking in quantized models, or is quantization an element that you believe a compiler could be taken care of? Is there an opinion on your side?
Yeah, so I mean, I think quantization is like an essential part of that optimization loop. So I think I showed the stack earlier, where that's like something that can really improve performance, significantly reduce memory bandwidth and latencies, which is key for how big some of these models are getting. I think from our side, there's data types that we're looking at is that we think we want to support as first-class citizens. There's questions of like, but it's also moving quickly. People care more about bfloat 16. People care more about these block scale types, that kind of thing. So that's part of where we need to make these careful bets about what we think people want to do in our system without like throwing everything, including the kitchen sink, at it. If you've got this general purpose hardware to fall back on, you have maybe a little bit of that risk of like if you've got quantized types, you end up having to emulate or like dequantize on the fly. But from a day zero perspective, it does mean at least you can run the system even if it's slower. But yeah, we want to make sure that like our like custom hardware is supporting the data types people care about and quickly. And representation within the compiler for that can be tricky because things like MLIR have a lot of data types that keep on coming out, but there's still not, for example, a standard representation for like block scale types. So it's thinking, how do we do something that is going to be taking advantage of that virtuous cycle of open source community, but also sometimes it takes a while for stuff to get into the main.
Thank you.
Okay. Perfect. Thanks a lot. Okay, next up is a talk by Huawei. We're quickly going to set up slides and then we can get started. Slides. Great. Thanks for setting up, Sebastian. So it's my pleasure to introduce for the next talk, Vladislav Lukiana with Huawei. He's a senior software engineer there with quite some good experience on AI hardware. He's going to talk about hardware-affine compiler ecosystem optimizations for SAN. Well, I think your title has changed, right?
Yeah.
Okay, maybe then go away.
Thank you. Hello, everyone. And let's start. We will start from the GPU architecture overview just to make it easier to compare with Ascent architecture later. And we will focus on memory units. Let's forget about computing units for now. Let's start from the streaming multiprocessor partition. So we're interested in register file, which is 64 kilobytes, and load store units, which are basically threads just issue a bunch of individual memory operations. So let's move on upper level to the streaming multiprocessor. It has tensor memory accelerator and TEX units. TEX units were originally meant for like texture and surface fetches. So like also they can do level of details filtering. We're mostly interested in TMA. So TMA is like a asynchronous memory transfer engine for like huge amounts of data. And yeah, that's one of the benefits of the new GPU architectures. And of course, shared memory is fast, as we all know. If we will move to the graphics processing cluster, which consists out of multiple streaming multiprocessors and have a benefit of SM to SM network. So it's also pretty new thing with SM's ability to communicate between each other. So you don't have to go back to the global memory to send some data or read some data from shared memory. Yeah, that's it. And now let's go to the NPU architecture. It's ASM 910B, or else it's called DaVinci V220. So nowadays we have a newer cards, but still not a lot of info about them. So let's also focus on memory and start with AI vector core because it's simpler. It's on the right lower part of the slide. It consists of unified buffer, which you can think of as shared memory, and vector unit, which is responsible for basically like element-wise vector math. Think of activations, reductions, pooling, etc. And we have a Scala unit, which is responsible for instruction flow and Scala operations. So, for example, dispatching instructions. So you can think of it as a small CPU. It's responsible for loops, branches, and address math. Let's move on to the AI cube core in the upper half. And it's responsible basically for matrix multiply accumulate operations. It's optimized for dense gems, convolution style workloads, As you can see, it has like separate buffers for the inputs and outputs. So you usually will see like your inputs in L0A and L0B buffers, and output will be in L0C. BT buffer is just a bistable buffer, and the interesting part is actually fixed pipe. It's one of the features of KubeCore, that it can do quantization, dequantization, pre-quantization on the fly, so you don't spend extra instructions on that. That's it. And yeah, you can see some basic technical specs of the units, and also in newer ASCENT 950 series, we will see SIMD plus SIMD, a hybrid solution, because currently it's only SIMD, and it should help with arbitrary memory accesses. So, and now to the platform stack and the priorities of the company. So it's kind of similar to the NVIDIA talk we've had today. So like, how do we achieve day zero support for the newer models in like inference and 7, like HDLang, VLLM, both of those products. HDLang is merged in the Streamline repository, so it's possible to use it out of the box. VLLM is like community hosted and maintained by community, so kind of independent now. Yeah, challenge 2 is about graph fusions in Inductor. Also, how to fully enable ASCENT-friendly support for operator programming languages. We're talking about Triton, TileLang. There's a bunch of work there. Currently, TileLang is also hosted by community and maintained by it. Triton ASCENT is currently hosted by Huawei, but we're hoping to be merged into the Streamline at some point. Challenge 4 is how to build ASCENT-friendly compilation technology based on MLAR. And challenge 5 is about how do ASCENT and PYR and LLVM jointly optimize to generate the best binary code. ASCENT and PYR is also open source. So yeah, those are the challenges and the priorities of the company right now. Some of them are like partially solved. Some of them are basically open questions. So we're seeking for the involvement. Here's the list of, this is one of the answers to the questions of how to like have a day one support, with the day zero support for the newer models. We have a huge operator coverage for ASCENTs. So we have like 100% coverage for the top 5 AI models, and we need a bit more to support like top 40 most popular ones. Yeah, sometimes it takes time. Like for example, if we would take like gather or scatter category, sometimes it can contain like a bunch of variations of tiling types, shapes. So different tiling strategies are required, and since we're talking about ASCENT, it's done for template programming, so it takes time sometimes to support operators. And here's one of the challenges. It's about CutLass. It's CAN templates for linear algebra subroutines, similar to NVIDIA's CutLass. Yeah, and so like brief introduction of how it works in Inductor. Inductor checks can we fuse? Yes. Like if we want some specialized gem operation, then it goes to the CODAI. If CODAI cannot offer such an operator, it will go to the Triton and else fall back to the handwritten or vendor provided kernels in ATanops. Yeah, so what's the deal with the CODAI? Currently, the NVIDIA CODAI works like that. Inside it, there is a logic for selecting proper kernels, proper tilings. So Inductor asks CODAI to provide proper kernels. CODAI selects, Inductor runs. Yeah, Inductor has also like auto tuning and some benchmarking inside it, but for simplicity, let's say CODAI selects, Inductor runs. And for Huawei's CODAI, currently it's opposite. Inductor selects and CODAI runs. So Ascent Inductor contains some logic in it for selecting proper kernels from CODAI. That's one of the to-dos. We need to offload the selection process to the CODAI, similar to NVIDIA's CODAI. But also we need to, param selection, tuning inside. There is some, we need more. The issues are that it's designed mostly for NPU architecture, not synced like GPUs. So a bunch of issues with memory transfers. It's not that easy going around that. So we have to invent a bunch of stuff. CODAI currently supports fixed pipe, so allows quantization, dequantization without wasting extra instructions. It has some tuning capabilities through MindSport tuner, and currently it's only C++ first. What it means, it can be used from Inductor, but only by Inductor itself. The users cannot use it from Python. That's what we also need to work on. One of the extra differences is that CODAI supports epilogue visitor tree, so like very flexible fusion of kernels, like the main loop and epilogues. That's something to implement. I think that's it for now. And let's switch to the Triton because currently Huawei is actively supporting Triton through Triton Ascent Repo. It's open source. You can check it out. And to demonstrate it, let's go through the IR pipeline for the Ascent cards. We start with Triton DSL. We're still in Python world. API was designed for GPUs, so not so obvious how to port it, but we managed to. And next step will be transformations from DSL to the Triton IR. So for example, as you can see on the snippet, tail.arrange, for example, will become TT make range instruction. Tail load will be a combination of splat, add point, and load. So at the Triton IR level, we still are in the high-level tensor abstraction world, but already have like explicit pointer arithmetics then. And at this point, it's a problem. We won't be going next level to GPU IR because there will be too much architecture differences. So we switched to our own Triton Adapt or Triton Adapter IR, depending on the sources you read. So at this point, we try to transfer from tensors to physical memory to get rid of Triton dialect from our IR and to move to the more basic ones as memrefs, linalg, and some specialized ASIN-specific dialects for hinting. Here we already move from like copying data will be done through memref subuse and memref copies, through tensor extract insert slices. Yeah, so level down and we move to ASCENT NPU IR, and that's the last level that we will be able to see IR before the binary. So it's a hardware specific mapping for ASCENTs. It will assign address spaces, as you could have seen, like global memory, unified buffers, L1 cache. It will replace generic math with NPU intrinsics and insert synchronization flags. It's very important for this kind of hardware, for this kind of pipeline, because it's all built around asynchronous data copies and copying large continuous buffers while asynchronously computing stuff. So, and we're moving to the specifics of the memory accesses in Triton. From the best to the worst. So, affine indexing, easy to tile. Compiler is happy. You can predict the caching, the vectorizations, the block sizes. Then we move to non-affine indexing, which is a bit harder. The main signals are like division operators, the modulo operator. So we will have to do something with them. And the worst case scenario is indirect indexing. That's like indexlet or gather-like accesses where you first read the index, and based on this index, you read the data. So it's data dependent, it's irregular, sometimes it requires runtime checks. So let's move to the non-affine indexing fixing. So like we're proposing two ways of doing it. First one is just linearize indices. So sometimes you can make sense out of them. For example, we had divisions and modular, but we can easily recover row columns and keep the last axis continuous. So we come in from the non-affine to affine, eliminating division and modular operators. And the second example is when we have a flattened index and we're trying to restore the shape and how we should walk through it. You can think about it as deepening for the loop, like we're making basically a nested loop through the dimensions. And the second half is an example with concatenation, because branch elimination can cause negative indices, which are eliminated through masking, but that can make trying to guess like block sizes hard. So you transform those loads to separate loads and like inserting slices to the end buffer. Next, we're going to the indirect indexing, the hardest case. So the example on the left is about index select like. Here's an example from PyTorch, but you can think of just memory access patterns similar to index select. So for index select workloads, it's enough to do mask and offset analysis, and usually if it's along the last dimension, you can find like continuous blocks which you can copy. In this case, for example, we can copy full rows. And for the gather like accesses, if it's along last indices, we still can optimize it from the, like if you see such a pattern in Triton, you cannot guess because you don't have enough context that your indices are in the range. So your indices values are lower than the dimensions, right? But you can do runtime checks. Yes, it's expensive, but moving values one by one is much more expensive. And the last concrete challenge we have is a robust feedback-driven cost model for Ascens. So we have our model inputs like operator. We are using shapes, types of the variables, device we're running on, software version, and through this cost model, which should rank and like produce a confidence score, it should select a proper backend. It should always select the best backend, choose between Cutlass, Triton, and Atom fallback in case of we cannot generate a kernel or it's just confidence is too low about it. And everything going through data store, so we cache the results and we don't rerun it a bunch of times, and it's just, it exists in some sort, but we need a robust model. It's hard because there are a lot of specifics with DMA orchestration and QB constraint and in general memory buffer constraints on NPUs. So that's like an open question, and thank you. We're very desperate for the compiler experts, so we're hiring. Feel free to talk to us in the lobby. Thank you.
Thank you very much. Yeah, amazing to see also the company perspective and so many hardware details. It's great to see that on a compiler workshop.
Yeah.
Are there any questions from the audience?
If there's no question from the audience, I would have a question. So thank you very much for showing right in the start kind of the background of what hardware you would deploy to. Do I understand correctly that the architecture that you've shown would be generally be capable of heterogeneous compute, or is the programming model for the entities that you showed, the cube and the Scala entities, would those be are they basically compute-wise able to run in parallel, or is this individual
No,
pipelines?
they can run in parallel. You usually have AI calls consists out of one AI cube core and two vector cores. And yeah, you usually try to asynchronously do stuff so that vector helps your cube unit to do some added biases or something else. Yeah.
Yeah.
Sure.
Is this an approach that you've kind of embedded in your compiler stack to kind of leverage?
Yeah. We try to support as much software as we can. We want to build a good development environment for people, and yeah, we're competing with bigger companies.
Thank you. Other questions from the audience? Yeah.
Thank you for the talk. Regarding like auto-tuning stuff, is there anything you can around how you represent your hardware to like auto-tuners, or is it driven by running benchmarks and building a database?
That's work in progress. We have some simulators to try and predict the performance, but I would assume we usually take a look at the like real world data.
Good. Anything else? If not, then let's thank Vladislav again. Thank you. And then we will have a coffee break. Okay, let's get ready to kick off the last session. Let me bring up your CV and then. Slow connection, slow Wi-Fi connection. Yeah, better than German. Okay, I'll do it while it's loading. So, okay, let's kick off the last session. So it's my honor to introduce Maxime Dax. So he's a Mojo champion. So working in the infrastructure of Mojo, a very new programming language for AI. So he will give us an introduction into solving the multi-platform problem with Mojo, like a general overview. Thank you, Maxime, for joining today. And let's give him a backhand.
Thank you very much. Right. So I would like to talk to you about a programming language called Mojo. The programming language is developed by the company called Modula. I'm not affiliated with the company. I'm an open source contributor. And the company was founded by Chris Latner. I guess people know who Chris Latner is in this community. So yeah, let's start. What we'll have, like what I would like to talk about, basically, I would like to give you a quick overview of the Mojo syntax, not into depth, but just an overview, the type system, how it is connected with MLIR, then how you can write GPU kernels in Mojo, how you, these kernels can be run on different GPUs. Then I'll briefly talk about Mojo and AI. Like the language itself is actually like the main focus of the language currently for Modula is actually on AI, and I will talk briefly about it, and then we have a short outlook. So what you see on the screen is just simple hello world, right? And what strikes the most, basically, Mojo is a systems programming language in the Python skin, right? So like the idea is it should look familiar to AI developers who mostly know how know Python. So with Mojo, the idea is to be very familiar, but generally you have much more like tricks in your sleeve. So like this def main is just definition of functions which we know from Python, but in Mojo we could also write with a different keyword with fn, and this means that the signature of the function is more strict. We need to tell if the function raises or not. The def functions always raise because they always could raise in Python. In Mojo, we could say if it's raises or not, and we also need to define fully typed for signature. If you would use the def keyword, you don't have to do it actually. Let's see a slightly more complicated example. Here we define a sum function, right? Let's see if I can see my cursor. Like we define a sum function which has two arguments, a and b, of type int32. It returns int32, and we just do a plus b. Then in the main function, we just print out the result, and we have something interesting here. We imported the compile module, which has a compile inf function, which can be a compile time parameterized over this sum. This is also, it's kind of like, looks like Python, but it's not. There is no such syntax in Python where you can actually just define compile time parameters and don't provide any runtime arguments. What it returns is basically, we see like, okay, a plus b, 50 plus 20 plus 50 is 70, correct, right? But what interests us more is that we see like, okay, the function translated just to one operation in assembly. right? And this compile time info returns us the assembly of the function, so we can introspect the outcome from the compiler. We see here, that's very nice, okay. Like we also see that the type is a little bit funky, and we will talk about it in a few seconds. It will make much more sense. So now we would like to break it. We say like, okay, now I'd like to do like sum over 2.1 and 50, right? And the compiler tells us, okay, sorry, it's floating point literal, so I wouldn't be able to compile it. So what we can do, we can generalize the sum function. We do it by defining the function with a compile time parameterization, where we say like, okay, we would like to define d time as a compile time parameter, which can be inferred. And the A and B, we can define a scalar over d type, and then we return scalar over d type. And also here, like we see that in sum, we don't have to, as the parameter can be inferred through the literals, we don't have to define them. But here in the case of compile info, we don't provide runtime arguments. We need to define it explicitly at compile time. To say like, okay, I would like to see what you will generate for d type of float 32 as an example. And we can see here again, perfect is just one operation, but it's already a different register, right? So like something is happening here. We can generalize it even further. We can just say like, okay, now we provide d type as a parameter d type and also the size, and A and B becomes SIMD vector over d type and size, and we can add them. Right? Still, again, the compiler can infer the d type and size in case of literals, but in case of like when we need to want to see like what it will compile to, we can provide these parameters directly at compile time. And then, as you can see here, we have here size 32, right? And I compiled this program on an AMD laptop with AVX 512. So the result is just two operations with 512 bit white registers. All right. So we might ask ourselves, okay, how does it actually work? What is a D type? And D type is actually also just a struct in the standard library, which is actually just a facade on top of an MLRI type. We see that we have here this dialect called KGen, which is internal to module compiler. And again, what's interesting here is that we see an assignment prefix with comp time, meaning that this assignment will be evaluated at compile time. In this case, it's just, you can call it just a constant. But if you look here, actually, like right-hand side of the assignment can be as complex as possible. It will be still evaluated at compile time, and there is no runtime cost for this. And here we see like we're actually instantiating this type and have like an alias for int32. Here's our old friend int32, and this is just an alias for scalar over d type int32. Scalar is again an alias for SIMD where the first parameter is unknown yet, but the size is equal 1. So like basically we have just a vector of size 1. And SIMD itself is also a struct. Again, it's a facade over a different MLRR type. This time it's the POP dialect. And you can also see that we can internally express like templating of like MLR types directly in the language itself. It's possible to create complex expressions and evaluate them to compile them. Right. So what about GPUs? Right. So with GPUs, here's an example for addition of vectors. And again, what we see here on top is just typical boilerplate that you need to define like everything at compile time again. So it depends on the compilation target, but we just define like, okay, this is the size, this is the D type, this is the layout, like the block size, num blocks. And the function itself is just a regular function with some regular types which you have defined in Mojo as well. So like on the abstraction level, it reads like as simple as CODAI, right? But it's kind of in a familiar syntax, and it all looks fine. And generally, like the computation is also quite regular. You compute with thread ID, then you check that the thread ID is smaller than vector size, and you just do the addition. Simple. In order to call this, we have this example where we say def main, and we have an if-else statement with a declaration of add parameter, meaning that the predicate will be evaluated at compile time, and it's just basically conditional compilation, right? So like if we have, if we compile for a target which doesn't have an accelerator, then all we'll get in the final program is just print no compatible GPU found, right? If we compile for a target which has an accelerator, then we can instantiate device context, which works asynchronously, so we can enqueue creation of host buffers. Then we can synchronize, we can do stuff on the CPU here, like basically initializing the buffers. Then we print on the CPU. Then we do a copy from host to device. Right, from host to device. And then second, yeah, the interesting part is actually here, we can enqueue a function. Again, the parameterization is at compile time, and I also added this one parameter, which is by default set to false. But here you can also say just, okay, please dump me the ASM because I would like to introspect it, right? And then we do synchronization and print the result of host buffer. All right, so here is the output. As we saw, we printed out the first buffer, second buffer, then we generated the assembly, which we need, and then we see like the result vector, everything works fine. We see what kind of backend was used for generation, and so on and so forth. Again, I generated it on a laptop with an NVIDIA GPU, hence it worked for NVIDIA. Right, what about different GPUs? Well, I picked one function from standard library, which is called store release. It has following parameters. This one is inferred. The others are set to default, or you can parameterize them yourself, right? And what it do is performs an atomic store with release memory ordering semantics. And like the first thing that we do, we have a compile time assertion that we are on a GPU. Otherwise, if you have these functions somewhere in your code and you compile it not for the GPU, it won't compile. It will just complain directly, telling you that atomic store only supports on GPU. Right, the implementation itself is actually just an if-else statement. Again, it's just conditional compilation. And I would like to show you, oops, yeah, show you like internally how it works. Here we say like, okay, if we're on NVIDIA GPU, we have a few compile time statements, which we evaluate at compile time. Basically, here we just say we would like to inline an assembly statement and execute it on value and pointer. In case of AMD, we actually go with an MLIR op on the POP dialect. In case of Apple GPU, we actually have two external calls. And else we just say like, sorry, the target is not supported, right? And here you can see actually that Mojo, I specifically chose this example because it's already in standard library and it shows like that as a developer, you can just pick and choose the layer on which you would like to kind of connect and how you would like to implement something, be it with given C library, MLIR dialect, or directly in assembly. All right, what about AI? Well, would I remove this one? Ah, look, perfect. All right, so for AI, Modular developed a serving inference framework called Max, which contains multiple things, but main things are there is a Python library to describe computation graphs. There are at least two MLIR dialect and a graph compiler which work on them, and then they provide also multiple Mojo kernels which are kind of connected and which can be used from these compute graphs. There are multiple like APIs how you can express a graph. This is the simplest one, and it kind of like PyTorch inspired. So this is just a simple GPT NLP feed-forward network where you just initialize your operations, and then on call, you just execute them and return your tensor, right? If you would like to kind of have your own kernels, you can define them in Mojo. Just a second. Here, you define as, like I'm trying to get this thing out of the way again. Come on. There you go. Perfect. All right. So like you need to annotate a struct. I'm saying like you need to have a static execute method where here we again have a conditional compilation where we say if we are on, if a target is CPU, then we call one function. Otherwise, we call a different function, right? And the implementation for CPU function is quite simple, just zero out stuff and then accumulate the values for histogram. For GPU, it's a little bit more involved. You have a kernel, and then again, you have the context, and you enqueue the function on the kernel, and it just runs. Right. In order to run a kernel, in Python, here is a different example how you can define a graph, computation graph. You would just be able to say like, okay, here is the path where my kernels are located, right? And you will provide it to the graph as custom extensions. Then you use a ops custom with the name of kernel that you defined, and you identify the outputs and the inputs, and then you have an inference session. You create a model from the graph. You can use NumPy for input generation, and everything works, basically. Right. So outlook generally, like in 2026, Modular promised that Mojo will get its first 1.0 release. The development of a Mojo programming language started 2023, so it's like 3 years, and there are multiple milestones defined in the roadmap, and the first milestone will be hit this year, so that there will be a possibility to stabilize the language and standard library, right? Then the compiler should go open source also this year. Yeah, and then if you are interested, you can have a look. It's already open source, but it's kind of like currently is rapidly developed. So the main branch is actually nightlies, and then there are like releases every couple of months. So if you want to build something on top of it, you would have to like do some adjustments every couple of months, which you might not want to suffer through. But starting with release 1.0, things will get stable, so it will be easier for people to build stuff on top of Mojo. All right, this is it from my side. Like, if you have any questions. And thank you.
Thank you. Any questions from the audience? There we go.
Yeah, thanks for a great talk. I like it. It's a lot of code examples, which is great. So I'm just curious about the technical advantage of actually extending the language itself, comparing it to like most of the other common approaches, which just build like embedded Python DSL. For example, the GPU example you showed, in theory, I can also kind of replicate a very similar thing, say just using MLR Python bindings. It's like a GPU dialect with SCF, with ManRev, and lower to MVPTX. I mean, we can do the more normal thing, like for example, what QDSL does is exactly this way. And if I'm going to build my own small compiler, I will also do that. And usually, for example, if you want to take care of the control flows, you can do some ASD passing in Python without actually going beyond it. I'm just curious about like that.
Right. So like generally, it's I would say it's all about control and like possibility to get like the state-of-the-art performance out of it. Because like generally, if you work with DSLs, normally it's much harder to build things without tiny inefficiencies which you need to sprinkle around, right? So like, for example, I think it was October 25, a new AMD GPU came out, and Modular was able to like support it in 2 weeks and have like state-of-the-art performance already. So it's also what Modular tries to achieve is kind of like have performance same as CUDA. And in some cases, like they are like a few percent faster or few percent slower, but generally, like you don't need CUDA anymore as the infrastructure. You have just one infrastructure which will work on different GPUs. It also means when you're deploying, your containers can be much smaller because you are dependent only on one thing and not on multiple, and without all the historical baggage, basically. Does it answer the question, or?
Yes, roughly. And I just want to clarify. So you're more referred to the efficiency in compilation or in actually execution?
Execution.
Execution.
Yes.
Okay.
So it's kind of like the execution supposed to be on par with what actually CUDA can provide you, right? And like at least from my experience, if I compare code which I write in Mojo with stuff which I write in Rust or in C, it's all comparable. So like it's a real systems programming language, and it's also a general purpose programming language, right? Now it's the focus is more on AI, but generally you could build the full stack in just one language, having like being able to utilize SIMD, writing code for CPUs, GPUs, and maybe also other programming units. Depends on like what they will add on the compiler side. Okay. And also extensibility. They're kind of secretive about it, how extensible it's going to be, because they would like to kind of like pinpoint the things first, and then they will open up the stuff a little bit more. So like for example, the standard library was open source in 24. Max, all the kernels was open source in 25. And the compiler should come in 26. Any more questions?
Oh, thank you very much for the talk. I think, yeah, the examples that you gave, especially with, say, being able to put like inline assembly and inline MLIR kind of shows it can be quite flexible. But have there been any times that you've been working with Mojo that you wish you like get into the guts of the compiler and like kind of leave Python land?
Like it would help to see the dialects actually, because like they implemented their own dialects for lots of things for the in the compiler. They are lowering to LLVM IR. You can also just say like, okay, I can also plug in stuff on the LLVM IR level, right? But I think it would be helpful also to see the other like dialects, what they actually entail, and so on and so forth. It would be helpful. Again, depends on what kind of abstraction level you are working on, right? And the idea with the language is basically to say we can like create facades which are zero cost abstractions, basically, right? And then as a developer, you can actually like work in this abstraction, so it's all good. But again, it depends what are your ambitions, right? So how deep you would like to go and what kind of stuff you would like to build. Any more questions? Okay, then. Thanks a lot. Thank you. And then let's move over to our next speaker. So up next is Smail Nair with INS, Haute Force, and CNRS. So Smail will give a talk about hardware-aware AI, bridging model design, compilers, and edge deployments. And I think we're still waiting for the slides to come up on the big screen, but let's give him a backhand anyway. Here we go. Here you go.
Okay. First of all, hello everyone. So first of all, thank you for the workshop organizers for the invitation. So my name is Smail Nair. I am from the University Polytechnique de France and INSA. So today I'm going to briefly talk about hardware-aware AI and how this hardware-aware AI can fill the gap between these different levels in the design of models, of AI models. So I will talk about how it is possible to fill the gap between the design of the model, the compilers, and the edge. So first, I will briefly present what are the biggest challenges in deploying AI models on edge computing. And then I will briefly also present what are hardware awareness. And then I will talk about the different contributions my group made in this domain. And finally, I will present some slides on how code optimization, how compiler can help in designing efficient models for edge platforms. So as it has been repeatedly mentioned in this conference, in this workshop, designing modern deep neural networks and convolution-based models and transformers has or have a large number of challenges. Here I put, in my opinion, the biggest challenges. So here you have the required expertises. So you need to, in order to design a model, you need to recruit a large team of engineers, and you have to pay them, of course. And then so probably I will use it's this one. Probably better. Yes, and then you have to pay them, as I explained before. So this will impact the time to market, and for companies, this time to market is very important. Another issue which is very important is the CO2 emission, and probably you know how much these models can generate in terms of CO2. And finally, if the model must be fine-tuned, you have to pay the cost. So we obtain all these big numbers in terms of cost. So in total, we have something like between 10 to 100 millions of dollars to pay the people you recruit here. In terms of delay, you have to wait more than probably 2 or 3 years in order to obtain the model you want to deploy. And finally, there is this very massive carbon footprints. So in order to, this is one problem. And this morning, probably you attended the keynote given by Limin Shen, who also presented this big difference between what is required by the modern deep neural networks, transformers, and so on, and what the Moore's law may offer in terms of training and for the computing part. For the memory part, we have also the same gap as you see here. So this in red here, you have what you can use as a memory in GPU platforms. And in red here, you have what is the requirements in terms of memory. So the conclusion is that first, future ML models, it could be either convolution or transformer based, it doesn't matter. Needs are greater than what technology may offer or will offer in the future. And also, so technology scaling alone is not sufficient. I think this has been mentioned several times in this conference or in this workshop especially. And we need to propose new techniques or new framework in order to design and to propose both the models, the models you want to implement, and also the hardware. And for this reason, co-designing or co-optimizing software and hardware is very important. Okay, so in terms of optimizations, here in this slide, I tried to classify the different techniques from the algorithm level to the more, let's say, electronic level. So here we have the algorithm level where it is possible to use neural architecture search and different kind of techniques like quantization, distillation, and so on. Then you can also optimize your code using the software level or techniques such as compiler optimization, transformation, fusion, and also using the transformations that are possible using the different kind of compilers like TVM, MLIR, and so on. And also the next level will be the architectural level, the hardware level, when it is possible to choose between different kind of implementations, going from CPU to GPU to TPU, and also to propose domain-specific acceleration, including systolic arrays and data flow architectures. Then you can optimize also the memory. You can fill the memory gap using new techniques. And in this conference, several presentations try to attack this problem, how to include near memory computing, in-memory computing, and so on, how to propose new techniques for analog and digital memories, or combining mixed signal AI. And finally, you have the new paradigms using quantum computing and this kind of photonic computing and so on. So what is important to mention here, what is important to notice here is that, I mean, if we want to optimize the system, we have to combine, we have to co-optimize, we have to have some approach where it is possible to mix between the different levels. So this is the I think the most important thing to mention here. And in the group, what we try to do, we try to see if it is possible to combine neural architecture search with the code transformation, with the software level. So this is what I'm going to present in the rest of my talk. So very briefly, so this is the neural architecture design. So if we want to design a model, so this is the classical way or the generic way to propose a model. Here you start by generating neural architecture generation. So you take a code and you try to optimize the code to obtain your model. Another possibility is to use neural architecture search, and I think Olivier in the morning explained very well how neural architecture search. So I can go very briefly in what is neural architecture search. So in this case, we try to choose or to build a model that is dedicated for this or this application, taking into account the data, the data set, the requirements of the application, and so on. And also, what is also important is when you want to use neural architecture search, it is possible to choose in this large space of computation, and you can add the hardware where, and to obtain the hardware where NAS, and you can add the target or the constraint of your system. So this is the three possibilities you may have. So in another possibility here is to, oh, what's happening here? Something. Yes. So the fourth possibility here is to have hardware or co-optimization. And in this case, you have two search spaces. You have the search space, which represent the models as in the neural architecture search. And to this search space, you add a new search space, which consists in the hardware. So in this case, the idea is to explore two search spaces and to try to find the best matching between the requirements of the model you built from scratch using NAS and the requirements or the possibility in terms of hardware. How are you going to implement or to deploy your system on edge platform? So this is the idea. So depending on the requirements, it could be interesting to use a different kind of approach. So one question which has been, proposed this morning in the keynote is we know that models is progressing, or hardware, let's say ML models or AA models is progressing very quickly. The opposite, hardware is progressing with a very low speed. So how, let's suppose we have new models, how it is possible to propose or to implement this model very quickly. So this is, using or designing hardware from scratch, and this hardware we want it to be dedicated to this model is very difficult. It will take time, and the time to market will be probably long. So in this case, the best possibility is to use hardware where NAS, and in this case, it is possible to optimize the model for the new platform or for existing platforms. One of the method we used in the group is to, for instance, use DVFS in order to reduce the energy and to optimize the latency and so on, as I will present later. So this is the conventional neural architecture search components. So here we have the first component is the search space. So in the search space, we have a set of operators, and also how these operators can be connected. So we have many a large number of NAS search spaces with different kind of operators, like different shapes or different sizes of convolution and so on. The second component is the search algorithm. So the idea here is to explore very quickly the search space by trying to evaluate the accuracy of the different candidate in the search space. And for this reason, or for this purpose, we have the evaluation model. So the evaluation model could be something which is based on full training or partial training, or using accuracy predictor surrogate, as called in the domain. So this is the conventional way to design NAS. So if we want to include hardware awareness, or if we want to tune or if we want to optimize the model to dedicated or target hardware, we need to enhance, we need to add to the NAS, to the conventional NAS, the hardware search space. So in this case, among the different parameters we may include in the hardware is the different tiling sizes, the number and type of processing elements, and the VFS, as we did in the group. So then we have the search space here. And this space, it could be based either on reinforcement learning, genetic algorithm, or gradient based. And then we have let's say two components. The first one is how to evaluate, as before, the accuracy. And the second one is how to measure or how to predict the cost of the hardware. And for this reason, we need performance predictors in order to speed up the search. And finally, we have the best model. And one of the classical technique, or what is proposed in general in the literature, is to apply at the end of the pipeline different kind of optimizations or compression techniques, such as quantization, pruning, and so on. And in the group, we demonstrate that this approach is not optimal. I will explain the reason why this approach is not optimal in the next slide. So here I will give some contributions of my group. So the first contribution was to present a survey and taxonomy, and the paper has been presented in ISHCAI, I think 2 or 3 years ago. And we have a long, very extended paper in archive. So the second contribution was in developing different kind of surrogate or performance model predictors for CNN and on edge GPUs. And the third contribution was in attacking the problem of multi-objective hardware-aware neural architecture search. So in this contribution, what we demonstrated that if we want to measure the different, let's say, cost in terms of accuracy, execution time, power consumption separately, it is not optimal. It is not interesting. And instead of doing this, instead of having different predictors, the idea is to merge all the predictor in one function. And this function will predict or will try to obtain the Pareto rank, then instead of predicting each objective on its own. So this is the main idea, because at the end, when we search or when we explore the two spaces, the accuracy and the cost, we don't need really to obtain the exact value in terms of performance. What is important to obtain is the best solutions if we are interested by the Pareto front. So this is the third contribution in the domain of hardware awareness. And then we try to see how to include compression techniques such as quantization in the pipeline. So the solution that is presented in general is to apply a quantization or pruning at the end of the pipeline. And this is not very interesting because sometimes for some cases, for some models, when we do neural architecture search, you may have two models, A and B. So when you try to explore the spaces, the two spaces, A could be better than B. But when you apply quantization, the situation could be in the opposite. So in this case, the idea is to include quantization in the search space. Okay, so here the idea is to not to do quantization or pruning here at the end of the search, but to include them in the model itself. I mean, in the search space. So the problem is that, I mean, if you do this naively, probably the search space can be huge, and this cannot be accepted because probably the exploration time will be very important. So the idea is to use a predictor, to use a surrogate, to use AI, predictor to convert or to help you to converge very quickly to the most important or to the most interesting quantization values in order to obtain very quickly the most quantization technique. So finally, the fifth contribution was in trying to apply neural architecture search, dynamic neural architecture search, or what is called early exit, if you want, and combine this dynamic neural network in DVFS to reduce the latency and energy consumption. And finally, we tried to combine neural architecture search with compiler optimization. So this is what I'm going to detail in the next slide. So the idea is to see if it is possible or if it is interesting to extend the space of the models by including the different code optimization. How it is possible to combine or to play with the neural architecture search and its different values in terms of models and the code optimization, the optimizations that are provided, that are proposed by the compiler. So, I mean, is it interesting to apply code optimization at the end of the design choice, the model session, sorry, or is it interesting to include this code optimization in the search space? So this is what we try to explore. And here you have this in this figure. You have, for instance, four schedules. One schedule consists in applying a sequence of code optimization, and we try to measure the speed up and the acceleration here compared to the reference, to the model you obtain or the execution time you obtain when you don't apply any optimization. So what we can notice here, we notice that depending on the model you use or the model you are interested by, the optimal or the best schedule could be different. For instance, here, yes. For instance, here we see that for VGG 16, okay, the best schedule is schedule number 1, and for this one, for ResNet 34, the best schedule is schedule number 2. So this is very important, and vice versa. For instance, here for ResNet 34, the situation is different. So we have the same. We obtain the same conclusion with the other schedules and with the other models. So at the end, the conclusion is that compiler transformation is not universal. So depending on the model you apply, different schedules could be optimal or not optimal. So this is very important. And the second conclusion is that code optimization, if we apply code optimization independently from the model, we obtain something which is suboptimal. So for this reason, I mean, it is interesting to, when you decide on which code optimization you want to apply, it is important to take into account the model and how the model is built, what are the different operators you have in your model, and then selecting the best schedule. So for the then we try to see in the literature what are the how it is possible to combine NAS and compiler optimization. So we have two possibilities. The first possibility is to do this combination in two stages, in two steps. So this is what I explained before, where the code optimization is not the end after the model has been selected, or to merge to do the two steps, selection of the model and code optimization in the same step, the same process. So this is called one stage search. So in the first approach, in the two-stage search, we have two approaches. In the first one, we use hardware-aware neural architecture search. We obtain a model, and then we call the compiler. The compiler gives us an optimized architecture, an optimized model, and vice versa. We have this loop. The second possibility is not to work at the model, at the whole model, but to decompose the model in different blocks, in different layers, if you want, and this will probably gives us a better model in terms of optimization. The second family or the second category is to merge, as I explained before, to merge the two steps in one step. And here also we have two possibilities. The first possibility is to have the same big or one big search space, including models and compiler optimizations. Of course, this could be very simple in terms of design, but the search time, so I mean, the search algorithm will probably need a long time in order to converge. The second possibility is to have two search spaces and to try to understand how the combination, how the matching between the model and the code optimization works. So this is what we propose in the paper. So the paper has been published recently in Journal of System Architecture. So let's see what are the propositions we made in order to enhance hardware awareness with the compiler optimization using dual search, using the one step, and how this code optimization can be combined with hardware awareness. So in hardware awareness, search space is limited by predefined operators like convolution, batch, normalization, and so on. And we know that convolution layers makes the CNN performance, but costly. So the idea is how it is possible to have these two stages. Okay, the first stage is in the first exploration in the approach with two stages, promising network are often dismissed. So I mean, if you try to use the two stages as I explained before, sometimes you select a model, and when you apply code optimization, this code optimization does not give you the best model. The reason, as I see here, is that the best model may appear inefficient before optimized by the compiler. So for this reason, the idea is to use one stage and to combine the two spaces in one space. And this is the first idea, and then to also to find alternative operators in order to replace convolution by less costly operators, but which can give you in terms of accuracy something which is very close to what you obtain with convolution. So we have two ideas. First, combining the two spaces in one space for combining hardware awareness and code optimization, and replacing the convolution by something which is less expensive in terms of computing. So I have to go very quickly. So the idea is to propose CompNAS, so a compiler integrated neural architecture framework. And in this CompNAS, we propose an operator level NAS. And the idea behind CompNAS is to to transform the models in graphs of low primitives and to construct a candidate as a DAG, DAG of primitives, and to discover a new computational graph in order to replace convolution. A graph can be either unary, binary mathematical functions like square root, matrix multiplication, matrix addition, I mean the very low level operators, or a constant. And this, in the search strategy, we use an evolutionary algorithm, genetic algorithm, I mean to be precise, in order to explore the different candidate and to replace convolution. And we explore a large space of operators that is hard to optimize. And we have two scenarios, two possibilities. The first possibility is to have a random initialization. So in this case, we start from nothing. We build very elementary operators to replace convolution, or to use the how to say the background or the proposition or the operators that is proposed by the designer. Okay, so in this case we use the optimization passes of MLIR, and we try to mimic the original implementation of convolution using this paper, the paper you see here. And so this is what we obtain in terms of performance. So as you see here, we have this. Here we have the accuracy, and here we have here we have accuracy, and here we have speed. Okay, and so here we have two benchmarks: the ResNet 32 and convolution next. And we use this platform. So what we have here, we explore different layers, and depending on the approach, it could be either from scratch or using structural nodes or structural approach. There is a negligible loss in terms of accuracy, but with high speed up. So here we have the speed up, okay, and we have for these two benchmarks. So what is really interesting, for instance, here for this layer, so this is something which is in development. So it is we are trying to develop or to finish the development of this project. So here we have negligible loss, and we have something like 7x in terms of speed up. And here also we have something very interesting. Let's say accuracy in terms of loss, but with less speed up. So depending on the trade-off, depending on the model, and depending on the requirements, the user can decide to have higher speed up or let's say interesting speed up, and with a certain level of loss depending on the platform. So here the same we have for another benchmark. Here we have this kind of loss with this speed up, and same here we have close to 3% loss in terms of accuracy, but with a very high speed up. But for edge devices, this kind of speed up could be very interesting if we accept this loss. So the conclusion is that depending on the approach, it could be from scratch or from structures, we have trade-offs in terms of accuracy and latency. Conclusion. So DNN models are increasingly larger to fit the edge platforms. So for this reason, hardware awareness could be an interesting solution in order to find the efficient deep learning architecture for different kind of platforms. CompNAS, as I presented here, may propose or may define, may find new operators in order to replace convolution with a certain level of accuracy loss, but with a significant speed ups. We have a trade-off between the two approaches, from scratch or from manual construction of the models. And finally, for future work, we try to finish the experiments. We try to extend CompNAS to other deep learning networks, and to try to, if it is possible, to enhance the design or the space by new models, by new operators. Thank you.
Thank you very much. Thank you, Smile. Great work. Thanks for showing to us. So any questions from the audience to Smile? Okay, let me get started. So Smile, one question. I mean, I've seen you done a lot about CNN. So I'm curious, what about transformers and LLMs? Have you worked with them or have you seen any research? How do people think about NAS on transformers and LLMs?
Yes, I think yes. Thank you for the question. Yes, of course, it is possible also to apply neural architecture search or hardware NAS for LLMs. So this is something which is in progress in my group, and I think the applying NAS or hardware NAS for LLMs is crucial, because probably, as you know, in terms of processing requirements and memory requirements, the requirement is huge, and I'm sure the NAS could be very beneficial for LLMs. But this is something in progress, and in this conference and in many workshops, in this conference, people try to propose different solutions like in-memory computing, compression techniques dedicated for LLMs, and so on.
Perfect. And this is something for next year.
Yes, probably. Yes. I hope to see you next year.
Perfect. Any further questions before we close? There's one more from the audience.
Yeah, thank you very much for the talk. Some very interesting stuff. Like, is there anything that you could give to our, like, in your experience, were you looking at anything around giving hints about how the hardware works and like what kind of memory hierarchy and other things it might have that could help with the search process? Or was the search process good enough when just like running benchmarks and building up these cost models and stuff?
But your question is about the memory, yeah?
Well, I guess my question is like having a representation of like the hardware features and if that could help in the NAS process.
Yes. So let me rephrase your question. So the question is it possible to analyze, to profile the model in order to extract some information to optimize the memory, isn't it?
I guess in a sense, like have a representation of what hardware you're deploying to help with the NAS process to know that, oh, I've got this much memory, so I should probably make a layer of this size.
Yes, I agree. Yes, I think for memory for the moment, we didn't work on the memory requirements, how to optimize the requirements of memory. But I think the two possibilities or the two alternatives are possible. I mean, in my opinion, we cannot separate the processing part from the memory part. Why? Because for some models, it could be either convolution-based or transformer-based models, it doesn't matter. But depending on the model, for some models, they are computing bound, and for some other models, they are memory bound. So I mean, the design or the framework you are going to present or to design must take into account the requirements of the system. I mean, you cannot propose something which is fixed, which is static, and say, okay, this is the best approach, and we can support any models. So the framework or the model you propose must analyze the needs of the different applications or the different models in terms of processing and memory and propose efficient solutions.
Okay. Just no further questions. I think, Michael, in view of time, I would suggest we.
Okay, then thanks again, Ismail. No. So I'm not sure if the camera is working. Sebastian, could you come up? There is hopefully the last one. So it's not going to turn on the camera. You cannot turn it off. On. On. Unable to detect the camera. Did we unplug? Is it unplugged?
It's interesting. Well, there's at least a camera in the mic in the laptop, right? Michael, in view of time, shall we go without camera on the last one? Because the screen seems to be working.
Yeah, maybe let's try to fix it during this stream.
Well, let's do one more thing. Let's unplug. Let's unplug the camera.
Is the camera?
Yeah, it's the camera.
What's the?
I think it's on. Plug it back in. Thank you. And you need to.
Okay, while we are waiting, let me quickly get introduction and before we get started. So this is going to be the last talk. So please stay here to the end. We will have a surprise at the end for everyone who endures to everything and stays to the end. Now we will try to get the camera working as we talk. It seems not even the laptop camera.
Exactly. It doesn't recognize any camera. It seems like Zoom needs to start or something. I would suggest share screen and go with that.
Yep. Okay.
So, yep.
Okay. Our last presentation is by Irina de Albuquerque. So she's with CEA in France. So, and she's going to present EICH, the collaborative and open source platform for Edge AI. Let's welcome Irina. Thank you for coming here today.
Hello, everyone. Thank you, Michael, for the invitation, for the introduction. So today I present you this research project that we've been doing in my lab. I mean, it's a collaborative project, as I will show here. And it's mainly a research project that's been going on for 3 years now. And we came from so far. We've done a lot of great things. I'll try to show you most of it. So it's a project in collaboration with many industrial and academic partners, and So I think I don't need to justify this part about Edge AI. So you're talking about. I mean, we can agree now. This is more than an opportunity. It's a necessity, right? Moving the deployment from the cloud to the edge, and. What we have observed is that we need an open and a serving software structure to tackle the challenges that come with this new paradigm. And this software stack that we are trying to develop, it has to, of course, above performance, which is essential, there are many technical challenges that we have that we identified from the very beginning. So you have to assure our competitiveness in this domain. We defined some objectives. So you're talking about having the control of the model manipulation. I mean, I'm talking about machine learning models and optimization. We have to be able to integrate innovative paradigms for reliability and frugality. And we have to be adaptable for different hardware if you want to have our place in this domain. So what are the solutions for embedded AI today? You have a lot of tools with stronger orientations and dependencies from the software to hardware and everything that's in between. I'm not teaching you anything new. And what we are doing, so it's what we call edge. It's a deep learning framework dedicated to embedded AI. So what is our objective is to have this end-to-end interoperable framework, including optimization and deployment. We have developed this modular library with a light core, with different plugins, and very few dependencies afterwards. And the very important thing, it's completely open source. It's hosted by the Eclipse Foundation with our permissive license. So here's a overview of the framework. So going down from the design to the deployment. So here, so yeah. When you talk about design, you have some features. So we have this, what is important is the interoperability with different machine learning frameworks that are already the state of the art. So it's important for us to be able to interact with them if you want to be relevant. Inside the Edge, we have different tools for analysis of the machine learning models. So I will go into details right after. And then what is really rich in the platform is the intermediate representation that we have developed, that helps a lot with, I mean, that's really, that was designed for using model manipulation and optimization. So a very strong point is the edge on Unix interoperability. So we know in Unix it was developed to be to have this exchange it's exchange format, so to have this to communicate between different frameworks, and the Edge has been built around this concept as well. So it's really easy to load in a non-Unix model inside Edge, manipulate the graph, and go back and output a non-Unix model. We have a very straightforward functions to do that. It's so they are mainly encapsulated in the Edge on NX model. And you have this function to load on NX, to export our graph in on NX in different formats as well, you see, but especially on NX. We have this very powerful plugin with Google's Model Explorer that has been adapted to understand Edge's internal representation. So you can you have this what we call the Edge Model Explorer. So it's basically it's a very powerful tool to visualize and play with your computational graphs. So here's an example of how we can visualize different levels of the graph. So we have this big LSTM operator, and then you can go inside and see every operator that composes it. We can also add different, how do you call that? Visualization schemes to our model. So here, for example, you are selecting all the convolutional layers and saying that, please in this graph, mark the convolutional layers in red. So it's something that is completely, I mean, you can define rules for pretty much anything that you wish. Or you can define size of kernels or something like that. Please find the convolutions that are followed by ReLU activation functions, for example. You can also afterwards search, that was in the end of the animation, but you can afterwards search the models and the operators or when combination that you desire and just show them. And so yeah, I will go through some key features of the Edge's internal representation. So what we like to say that the computational graph inside Edge is completely transparent. It's never implied from the code. The user has to define it. So as you been seen before. We have this high-level Python API, so it's really easy. I mean, it's pretty much like other machine learning frameworks that you may be used to work with. So the user can define each parameter and the specifications of each operator very easily. You would like to say that this you have this multi-paradigm abstraction model. They're not limited to tensors. You can just talk about a consumer-producer model, for example. So it can have also different levels. I mean, you can talk about a node. We have this notion of graph view that will be just this view of a graph that you define, composed of the nodes that you set up, that you decide, for example. So yeah, you have this this way to deal with different granularities. Very easy. We have what we call meta operators that can be pretty much anything, like a composition of operators. You can define what you desire to be included in your meta operator. So you can it's a very simple example. Have this meta operator as the padded conv. So it's just essentially a pad followed by a convolution. And then depending on what you're doing with your graph, you may want it to be exposed, or if you don't care, it can just be a meta operator and do with that. So again, very easy functions to just go in each way. So, and then, yeah, so you have a saying, you can transform your graph to match the granularity that is required by your implementation. So you saw about the LSTM operator that you can expand, fuse as you wish. We also have what you call generic operators. So I was saying we support a lot of on Unix operators, but if you load a model that is not which operators Edge does not support, I mean, if there are operators that Edge does not support yet, it will just sorry. Okay. So Edge will just let you do your import and just say, hey, this operator, I don't know, are you treat it as a generic operator? And then the user can go afterwards and say, okay, this operator is a new one that I've created or something. So I define an implementation, I bind the implementation to this operator, and it will just work smoothly, more or less. And then Edge's graph is a searchable graph. Actually, we have this implemented this pattern matching engine that you can essentially look for the graph to do pretty much anything that you wish. Here we are talking about. So you have the Dino V2 on NX, which is really big, and then we try to fuse it to some meta operators that will just be enough for my presentation, for example. And then we can define the rules. For example, here have if you have a mat move followed by an add operator, just say there is a linear and fuse it into a single operator, a meta operator. So yeah, that's something that we can do very easily. And yeah, we have some graph transformations like constant folding. Those are what we call recipes. There are a lot of them that are already implemented in Edge, but also, again, the user can decide pretty much any new recipe that can just modify the graph as needed. And we have this scheduling based on the graph that is static, right? I mean, it's just a representation of how the different operators they can be scheduled, they can be treated, processed, for example. So you have different scheduling strategies. We can define, for example, if you want to biggest operators to be scheduled first, or I don't know. We have a lot of around 5 different scheduling strategies. So there's something that also can be expanded, of course. And then we also have some tools for analysis of the model. I mean, static analysis of profiling of the model, just to get, for example, the number of floating pointing operations, integer operations, for example. That's something that, again, as everything can be extended, of course. So yeah, when I was talking about the optimization of the graph, you have this tool for automatic simplification. We have implemented techniques for quantization. So we have post training and our accurate quantization our training, and you have also implemented some techniques for tensor compression. Again, extending the state of the art and sometimes just implementing research papers. So how I was saying about the Edgeonenix cleaner, it's a automatic optimization path that you can go in that you can do in your graph. Again, the type of optimizations, they can be they have different levels, and if you want to keep you can do approximations in the graph. You can maybe just say don't touch the operators themselves. So you can select which optimizations to do and the order in which they are executed, of course, and you can create recipes that you think that are useful for your use case. And concerning deployment, we have a lot of so we have this code generation strategy that is that targets a wide number of hardware targets. We have a big part working on building trustworthy, having this trustworthy deployment, mainly oriented for aeronautical certification. So that's why it is important to have this this workflow that is completely transparent, and it's the user can go in and go out anytime they desire to see what's going on. Each transformation can be traceable. So it's something that we have working on. Of course, there's also some work going on, hardware fault testing, for instance, with hardware fault conditions. And most recently have implemented this benchmark module that aims to compare inference time and the output results with different frameworks from the literature, notably ONNX runtime, PyTorch, and GVM is ongoing work. So yeah, how I was saying about this code generation engine, it's based on templates. It's completely open and transparent. We don't by default generate binary code. So of course, afterwards, the user do what it wants, what they want, but it's not something that we do by default. So you can generate C, C++, HDL code. So, and of course, the code that is generated by default is just a C++ code. So it can be extended with specific primitives. And yeah, so I mean, to define an operator, you have basically to specify the data type that is used, the data format that you desire, the dimension range in which it will operate, and some other attributes that may be specific to the operator. And then, for example, based on all the specification, we can do some automatic graph adaptation. For example, here we have this graph, and then I said, I want to export it to CPP, and please adapt it to the backend. And then I know that for my hardware, for example, the optimal is to have the channels last data layout. So you just say adapt to the backend, and then the graph will be transformed to be current, more adapted to the backend that I desire. And then Yeah, we can also here it's just an example where I know that for my hardware, I don't know, I have a specialized processing units for matrix multiplication. So you say, please in the graph just transform convolutions for matrix multiplication. That's something that we can do as well. So some example about tiling matrix multiplication operators or convolution operators. We have these recipes that exist already. So it's but again, it's something we can pretty much add anything that we want. And yeah, we can also have this, it's a really preliminary concept, but we can have what we call the memory manager. So when the source code is generated, let's say C code, we suppose a single memory buffer, but you can already output the memory layout of the intermediate of tensors, and so the user can see their lifetime, for example, for the buffers and the adaptations that may be required. And so it's an overview for the code generation export that we have. So export is the name that we use for the output of the framework. So we have, how I said, this generic CPP code that is afterwards completed with a specific code for target a special particular course. So I mean, all of that is done by different partners. We have how I saying this code that is generated specifically for certification. To have this part, we have some code generated for hardware, for proprietary hardware, also for the partners' desire. So they implement it. It's really it was found to be complemented in this way. So yes, I was talking about the benchmark model. It's so the goal is to really to compare the different mainly inference time and the precision in terms of floating point precision, for example, during the execution in Edge and different frameworks. So yeah, we can benchmark the whole model, or you can benchmark operator by operator. It's really the user can go at the level that it can explore the graph in different points. So yeah, we have a lot of work going on. So it's this project that has many partners, as I said, and we have some. I sit here just some features that we are working on. So it's we are adding the support for SNNs. We have this adding some optimization, some quantization techniques for transformers. And as I said, for the code generation, working on the certifiable generation, and also a lot of work going on about compiler optimizations, about the code that you generate. So it's a different approach done by our partners in Urea. And so yeah, if you want to know more about the project, don't hesitate to come to me. We have, as I said, it's hosted in Eclipse. So the GitLab, it's pretty much, I mean, it's really active. You have a lot of members working on. The documentation has improved a lot this last month, I can say, but we still have work to do. And very importantly, you have a lot of tutorials. So essentially all the topics I mentioned here, they are available as tutorials. So, and we use a binder to facilitate the user integration. So please just, if you're interested, just go take a look. And yeah, you have this the chat if you want to get in touch with the different developers, really don't hesitate to be really help to integrate to communicate with everybody that can be interested in our project. Okay, thank you.
Thank you very much, Irina. Yeah. Okay, any questions from the audience?
Thank you for the presentation. It was really interesting. You mentioned certifiable C code generation for like aeronautics or things like that. What do you mean exactly by certifiable? Like, is it the compilation phase or what is it exactly?
Yeah, thank you. So what it is essentially this model is called Aceton. So it's essentially a C code generator that is so the C code that is generated, it has a specific layout. I mean, we just avoid some like a dynamic memory allocation, for example. So it's a C code that can be afterwards easily analyze it to infer, for example, worst case execution time bounds. So it's I mean, it's essentially a C code that was designed to be afterwards studied and potentially certified. So it's essentially a workflow that follows the what is done in aeronautics domain industry.
Okay, thank you very much.
We can talk later, but it's my thesis subject, so I have to discuss that.
I'll look into it.
Yeah.
Okay, further questions?
Thank you very much for the talk. Yeah, like the C code stuff is interesting. I hadn't thought about it from the certification side before, just like the kind of sometimes you've just got platforms that you've only got a C compiler as a tool chain, so it could be very useful. In the environment that you've been working in, how much performance is coming from the C compiler doing a good job, or is there more work that happens in terms of making the template for the layer fast and efficient?
Yeah, sorry. Essentially, that's a very good question, but it's again something that I really worked really hard during my thesis, because in this domain, we cannot rely on compiler optimizations pretty much. I mean, there are some compilers that are adapted to perform the optimizations that are aeronautics compliant, for example. But essentially, the approach that we take is that all the optimizations that we do, try to do that in the C source code and not rely on the compiler, because I mean, for example, it's kind of hard, but one of the constraints that we impose ourselves was to compile using O0. So you are at this level. So yeah, so I mean, we can add assembly blocks, for example. That's something that we did for matrix multiplication blocks. We used a compiler as assembly blocks. So that's something that we can do, because we can be able we can master that, and you can prove that it behaves as we desire, right? So yeah, so it's pretty much let's say we don't rely on compilers at this level, of course. So it's just.
Hello, Irina. So I have a comment. I told you yesterday that it's very cool, this tool. For future where you put that you would like to target spiky neural networks and also transformers. So I wanted to make the same comment that Ismail received about the LLMs, but you already mentioned transformers. So spiky neural networks, I mean, transformers, which are based on GGUF format, which is different from CNS, they are different types of models, right? So it seems like a quite ambitious, future, right? So you want to cover many things. So how do you envision this, right? So covering spiky neural networks, transformer LLMs, and moving forward what you have now.
Yeah, actually, for the history, Edge it started as the thesis project, the PhD project of my supervisor that was working on SNN. So it's something that they already done. But for now, as I mentioned, we have a lot of partners. So we do have people that are specialized in that. And what we do is try to have this framework where everyone you find their spot and you try to plug in their ideas. So yeah, it's really ambitious. I agree, but so essentially, you have this core team that is mainly working on making the Python API and everything work, and then you have different groups that come with their ideas. So I can put you in contact with every group that that does everything. So yeah, you have a lot of people.
Oh yeah, yes. Apologies. It was quite comprehensive from the start to the end. So yeah.
Hi, great talk, Irina. So about the being a platform for research, if I have custom quantization over training passes and I have custom data formats that are not int8 or int4 or FP8 that you mentioned on your slides, how difficult, first, is it possible? And then how difficult is it to use Edge to implement those?
I cannot say how difficult it will be to do that. We have different, we support different data types of different precisions. And yeah, I mean, I want to say it is totally feasible, and I can totally tell you who to look at, who talk to, and yeah, I mean we have how they said we've been working on the documentation, the tutorials, and then it's really in active development, so it's definitely something that can be done, and I mean we can. I cannot answer more precisely than that. I'm sorry, because it's not me who is working on quantization. Thank God, but yeah.
Okay, if there's no final question.
Thanks again, Irina. Okay, with that, I think we can close CODAI with the last session. So thanks everyone for joining. Thanks to all the speakers, all the participants, everybody who asked questions, all the technician here.
Yeah, oh yeah, absolutely professional here. Thank you very much.